Uh, Today we have a live stream, and it is actually a real live stream, so you can ask me questions in the chat, and when I glance there and I see them, I can kind of talk through. I'm aiming about maybe 1 hour, hour and a half talk, and that's my kind of long-term goal was to start doing these live streams and talking about some scientific papers or publications, which I don't have time to like make separate videos for, but I was thinking to make like a just a live stream, recording, discussing, showing through, and don't spend so much time for editing, but so just I can go through more material. And one of the books, it's a collection of the scientific work, which I personally know the authors and been working with, and really appreciate the work. And it's one of the topics which very important, but not so much covered, I think, in kind of like general science. I want to dedicate my time to this in several live streams. And because it is a book, so I'll just go show you that it's been published in 2018 by Elsevier, and it's Rockslides and Rock Avalanches of Central Asia, Distribution Morphology in Internal Structure by Alexander Strom and Kanatbek Brahmatov, Russian and Kyrgyz scientist, very leading basically scientists in the world in this topic. And they give me a green light to talk about this in my live stream, so I'm very happy to do that. So without too much description and introduction, what I'm going to do, I'm just going to make these videos. We're going to go through the book, more interesting chapters, and I have my Google Earth Pro here, so I will probably switch in between the book and Google Earth, showing some locations, some places, if I have something to say about a show. And we will just slowly go through this interesting book. The book is essentially its collection of whole life, long-term research of these dedicated scientists and the people who work with them, students they taught, and so on. And it's very important, very amazing, and just open new world of history, development, landscape of Central Asia, and how it's applicable to wherever you live, whatever we have, topography. It's very important topics. And it's just fascinating if you start diving into these topics. Also, I'm planning to do more like going through some papers, research papers, maybe some field area which I'm not familiar with. So I'm just going to go with you together and dive in and read through, see what modern science tell us about what's happening. So as I understand, this book you have to purchase, I think, but the parts of the chapters for this book, they've been published in many, many, many articles, papers through the lifetime in different languages. And so basically, I like this type of books because they nicely summarized, organized. There's all the references are given. So for scientists, it's like a very nice way to present long-term work through years. So let's just, without delaying, dive through. I will publish this video not just in the live stream section, but also I will just make like a short, just the videos, cut it through and published into my main channel video list. So please share it, like it, and so my work doesn't go for nothing. All right, let's come back. I just need to a little bit figure out how should I switch. So I'm here. Oh, I already have 9 people watching me. That's amazing. So if somebody can write me something so I can see the chat is working, that would be great as well. So Rockslides and Rock Avalanches of Central Asia. Rockslides, that's a big book. So I'm going to just go through this book and go see what's happened there. So there's obviously the dedication of the book. 2 beautiful wives, Tatiana and Gulnara, and actually both of them I met in my life, so it's hard to be wife of the dedicated scientist who constantly somewhere in the mountains, so that's the reason, probably the dedication for all the life support. So the content, so what we have in terms of the content, introduction, we're going to go briefly through part 1, general information, brief history of the bedrock landslide studies in Central Asia. So here we're kind of going to talk about, why the authors decided to publish this book, why it's so important to study this, overview of study regions. So there's a little bit of, probably going to go a little more briefly through that section, geology, tectonics, Tectonics, so it's kind of like Tectonics is a recent what's happening in that area. Geomorphology, what type of landscape you can find there. Seismicity, so what's happening with the earthquake, how active it is. Climate, glaciation, hydrology. And that's very important because this is kind of my part. I connecting glaciation and recent geomorphology of the area and climate change as well. So this kind of like how it's all connected together, because we know the climate is constantly changing, and it's been changing last 100 years, last 1,000 years, and so on, and it's have direct effect on the landscape. And things like landslides, rock falls, all this movement of the material, very much related to climate change. So it depends how much rain you have, whether your glaciers, they retreated or they're coming, all these things. It's all interconnected. And that's why we have such a dramatic landscape in the mountains, because of all this effect and how they interconnected. But another very important part, and here I think Sasha will and Kanadbek talk about this, it's the connection to how to understand, so how to interpret the landslides, because one of the main problem, and I've been twice with Sasha in that areas, and he was telling me that one of the main problem that it's understanding, like underestimation of this big catastrophic landslides, rock avalanches in the landscape. So more often and most of the time they just discard it, so people just don't see them, people just don't know that they exist. So one of the work they do, they reporting all these landslides, mapping them, identify them first of all, and identify them from other type of geomorphology, like for example glacial stuff, and then showing that this actually more often happened, and it's more probably going to happen, and it does happen today. We know it's happened last 100 years, and every day there's somewhere landslide happen on this planet, unfortunately. Well, it's normal things to do, but it's unfortunate for the people who might be damaged by that, So then they're talking about better landslides types and classification systems, so that's kind of cool stuff, which I'm interested. So what's actually, why we say sometimes rock slide or landslide or rock slope or rock avalanche, so what the difference, and they have specific little bit kind of like classification for the area they study area, how they distinguish for themselves. The bedrock landslide database, so that's just showing how they mapped it and what type of information you collect when you report those events. Part 2, it's regional description, so now we're going more specifically in study sites. So Jungaria, that's where, as I understand, there'll be some landslides reported there. Tanshan, the most, I think, the main bulk of the work done there, and it's more probably the territory of modern Kyrgyzstan, country of Kyrgyzstan. But like back in the day, it was all Soviet Union, all these territories: Kazakhstan, Kyrgyzstan, Tajikistan, Uzbekistan, and China, of course, separate country. And some study areas will be on a China land, land of China. But today, it's all separate countries. But the work continues throughout, so like neighbor countries. So we're not like working specifically in specific country. And the Pamir's, I did some of my stuff there, and with the help of authors, and there's even we're going to the territory of Afghan, Badakhshan. So they describing here the study sites, analysis. So then they do some kind of understanding, what does the collected data tell us about, and morphological structure and evidence of rock slides, rock avalanche, and motion mechanisms. So it's very important, as in previous videos, if you listen, I talked about landslides, how they travel, what's happening. Some of them extreme, some not. So we classify them, and the different effect they have on the landscape. That's they're probably going to talk about here too, and a lot of examples. Structure, and, I missed the number 11, structure and grain science composition of large-scale bedrock landslide deposits. So how it's actually, because it's catastrophic, so landslide, as you can imagine, happened very fast, and how it's affected how it looks like in the field, so carapace and toe blocky, crushing materials within, contact with whatever it's travel over, is it demolishing everything in the way or just going to slide over, all these things. Next thing was looking at seismically induced rock slides, the discrimination. So why we think if it's happened because of the earthquake. So when you have like earthquake and straight away you have landslides happen next minute or same time or sometime after. But because I'm faced with a problem, like people ask me, what if the earthquake happened today but you have landslide 2 days later? Is it related or it's not? Like technically it's not the same time, yeah? So you would say it's not triggered by the landslide, but at the same time the landslide, the earthquake can cause some movement in the slopes of changes. And then in 2 days it will actually physically go down. So there's kind of a little bit gray area in the science and how to distinguish. So we'll see what they're saying here. Rockslide dams and origin, evolution, and failure. And that's a very important type of topics, and they put it as the last one, and it's one of them kind of have big interest in, especially in relation to glaciers, because you can have complication. You have in the mountains big landslide fall down, block whole the valley, and in the mountains you can imagine there's everywhere streams, rivers. So eventually the river will fill up this till the dam, this all the valley up the stream, and eventually all the dam gonna collapse, go through, and it'll be huge, like a tsunami type of flood happened, or it's gradually gonna just seeping through, or it's just gonna go over this deposit and demolish deposit, gonna bring a flux of material same time. You're just gonna see the landscape, but doesn't gonna do much changes. So it's all related. And my part of the research was also related to the glaciers. So you also have a glacier, and the glacier is very active. They're melting or they're going down, and you have these things when you dam it, and you have the landslide on top of it, complicated everything. And then when we have glaciers in the mountains, we have a lot of proglacial lakes, so this kind of water that accumulated in front of the glacier, this can just go down the valley and washed everything in the way. So it's a lot of outburst floods, kind of that's how we call it in science, hazard related. All right, evidence of slope instabilities, potential of future large-scale slope failures. The large-scale slope failures happened and still happening and recently happening in all these mountain regions, and like in New Zealand it happens, and in Central Asia, in Asia, in Himalayas, in South America, North America. It's a big and important topic, especially now when there's so many people on the planet, and people not just going to the mountains because they, some alpinists or trekkers can be damaged doing that, but there's a lot of people who have pastures, animals in the mountains, they live in the mountains, villages in the mountains. It's a lot of danger, yeah? So let's continue now. So just have a see the chat. Don't see any messages. And we continue. So let's go through the book. So first thing what I want to say, it's again about how it's important and related, and just to say that we have a very recent event. It's in New Zealand, Mamanganui, just on February 22nd. The slope of the Mount Manganui collapsed. It's not a very big mountain. It's not a huge landslide. But this landslide hit the campground, and unfortunately it's the holiday time in New Zealand, January, February, and there were families camping and 6 people died. So it's kind of like a devastating recent event. That's how it looked like several days after, as I believe, because already moved. There was just a campground here, and the slope collapsed. So in New Zealand, for example, we have GNS. I don't know how they call it now, but it used to be GNS. They just changed it last year, the name of the organization. So they're monitoring, they have database, they're watching these landslides, they're trying to identify them, see how active they are. And we're really focusing on the idea that what we should look at to give us warning, is the slope stable, unstable? Can we camp or build house or build a road? How should we stabilize slope or not stabilize, all these things. So it's important for us, just first of all, safety, our lives, our buildings, our construction. And then it's important, of course, for scientists in terms of, how the slopes evolved, what the climate effect, what the seismicity effect, what the geology effect, what's the, all other things, how landscape evolving, how fast these things happen. And some people argue the landslides happening, small ones, big ones constantly, and they more changing the landscape rather than just a normal erosion. Erosion just like when you're just moving slowly, bit by bit, material by the rivers from the slopes. Other people argue, no, the landslides are very important, so you can have one big event only once in a couple hundred years, but it's going to move as much as material that in the last 500 years you move by just the rainfall and smaller, like rivers, streams, events. All these things, like, you might not so important for you, like if you're not a geologist, but it's all tell us information about how our landscape developed and how we should plan the land, how we should use it, and all this kind of stuff. And people find in direct correlation with deforestation, building construction, destabilization of the slopes, all this stuff, and also increasing rainfalls in particular areas can cause destabilize the slope because saturated material, and it's losing cohesion between particles, and eventually slopes prone to go, more often than we expected, or they used to before in the past. So there's a lot of things to study slope stabilities. Yeah. And the Central Asia, it's one of the places. I'll just trying to switch now for the Google Earth. We're just going to a little bit go into the geography. One of the places in the world where we have so many, different valleys, landscape, and examples of these events. Huge catastrophic. There's a high seismicity. There's a lot of glaciers on top of the, a lot of rivers, lakes, different type of climate in different areas, glaciations, deglaciations. So all these things happen, and very, very high active, all this in the stand pushing into Asia part of the Eurasia. It's all causing a lot of seismicity here. The fastest uplifting mountains, the biggest mountains today, most active mountains today on our planet. So it's an amazing place to study. However, all this area, and we're going to read through today, I hope, this area all is being studied kind of like more Siberia, Kazakhstan, Kyrgyzstan, Uzbekistan, Tajikistan, even Mongolia, kind of more during Soviet times. There's a lot of research done, especially like in Pamir, Tian Shans, or Chinese studies happens, but there's not much, maybe it's like a blank area in a modern publication in a scientific community. Maybe because there's a lot of research done by people who published it mostly in local languages, so in Russian Soviet times or Chinese. And then we have a gap, 80s, 90s, when there's not much research done or been done, but not much published. So this kind of book trying to, close this area for that area, research area of Central Asia, specifically around Kyrgyzstan, Kazakhstan, a little bit of Tajikistan, Uzbekistan, to include it into the world's database. Because, for example, when you start looking for landslides or glacier studies, there's some areas like severely studied, and some glaciers are being studied, restudied, many papers, which is amazing, like you have such a good examples. But some areas you have numerous, you can even tell by looking through Google Earth, numerous examples of landslides or glaciers, landscapes triggered by earthquake, landslides, and amazing landscape, landform evolution, but not much published or acceptably published scientific papers there. So I'm very happy to go through this book. So Central Asia here, just show you. So we're going to, there's India, and we have a Tibetan plateau, of course. Mostly it's all China. There's a Mongolia here as well. And Kyrgyzstan is this little, they call it pearl, the gem of the Central Asia. Beautiful, amazing country located between Kazakhstan, Tajikistan, Uzbekistan from the west, and China from the east. And it's mostly Tian Shan, a little bit Jungaria. It's going all the way up through towards here, towards China. But it's Tian Shan, the Osh Valley, most of the lowland, it's most of it Uzbekistan, because kind of traditionally Uzbekistan people more occupy kind of lower rivers and valleys, and Kyrgyz were kind of like more by nature more nomads, so they have animals and they go to the mountains, horses, goats, and sheep and this kind of stuff, and they go with them to the mountains. And the Pamir similar, so the Pamir will be only covered the Alai range, and I have videos about this huge landslides here, and the glaciers, and so the for Kyrgyzstan, it's just Ale Valley, but then you have whole the Pamir. It's basically country of Tajikistan. Yeah. Big landslides events we know about this catastrophic and very important, and we should study this stuff because it's very important. This can happen any moment in that area and affecting people and lives and just change the landscape dramatically. You can see even from the space, like if you look on this Google Earth image, this is all the Pamir Mountains here, the Zalai Range, and Ale Valley. It's the most northern part of it, and you go here towards Afghanistan here, and we have you can see this Karakul Lake, and we have this lake. Yeah, so this lake is new. In 1911, there was a landslide, Zarez Lake, and it's dammed the river valley. Yeah, so it was just like another valley here, like this river valley, and it's blocked it, and it's all filled up with the water, and there's a lake now, which is well my any moment bridged. You can see the landslide deposit here. It's called the also dam. So the dam, there's the other part of the lake seeping through. So there's a big catastrophic event, and there's a big catastrophic consequence at any moment. In my, discharge or something can happen, another earthquake. Big landslide can fall into the lake now and cause big, like a tsunami type of wave, and cause catastrophe. So that's just like one of the examples for you, the one we can see from space of these things. And if you can travel through basically Central Asia in the mountains, you see more evidence of this type of things. This type of maybe I'm moving too fast. Landslides that blocking the look here. So we have a valley, and you see this the landslide deposit. Sometimes could be like a glacier causing, but I'm pretty sure there's a landslide deposit, and it's been reported. You see there's another deposit material here, so you see the beautifully blocked the lake formed. So it's very common, more common if you can imagine, and it's just because it haven't been so known by locals, but not so much reported. Maybe reported, but not many of us reading, scientific papers every day. There's many things like that happen in China, even recently, and already in the 21st century, when there's a catastrophe happens like that, blocking whole valleys, and people just disappear forever, flooding whole the villages that people occupy. So it's very dramatic, sad, and at the same time, that's the landscape, and we need to be aware of it. And one of the reasons it's all happening so more recently, more frequent, it's because of the deglaciation of the valleys. So the valleys, the ice used to be in all these valleys, so the Pamir used to be very heavily glaciated still, because there's a big glacier, so there's all the ice sitting there, and it's retreating, melting away. You have all this area open up, and the slopes become steeper, less stable. The water table changes. The permafrost, like where it's frozen, through all year round, moving the snow line, and they start collapsing and causing all these dramatic things. So let's just come back to the book. All right, so I will see. Yeah, I'm back to the book. See how far we go. We're going half an hour, and please tell me what you think. Any ideas, any comments, any questions? While I'm here, you can ask me. So chapter 1, introduction. Let's go briefly through introduction. Large scale catastrophic bedrock landslides or rock slides. So this basically, in this book, we're not looking on the smaller rock falls, when it's just a little bit of, it could be dramatic, but it's not this catastrophic. Excuse me. So here we're looking on the big events, and this big landslides belong to the most hazardous natural phenomena. That's why I just talk. Endanger people in the mountains regions. Yeah, but even not in the mountain ranges. It's probably also in further down the valley. Yeah, because we know when something can happen in the mountains and go down the valley. Usually narrow valley. If you have a lot of material, it can go many kilometers down the valley, up to 10 kilometers, and destroy everything on the way. Unlike common landslides and rock falls affecting just collapsing slopes themselves and areas directly at the feet, The simultaneous failure of millions and sometimes billions of cubic meters of rock can devastate vast areas, extending up to 5-10 kilometers, and exceptional cases up to 30-40 kilometers. And we know there's cases, even in my paper, and we talk about Karakoram up to, we're going in Alay Valley, we're going up to 40 kilometers travel path, yeah? And things happen. South America, we know they travel up to more than 30 kilometers and demolished villages on the way. Some of these mobile rock slides claim hundreds and even thousands of lives. Numerous disastrous rock slope failure occur in rather densely populated Alps. And that's kind of traditionally when the people start looking into these things, and you'll be said further down that one of the first mentioned will be Elm Rocks in 1881 avalanche in Swiss, part of the mountain system, and that's the first long run out rock avalanche had been described scientifically. Vajont, 1963 rock slide in Italy, Nippon disaster that changed the approach to the slope stability. And this kind of thing is very, very famous for people who study landslides. Worldwide known historical bedrock landslide in Northern Southern America can be exemplified by the 1903 Frank rock slide in Canada, 1859 Madison rock slide triggered by 7.5 big Hepton Lake earthquake in the United States. Yeah, Good Friday earthquake as well in Alaska caused a lot of landslides, and so on. Yeah, and very famous rock slide in Peru in 1974 as well. And Denali fault earthquake in 2002. That was a very big one, and it's caused a lot of landslides on the glaciers. 1964, the Good Friday Alaskan earthquake. In 2002, Denali. Luckily, there's not so much populated area there, so it's not many people died. Many other similar events occurred in Asia mountains outside of Central Asia region, which is out of focus. Yeah, among the most recent, we can mention 2005 Bala rock slide triggered by 7.6 Kashmir earthquake. Yeah, 2010 Atabat rock slide, and a huge one, caused the dam as well. Numerous large-scale rock slides that buried thousands of people were triggered by 2008 magnitude 8 Vinchuan earthquake in Sichuan. And the valleys there are very narrow, in the Sichuan region, and it's amazing the big landslides there. About 30 of them formed large landslide dams, and only enormous effort undertaken by Chinese authorities prevented the uncontrolled catastrophic outburst floods. You see, this not just the problem that has happened, it's also the problem what are we going to do after, what are we going to do with the dam? Shall we stabilize it? Shall we somehow slowly breach it so it's, reduce the water, and all these questions are important. But one of the first things you probably should do is evacuate the people. Large number of rock slope stabilities has been reported in New Zealand, Southern Alps, and how we know not just Southern Alps, also North Island. But here we're talking about the mountain areas. And the large-scale bedrock slope failure, much more the disasters than the collapse and rapid motion of gigantic amount of crushed rock debris itself, river damming resulting in valley inundation and subsequent outburst floods. So that's what we talked about, the complication of this event. Yeah. So talk about Chinese event, 1786 rock slide caused 100,000 people killed downstream. Well, that's what I will say, and you can have a look. There's more examples. All the above mentioned, as well as many other case studies from this region, are world famous and have been described in numerous papers and textbooks. Yeah. However, Central Asian rock slides are much less known by the international community of landslide researchers, despite the fact that this region, embracing the Pamir, Tian Shan, and Jugarian mountain system, that's what I said, it's considered one of the landslide hotspots. And because, as I say, many of them described in Russian and Chinese, it's not much, it's like a blind spot in the scientific community. analysis of worldwide landslide database compiled study general regularities of landslide damage and quantitative relationship between landslide size and mobility. That's another very important topic to talk about: how big they are, what they cause them, and how far they travel, depends on the valley, and what type of force is involved and what it's mean for the landscape. And it shows that not many studies, such as 1911 Usoy Rockslide, that's the one that I show you that caused a big scene from the space lake, have been analyzed. Our book aims to fill this gap to some extent and to provide brief information about numerous interesting case studies to attract researchers' attention. Following the picture worth 1,000 words, we try to illustrate most of our description and statements by handmade photographs, schemes, space and aerial images, and 3D Google Earth views. Yeah, they're saying that picturing it's more important sometimes. You can one time to see than 7 times here. So they already mentioned that most of the studies describing those landslides in Central Asia are in Russian, considering the poor availability of many of them outside former Soviet Union. We tended to refer to summarizing Russian publication, as well as to primary source of information in which the phenomena is questioned were described for the first time. So some of them basically been described first time. Rock slides in Central Asia were investigated by the Chinese researchers too, often published in Chinese. But now I see there's a lot of papers coming out in English, good, very well-written papers. But still, it's not as much as actually research been done, or like country databases, which involve in all this landslide. These publications are inaccessible for us, and thus some data available on rock slides in the eastern Chinese part of the study region could be missed. You see, that's what they're saying. So they could do be some kind of government program to study all these landslides, mapping them, and be only Chinese and Chinese documentation. It's not even published anywhere. Most names given according to the Russian topographic maps could be local toponyms, especially for the Chinese part. And also like in Kyrgyz and Uzbekistan and Kazakhstan, they kind of have a local names as well. So usually Russians adopting the local names for that, but writing it in the Russian type of style. So Central Asian mountains located in 6 states: Afghanistan, say China, Kazakhstan, Kyrgyzstan, Tajikistan, and Uzbekistan. So they don't include the south, called Vakhan Corridor. Geologists, geomorphologists in these countries, including those that previously were parts of the Soviet Union, have their own traditions of landslide studies with somehow different approaches to landslide identification, classification, and mapping. So that's one of another problem to how you distinguish this landslide, rockfall, or rock avalanche. And there will be different peculiarities depending on your country or scientific system you work with. A little bit tricky, isn't it? Even if we looked on some like United States versus New Zealand / English kind of classification, will be different, and you have to always kind of, because when you publish paper, you publish it for global community, so we need to kind of find common grounds, in this sense. One of the aims of this book is to summarize data on the Jungaria, Tian Shan, and Pamir. That's what I show you. Where are they? Large bedrock landslides, to analyze these features through the entire region from the joint stance into characterize bedrock landslide distribution and regularities, regardless of the political boundaries. They have no relation to the geomorphologic, geological, and tectonic constraints. That's the truth. Like for geomorphological, for landslide, there's no boundaries. It's going to go through all the countries which are on the way. Same like in the Alps, here you have France, Switzerland, Germany, Austria, and Italy. And some landslides, they could be like in both countries. So they're talking about this monograph about the in Alpen studying the rock slides in Alpen region. What else? Emphasis will be paid on controversial issues such as distinguish between rock slide and a moraine blockage in selection of seismically triggered landslide. They're predetermine at a large extent both landslides and seismic hazard assessment and elaboration of technical and social measures aim to predict and to minimize, or if possible to prevent, related disaster. So that's main highlight through all this research. That's why I already say it's not just a pure interest of scientists. Oh, there's a landslide and being triggered by that or that. And people argue. It's very important. If it's seismically triggered, we need to understand we have this type of event, seismicity, what the chances, how statistically how far the landslide can happen, how big they are, all these things. Or maybe we can figure out that most of our landslide not even related to seismicity, so we shouldn't wait for big earthquake to be careful around those slopes. So we should stabilize them or whatever, remove people even before. Could be big rainfall, like we can see happens in New Zealand, for example. Yeah, other areas. There's many big heavy rainfall events happen, or in Nepal or in China as well. Those regions causing huge landslides, mobilization and catastrophe. So we're aiming for, I'll just check if I have any more questions. No? And just glance on I have 36 minutes. I will aiming for maybe hour, so we see. All right, so we didn't intend to carry out regular analysis of landslides, accessibility for the study regions, considering enormous variability of geological and geomorphic conditions. So you see the same. We're not kind of focusing on this book about the triggers, factors. What's more important, like what's more probably trigger things, or classify them, because it's too big area, two different slopes, different geology. And I was lucky to visit some of those landslides in Tian Shan, not in Jungaria, but Tian Shan, Pamir, and they're totally there's so big variety of differences of them, and many seismically driven. Although we're not sure, but there's all the evidence supporting this, and you actually kind of like a detective, you can figure out was it earthquake trigger landslide or not. So what else they say? We believe that our book will attract attention of landslide researchers interested in new impressive examples of large-scale catastrophic bedrock landslides. And that's like one of the idea, and then Sasha, also Alexandra Strom, used to run a lot of with Kanadbek kind of collaboration summer schools for years in international summer schools in Tian Shan. So they were inviting students, researchers, PhD students, lecturers from around the world, from all different countries, and showing them those landslides. We also believe that it would be interesting for hydraulic engineers, working in a dam projects, and that's very important for Tian Shan, Pamir, this area. Some of the work was a part of the building a dam. And since 90s, our study of this phenomena was supported by international research projects. So they put in all the attributions. You can have a look. The summer school that was run since 2006 in Kokomeran River Basin by Strone Abrahmatov. And there's a guidebook which kind of summarizing some of the important landslides that have been visited. And then they say thank you for anyone who take a part in it, help, and so on. So let's continue. We have some time. We can look next chapter. Part 1, general information. Let's start it on this. I don't think I will go very fast. So we just can go through the brief history of the landslide research. And next live stream, I'm kind of trying to go through topography, geology, and climate and stuff of the area. So next live stream, I don't know if I'm going to do it this week or next week. It's going to be more about just the settings for our study area, so you have idea. And it could be very interesting for you if you're not familiar much with that area, region. If you're just a geographist or traveler, you're just interested in this earth science and our planet. So let's have a look. Chapter 2, brief history of the bedrock landslide studies in Central Asia. So they mentioned that one of the global landslide hotspot in the world, this area, Central Asia. Indeed, numerous slopes failures occur here in soft sediments every year, causing significant losses and even casualties, death. Yeah, you can even go on the blog. There's a link. Have a look. These phenomena have been studied in details for many decades, but most of the investigations were focused on landslide in loess and other soft sediments that provide major hazard in the densely populated foothill areas of Fergana Valley rim and in the central and southern Tajikistan due to the almost annual occurrence. Yeah, I show you Tajikistan, central, southern, basically Pamir. These landslides constantly happen almost every year. First studies focused on large-scale bedrock landslides in Central Asia were performed by Russian researchers at the end of 19th, beginning of 20th century. Yeah, large earthquake happened there, and it's often the big earthquake happen, and it's kind of causing many landslides in the area, and obviously it kind of sparked the research. And back in 19th century, 1887, 7.1 magnitude Verni earthquake near the present-day Almaty city caused significant large-scale slope failures. It was mapped and studied in detail. Back in it was a Russian empire, as I understand, back in the day, and Geological Committee of Russia at that time kind of patronized it. It was the first professional description of such phenomena in Central Asia, the one that we knew. We should mention that 2 years before, in 1885, magnitude 7 Belovodsk earthquake affected the area just west of the present-day Bishkek city, the capital of Kyrgyzstan, today's capital, and about 200 kilometers west of the region affected by the Verni earthquake. This event was also accompanied by slope failures, but the reconnaissance team that investigated its effect paid attention on the structural damage mainly. Yes, I don't think they describe much information about the landslide. They didn't describe it. Same in gigantic Chilik earthquake in 8.3 magnitude. All these magnitudes unimaginable. This occurred in northeast of the Issyk-Kul Lake in 1889, 2 years after the Verni earthquake. And you will think, like people say these days, oh my god, the earthquakes are so common, so often happening. Look at the historical events. They have these 2 years of huge events happening, affecting all these areas. So when people say it's end of the world, we have too many earthquakes recently happening, I guess people at the end of the 19th century were thinking the same. One questionnaire filled by locals, local administration officers were collected and analyzed. So unfortunately, quite limited information about slope failures in the mountains during this earthquake is available. Yeah, so they did research, but it wasn't like, well, first of all, there was not many tools, I guess not many people, and we don't have all this remote stuff, so it wasn't as in detail and as today. 1907, two large earthquake affected the foothills of the Gisa range, west of the Tajikistan, Dushanbe city, and again, could be found some published reports. February 1911, largest historical non-volcanic Rockslide triggered, but the large earthquake originated in a very remote and hardly attained area of the central Pamir. That's the one that caused the Usoy landslide. Yeah. So magnitude was kind of reported differently, but we have this huge rock slide buried small Usoy village with all inhabitants except 3 men who went the day to the Zares village, about 20 kilometers upstream. So landslide was so large it was discussed initially if the slope failure was triggered by earthquake or the impact of sliding mass of the valley floor. An opposite slope was recorded worldwide as an earthquake. The people were thinking it's the earthquake triggered the landslide, or the landslide caused the earthquake. The Usoy rock slide dammed Morgap River, and that's what I show you in the beginning. Threat for the large part of the Amudarya River basin. It's all this big, basically, river that going through whole of the Uzbekistan and then into the former Aral Sea, which now drying out. It was studied soon after the disaster that attracted research attention till now, and attract researchers' attention till now. This extraordinary rock slide, one of the few worldwide North Central Asia case studies. Yeah, I guess they do talk about Usoi back in the next chapter. We're gonna see that. Impressive surface ruptures and seismically triggered landslides originated when the catastrophic 8.2 Cayman earthquake occurred in December 1911 in the northern part of the Tian Shan, north of Issyk-Kul Lake. You can see, same year, gigantic events, earthquakes and landslide in Central Asia. So that's why we have this book. That's why it's such important study site there. Earthquakes, slope instability, glaciers, different mountain ranges. That's all. Brief description of several earthquake-induced rock slides in the western part of Tian Shan in Uzbekistan occurred in the 19th century and survived in the memory of local communities is presented. There's a landslide catalog as well included, and they will talk about this later. So, and unfortunately, they say described by the locality name and the name of the river basin where it's occurred, not by coordinates. So that's why we need to continue this. If you go to this valley, there's so many and unidentified older, bigger landslide in the area. Several large, more than 8 magnitude earthquakes, likely being accompanied by rock slides, have occurred in the eastern Chinese part of the study region, as well as a Nilki earthquake. In 1812, the Kashgar earthquake in 1902, and the Manas earthquake in 1906. You see, this earthquake's just happening, popping all the time. Most papers describing these events in Chinese, well, limited data, so that's what we talked about. So the earthquake-induced landslide disasters at the end of 19th, beginning of 20th centuries, accompanied by numerous large-scale bedrock landslides, was followed by about 30 years long period when such strong earthquakes did not affect the Central Asia region. You see, it was very active for some reason in the end of the 19th century. So the absence of these big events slowed research activity, focused on this large-scale bedrock landslides. Then it started with 6.4 1941 GARM and magnitude 6 1943 Fazabad earthquake caused several landslides. Maybe because of during the war, the time wasn't so much focus on research there. 1946 7.5 earthquake in Kyrgyzstan resulting in numerous landslide rock slides. So yeah, in Taktagul dam site, yeah, Taktagul is a big reservoir as well in Kyrgyzstan. So in Case Valley inundation, the special measures were undertaken to prevent most catastrophic consequences. Unfortunately, no regular mapping of the environmental effect of this earthquake was performed immediately after this earthquake. Most of the data were obtained during field reconnaissance carried out in late 60s, 15 years or even more after the event, yeah, by Leonov E. Kuchai. There was another kite earthquake in Tajikistan, triggered 7-kilometer long avalanche, and 75 meters thick deposit buried the small kite town, several thousands of people. Yeah, so there's a more next impulse of study. Bedrock slides in Central Asia was provided by several landslide-related disasters associated with breach of landslide dammed lake that have occurred in Soviet part of Central Asia in the 60s. There was another 60 in 63 catastrophic breach of the rockslide dammed Issyk Lake east of Almaty. It was a capital of Kazakhstan at the time, caused a devastating debris flow that passed through the Issyk River valley, and still you can see the traces of it. That's what they say now, even 50 years after. So there's more examples they listing all around the area. So this one of the Issyk Rockslide Dam and the Issyk Lake after dam restoration. So that's a picture here. Actually, I should go Corsa, I think, so you can see better. Yeah, that's the dam. large alluvial fan entering the lake was formed by the 1963 debris flow that caused the dam's breach. Traces of the outburst are visible downstream from the blockage. The artificial dike was built afterwards in the eroded channel that you can see right now on the Google Earth. Now we're talking about a lot of outbursts caused by rockslide dam breach. You see another 166 happen in Insvar-Ramsey River basin in Kyrgyzstan. It was caused by the rockslide, was caused by the earthquake, likely. It's been reported before. And you see that they're saying that the event of breaching happened, could happen many years after you have this dam created. So any moment, for example, Saris Lake could go. Yeah. They're also describing another 20th century events. Let's have a look on the pictures. Remnant of the 1964 Ayni rockslide dam, just upstream of the Ayni town, Tajikistan, and downstream of the junction of Zerafshan River. Coming from the left, you can see the blue water here. So you see there's a deposit hitting and the river cutting through. And very often you can identify in the valley if there's a worse rock avalanche, not just by the scar, something on the slope, but very often unusually meandering river and a lot of kind of hummocky type of material. It could be something glacier, but very often it's the landslide. Let's have a look here as well. Breached Yashin-Kul Dam, not the large difference of the benchmark elevation upstream and downstream of the dam, resulting from the significant sedimentation of the presumably 300 years old lake. So the old lake formed by the damming, and then 300 years after it's burst out. Yeah. Just downstream of the dam, evidence of valley aggradation is still visible. Valley aggradation, so it's kind of building up of material. Maybe it's not as good. You probably should go to the Google Earth and have a look. Here they all provided coordinates and stuff, so you can find it easily. Most recent well-known disaster in the study region caused by large-scale bedrock landslides and river damming occurred in 1992-93 in the Belaldi River Valley, small right bank tributary of the Narin River that falls now in the Taktagul Reservoir. It's northern west of Kyrgyzstan. Large-scale slope failure occurred on August 19, 1992 in the upper reaches of this valley. Even these coordinates, you can go check it out, being triggered by the 7.3 Suz-Samir earthquake. It blocked rather steep by the wide glacial valley. So the rockslide buried the shepherd's family. They had tended a herd. This was because it's August. In August, everybody in the field with the herd, and dammed 2 minor streams, forming lakes up to 200-300 meters in size. Only. Nevertheless, 10 months later, in June 1993, likely after intensive snowmelt at elevations exceeding 3,000 meters above the sea, that's elevation where usually people go with the herds in the summer, these lakes burst out, producing powerful debris flow that partially devastated the village 70 kilometers and the Torkin village 30 kilometers downstream of the damming site. So you see, it might be like even village so far away, 30 kilometers, you might think, okay, it's not related. You can have this event that happened after 10 months later, 9 months later, or several years later, and flooded everything. So we have to study these things, yeah? And it should be the part of the government program in the areas like that. Yeah. 1992 rock slide at the upper reaches of the Belaldi River, source of the powerful debris flow. And the debris flow, it's not just the water or just the material, so it's kind of like this slushy, saturated material. They behave kind of like a river, but it's not. It's different viscosity. and it's very devastating. It's no mercy. Furthermore, we will skip at the elevation mark and will indicate altitude values only. Yeah. Let's have a look. Yeah, a little bit left. I can finish. We'll finish it now, and that'll be the end of the today part. Besides studying these historical rock slides and rock slide related disasters, regular study of the prehistoric large scale bedrock landslides was performed in some parts of the former Soviet Union Asian regions as well. And there's authors provided. These studies were stipulated by the above mentioned disasters in 60s, by anxiety of the Zarez Lake safety, and by the construction of several major hydraulic projects that had started in the Soviet part of the Central Asia in the same period. Yeah, and back in the day, like in Soviet times, because, well, obviously there was a borders, but not, it was all like one country. So they had these projects of hydraulic, so they had this, how to say, the connection of the rivers and dams coming through several stans, whatever, republics. And that time, you know, there was no idea that the Soviet Union would be collapsed, so it was all part of one. And now when the countries separated, put the borders, it's become a little problem for local communities, because you have one dam kind of serving several stans, several countries now. But there was a lot of research done, and you see, because of all, first of all, health and safety, because of all these events, and secondly, to, you know, infrastructure, start developing the area, help people build the dams, build the hydro station, and this kind of stuff, electricity and so on. So they've been reported, and you have to study prehistoric, historical landslide to understand slope stability. What are you going to do with the area? More than 50 rock slide named lakes have been identified here, but most of these data were presented in unpublished reports written in Russian. And yeah, and it's kind of like Russian Academy of Science. They had this tradition. They publish a lot of stuff, and it's all, of course, in Russian. I think they were publishing some annuals, like news kind of stuff, brief results in English. At least I know they did it in Geology, but I'm not sure about this type of research, if ever been published in English. Some of which are hardly to get now, even for Russian-speaking researchers. Yeah, so you still need to find them. What are they? There was no digital word exist back in the day. We must mention that during compilation of the 1.200 stage geological map of USSR that covers the entire country, in many cases coarse debris accumulation at the feet of the mountain ranges were mapped as moraines. One fact, there are bodies of long run out prehistoric rock avalanches, and it happened in New Zealand, everywhere. So they were mapping. When they were mapping, it's a big job, especially, you can imagine, to map Soviet Union. So I assume they didn't have opportunity to go on every site and research it, map it, deposits, identify plus there was not much research even done on those events back in the day. So I don't think they had like a lot of identification methods of, is it rock slide, or is it glacier material, or is it rock slide on top of the glacier material, all these things. So they're just mapping them as a moraines. And it was kind of more common back in the day, same in the European Alps and everywhere. The pioneer work in this field was performed by Kurdyukov, the first researcher who identified deposits of the extraordinary mobile prehistoric rock avalanches in the Alai Valley. And I talk about this when I talk about Common Sioux, Common Rock Avalanche a lot. It's the world's second event according to its travel distance, after the 43-kilometer long Cherilos Negros Tomasiri rock avalanche in Peru. That's the one that's devastating, which however much larger in volume. Yeah, so they suggested this big Achiktash River big rock avalanche, and in fact we went there and we did prove that it is the rock avalanche deposit. Watch my Ale Valley Hamaki Moraine video about that. Detailed studies of the bedrock landslides in the Zeravshan River Basin and the Narin River Valley near Taktagul Dam site in its vicinity were carried out by researchers from Moscow State University. So it was summarized in Fedorenko. And they say that you can find all the reference there. Numerous investigations were performed Soviet times in Zarez Lake, aimed to specify the Usoy blockage. And we'll talk about this later. And so they were assessing the risk of lake outburst. That's very, very, very scary and important. Tajik part of the region that include most of the Pamir and southern Tian Shan. The bedrock landslides were studied by Vinichenko, even in 2006. She identified numerous subtypes of large-scale bedrock slope failures. That almost each feature can be ascribed to a special subtype. So they're very, very different. Okay, what else? Recently, Shuk published a series of papers in which he argues that most of the natural blockages in Pamir and southern Tian Shan, including well-known features such as existing dam of Yashinkul, Shiva, Iskandarkul lakes, and the breached Kudara Passer blockage were formed by ant moraines. We disagree with such interpretation. This problem could be discussed in detail in chapter 4. That's another thing, yeah? So maybe traditionally, well, in some cases it is true that the glacier blocked the valley and you have proglacial lake formed as well. But in this situation, it's probably not the case. Many large-scale bedrock landslides were identified in the course of paleoseismological studies, being considered as effect of large prehistoric earthquakes. And that's one of the very important things, that also understanding seismicity of the area. So if you want to know how your mountain's active, so we know, for example, right now, I don't know. Well, for example, Southern Alps. Yeah, I can speak from my heart for Southern Alps. They're very active. We know for last 20 million years these mountains were building. But you also want to know how, like, is it in the last million years, is it become more frequent earthquakes, bigger or less? Is the rate of uplifting slow down or continue or speeding up? All these things will tell you have to go and study deposits that can tell you that there was an earthquake. For example, your landslide caused by the earthquake, you can map it. Excuse me, because it's the important part of the, like your database. So if you discarded all the earthquakes, which you can only identify by landslides, so it's what they call paleoseismicity studies, reconstruction, you can have a chunk of the earthquake which you didn't report it. Or opposite, if you only focusing on earthquakes, but you didn't count it how many landslide they caused in the past, but only on the modern cases, because we do know they happen because we observe it. You will have like last couple hundred years we have so many big landslides, they're happening, but nothing happened 500 years ago, yeah, or 1,000 years ago. It doesn't mean that didn't happen just because you didn't find deposits or you didn't identify the deposits. And what it tells you, it tells you about the evolution of the landscape. Yeah, is that we're going to have more people suggesting, there's much more slope failures, landslides right now because of climate change. It's all because of climate change. No, maybe seismicity change in the region, yeah, or maybe you didn't have database for the past. Is good. So there's a lot of questions, yeah. However, the problem with the correct and well-grounded discrimination of seismically triggered and non-seismic rock slides, so the one that caused by earthquake and not, is far from final solution. Yeah. We'll talk about the separate chapter. Special investigation of highly mobile rock avalanches and the motion mechanism were performed Soviet Union 70s, 90s. Predict shape in artificial rock avalanches that were proposed for the blast field dam construction. Yes, they were doing this research as well, like if you artificially produce a dam or blow up something, slope, what's going to happen. And I know in Norway, for example, they did a lot of detonation of the slopes because they have a lot of tunnels in Norway. If you ever go in Fjordland in Norway, you're just driving through tunnel after tunnel after tunnel. I think it's a lot of the most tunnels country in the world, probably. And they did a lot of because where you put your detonation, what the forces, exposure, all these things, and then you creating this landslide basically artificially. So it's another kind of like experimental part of the research, which aid into understanding of our landscape evolution. This technology was considered an alternative to the conventional technologies of high dam construction in narrow river valleys. Blast field dam construction. Studies included not only field geological reconnaissance, but also extensive laboratory numerical and physical modeling. That's another thing that, aiding to your research. That's what I already kind of alert you. Even observation during the after large-scale underground nuclear and chemical explosions. Yeah, I don't know about modern days, but back in the day it was kind of things that people did. Several dams were created in the Soviet part of the Central Asia by using these technologies. Most of them by the directed blasting, while the proposed 270-meter Kambarata 1 dam had to be created by artificial rock avalanche. Yeah, and then after collapse of USSR, this project was stopped, of course, for obvious reason. All right, let's just shoot through till the end. We have some time. In the last year, I'm looking for if anybody had any questions. No. In the last year, several rock slides and rock avalanches in Chon-Kemen River Valley and in the valleys dissecting the northern slope of the Kyrgyz range were studied during preparation of the field trip of the NATO Advanced Research Workshop. It was held in 2004 in Bishkek. Numerous prehistoric bedrock landslides of various types were identified and described in Kokomeran Basin and some of other parts of the Kyrgyz Tianshan. And that's when Alexander Stone started his kind of flow into this summer school of studying landslides. So they identify a lot of older landslides, which not necessarily they identify the glacier deposits, specifically not in Tianshan, but just they were just unknown. They're also big, large, and unless you do good mapping and look through the deposits, lithology, grain size, dating, I don't think it's quite tricky to identify them. These data allowed elaboration of rock avalanche classification. They will be widely used hereafter. Yeah, so kind of telling you that they use this specific type of classification, because I told you, like, for every area around the world, and also depends on what you're looking at, classification could be so different. And it could be quite confusing because that's kind of my brick wall, which I always hit, is why there's so many terminology and they're so slightly different. And it also depends which country you're in, which valley you're in, and so on. Regional analysis of the landslide-related hazards of the former Soviet part of the Tianshan and of some of the local regions, Kyrgyzstan mainly, was performed recently. Yeah, so there's a more recent research done, and I know some people who did this. 2014, the landslide hazard map of the territory of Tajikistan was conducted with the support of the UNDP Disaster Risk Management Program. So there's some things happened right now, recently. Similar studies were carried out in the Chinese part of the study region as well. Several papers present interesting data on the ages of prehistoric rock slides in the study region. We have to know that some recent papers provide quite unrealistic assumptions of the rock slide related hazard. An example, we should mention the possible 1 cubic kilometer failure of the Tectogul reservoir. No evidence of so voluminous present or past slope deformation on the reservoir bank is available to propose such a catastrophic scenario. So it could be also another thing that people over proposing. No doubt that we are just in the starting point of the comprehensive study of Central Asia bedrock rock slides and related phenomena. Much more effort are needed to solve numerous controversial problems of the nature of these features and triggering phenomena such as large earthquakes or climate change that can destabilize high rocky slopes. Some conclusions on the origin of the prehistoric rock slides in the study region are prevented at a large extent by lack of their ages. Yeah, that's a very big problem, specifically in that area, because of when there was all this done research back in the day, we didn't have such availability of the dating methods, specifically cosmogenics. And now we do have it, and it's a little bit more available. But even since I've been involved in the last 10-15 years, it's kind of slowing down again. So people did a lot of cosmogenics, and now it's kind of becoming more expensive or less qualified stuff. And it's not just, you might have funding, you might have samples collected, everything, but you might wait for years, so the specific laboratory will have stuff available for you to analyze it. And often, like, unless you go in and do it yourself, you know, it's you can wait years and years. I was helping somebody to actually preparing something. There was nobody to like actually prepare, which can take took me a couple months to do, like I think it was like 20 samples. So it's quite severe work, you know, to do. That's why those labs, they have like years of queues, you know, if you have some samples. It seems to be the most critical gap in our knowledge and should be considered as one of the main target of future research projects. Limited data on the ages of several features that are available at the present will be presented hereafter, along with the morphological description of selected studies. Authors have that inevitably brief description of the impressive bedrock landslides from the study region presented will attract attention of the next generation of landslide researchers whose studies will shed new light on the problems that we could just mark out. And that's what all the point and hopes of the authors. It's to attract new research. And then I found people kind of become very focusing maybe on some specific or some particular study sites. And recently they've become very big interest in actual methods, but nothing as such a ground understanding as a concepts, you know, behind. So we're very specific about something, how to map it, sophisticated methods to map something very regional or one case, but there's no much researchers, especially I didn't find, I don't know, among younger ones, who kind of categorize it and make it more like a big catalog and aiding to bigger picture with what's happening with the landslides, with the valleys, how important the seismicity, what the input, and this kind of stuff. So me and all the researchers who does this, we calling and encouraging younger researchers to get interested in this kind of stuff. So although it seems like there's so much studies done, but there's so much work to be done to catalog it, classify kind of classifications, to create database and understand what's actually the gaps, what we know, what we don't know. And it's very, it could be kind of boring type of work, or very long, you know, like you have to go and collect a lot of data, or creating tables, mapping stuff. But it's a very important part of the research. It's always been. So I hope you like this type of videos. I'll publish this, maybe I will divide it in a couple and publish it as a videos, and I will try to prepare for next live stream, maybe this week, maybe next. And please write me what do you think about that, and are you interested in this topic at all? And I will see you in my next videos. Hi everyone and welcome, and we're starting our live stream, and I'll just check that I have my sound, and the stream is running. Okay, I need to check the sound. Oh yeah, sounds like it's all good. And please, if you have any problems, just let me know in the chat. I'll try to keep an eye on it. Welcome to my live stream, and you can see from this picture that's me back in the day on one of the landslides in the beautiful, beautiful Kyrgyzstan country in Tanshan. So we continue our beautiful journey through the book. And today second part will be more kind of more general geographic. As I can say, we will look briefly on geography, geology of the study site. Central Asia, and it's a little bit very broad area, so from previous video you figure out that it's Central Asia. We covered many countries, many mountain ranges, different geology, so we're going to go very briefly through so you can have some kind of idea, understanding, and general picture of the area. And we're just going to go through our table of content again. So while we're doing this, what is it? It's everything in the first part of this video, first 2 parts or the live stream. We are on a part 3 overview of the study area, region, and we're going to talk a little bit about geographical position, where we are, geology, tectonics, neotectonics, geomorphology, what's happening right now, what type of landscape you can find there, seismicity, a very active area you already figured out from previous video, and we'll continue talking about this. And then what in terms of the record we have there, what's happening right now, and final will be climate, glaciation, and hydrology. So it's a very important part of this book, because if you're thinking about big landslide slips, first of all, we study them while we looking at this planning, hydrology, getting energy from the land or redirected something. And then if you have big slopes, landslides collapsing, obviously will be affected. And with the climate change, deglaciation that's happening right now in this area intensively, fast, I mean, you will look at these, problems. So it's very correlated, and it's affect one another. Yeah. So the deglaciation, change of the climate, or hydrology, for example, rivers become less strong because of the glaciers melting away, or opposite, we have too many precipitation in some areas. So it's all affecting the slope stabilities, and as a result, if there's something happen or big earthquake, what role it play in further effect on the area. All right, so let's be very ambitious in trying to go through. So I did prepare some sites on my Google Earth, so I'm going to switch sometime to my Google Earth and show you where we are. But just in general, that's the picture that's provided by the authors in the book. I don't know if I need to zoom a little bit more. I'm trying to go 180. That's better. So please, if you have any questions on the way, just because I'm here, you can ask me and I can answer. Because I'm not so much have time to answer for all comments. I'll try my best. So let's see. The Tanshan is one of the biggest range you can see here. They're going through. Mostly it's Kyrgyzstan. It's a little bit touching also the China. Jungaria, it's here, and we have this range here, and there'll be some research done and description in that area. And of course the Pamir. Pamir, it's this curve you see, like a little, they're called horseshoe mountain range here. It's basically all the Pamir. And we're more interested in the northern part, which we're going to talk about this a little bit, about the landslides there, and that's what I have my Achiktash video about hammock moraines talk here. You can have a look at my previous videos. Yeah, so that's more bigger picture. So where we are located on the big map. So I switch for my Google Earth, and I'll show you. So obviously I'm located in New Zealand, Australia. So we kind of go towards Eurasia, and you see here we have our Industan Peninsula crushing into the Asia and kind of Siberia. So there's a very complex area here. And a part of the Pamir, so it's kind of this northern western part of the this all big range, which Nepal and Kathmandu is obviously connected, the highest mountains in the world right now today. But this Pamir and crushing into the Asian part, and Tarim Basin is sitting here. So you creating this like two big waves, so Tanshan and basically Kathmandu, the Nepal mountains. Tibet is going through here, Tibetan plateau. But some geologists actually saying this all part of the alpine mountain range going through here. It's kind of curving through Caspian, shooting through Caspian Sea. Caucasus part of it is, and then you go through the Black Sea, Turkey, and you're going towards the Alp range. So it's one of the big system, and that's how I think I remember been studying back at university in my years. And we're going to look at this area. So Pamirs, we're going to talk about geography, geology here. Tian Shan is basically this range, and Jungar, a little bit part of it. And there's a lot of mountain ranges, and they're about 3, 4, 5,000 meters high. And then you're going towards Pamir, which is directly connected to Tibet, and it's up to 7.5 kilometers peaks we're talking about here. All right, so let's see what we have in the book, and I'll come back to that geographical position. So I just need to a little bit switch, and I'm back. So when we go to the chapter, we talked about brief history, so we're just going to go to the chapter. Sorry, maybe it's not very comfortable for your eyes, but I need to switch. Overview of the study region. Outline, so we're going to talk about topography, boundaries, where we are, geology, tectonics, neotectonics, geomorphology, seismicity, earthquakes, high active area, climate, glaciers, hydrology. First, we want to study region, topography, boundaries. Central Asian region includes, and here we're talking about geographical, Central Asia study site rather than anything politic, geopolitic, and so on. Yeah. So Central Asia includes 3 mountain systems: Jungaria in the north, Tian Shan I showed you, and Pamir in the south. Jungarian mountain system stretch for about 350 kilometers from the west to east, Kazakhstan mainly. And its southern parts, it's in Xinjiang province of China. I hope I pronounced correctly. I swear I was practicing before with a Google how to pronounce it. Maximum width of the system mountain ranges is about 110 kilometers. At highest summit is 4,622 meters sea level, Semyonov-Tianshansky Peak. While from the westward and northward to Jungarian mountains, height declines gradually towards the Balkhash Plain. Balkhash Plain and Balkhash Lake are one of the biggest lakes of Eurasia. From the east, it is cut sharply by the northwest trending escarpment associated with the Jungarian Fault, dividing it from the depression with the several lakes, and largest of which is the Alakol Lake. So from the south, Jungarian Range is bounded by Ili Intermountain Depression, I'll show you on the map, and Xinjiang east of the meridionally trending part of the China. Kazakh border. So it's kind of on the border between Kazakhstan and China, southern chain of the Jungarian Mountains named Borokoro Range, and stretch from east-southeastern direction, merging its eastern terminus with the Iran Kaburga Range. And it's the northern mountain chain of the Tian Shan. So they're kind of like Tian Shan flowing into Jungarian. Tian Shan is the largest mountain system. So let's have a look. I just have this map, general map of the area, and hope you can see. I'll go a little bit zoom out. And we have here, basically, here they're indicated with a red, the Kyrgyzstan. Tian Shan, it's the realm of the Kyrgyzstan mostly, and even here. And then Alay Range, I talked about in my previous video, we have Zalai Valley, bounding, dividing Pamir. So it's like a sharp border. Yeah. So when you're in this valley, you're looking on one side, it's Tian Shan, and other side south, you're looking on a Pamir. And then this is all Tian Shan here, Osh Valley here, the big Fergana Valley, they call it, with the Osh located on the Kyrgyzstan territory, and it's mostly Uzbekistan, the rest of it, lowlands. Well, not that low, but lowlands in comparison. And then we have a big system of Tian Shan. And this lake, it's one of the biggest mountain enclosed lake, called Isekul, which is translated the pearl or the gem of the, I think the pearl, correct translation. And it's amazing. And as well, it looks like a sea, basically. They even call it sea there, local people. But it is the lake, and it's also bounded by Tian Shan. And then Other picture, yeah, that's the Isekul shore. People, it's the main destination for locals because going to the ocean or the sea, it's quite far for these people. So the Isekul, it's the local sea for them. And that's the bigger picture. Hope you can see. So we have this Tibetan plateau, Taklamakan, the biggest desert here, China realm, and then we have Tian Shan going through China, Kyrgyzstan towards Uzbekistan. Pamir to the south, that's everything I show you. Isekul here, and the Balkhash, it's this big lake which is already in the Kazakhstan. So Jungarian range. I need to show you so I don't lie. What is it? We'll look on the map. I'm probably just gonna go to the Google because it'll be easier for me. So if we're going to the Google, let's zoom in. Again, Isekul, Tian Shan, Almaty, and that will be this Jungarian range basically here, yeah. And that's kind of getting into the plains of the Balkhash, big lake, Balkhash Lake. And that's the lake which was stated. And here the Ili Valley, the already part of the China. So let's now return to the Tian Shan. And I think most of the landslide which going to be probably mentioned in this book will be from Tian Shan part. So I'm just marking around between my program. From the west, the Tian Shan is a stretch east-western direction about 2,500 kilometers, can you imagine, being up to 300 kilometers wide and has very wide defined natural boundaries. From the west and northwest, Tian Shan is bounded by the plains occupied by the Karakum, Kızılkum, Myunkum deserts. Further to the east by the Ili Intermountain Depression, dividing the Tian Shan from the Jungarian mountain system. That's what I show. Eastern Tian Shan is bounded by the plains of northern Xinjiang, extending towards the Altai Mountains and occupied by the Gurban Tungut Desert. So you see all these mountain ranges, the kind of in between, they have this, because of climate, we'll talk about this, they have a lot of deserts around that area. Very deep continental. It's one of the most remote areas from the ocean or the sea on our planet you can get into. From the south, the Tian Shan is bounded in the west by the so-called Tajik Depression, variegation of mountain chains up to 2.3 meters high between the southwestern Tian Shan and Pamir. In the central part, its southern boundary passes along the Kızıl, Surhop, Apa, Vakhsh rivers, dividing southern Tian Shan from northern Pamir. And Ala range, yeah, that's what I told you, or they're called Zalai and Ale Valley. The most prominent geomorphic feature of this boundary zone is the Ale Valley, 130 kilometer long and up to 25 kilometer wide intermountain near Tectonic depression. Please refer again to my video. I very detailed show pictures, our study sites, our campsites, and I show you cool stuff from that. Further to the east in China, the Tian Shan is bounded from the south by the Tarim Depression occupied by the Taklamakan Desert. Most of the Tian Shan reaches up to 4.5 kilometer high, and they rise up to more than 6-7 meters of sea level in the central part of this mountain system close to the China-Kyrgyz border. So we're talking about Victory Peak, 7,439 meters. Kantagri Peak as well, almost 7,000. So let's just go through text. Tian Shan can be divided conventionally into eastern highest, northern central, northwest, southern part, for simplification because it's quite big. Pamir is the plexus of the Karakoram, like a main nervous system. Kunlun and Hindu Kush mountain system. Pamir, the most elevated mountain system of the entire Central Asia. Highest summits, Kongur Peak, Mustagata Peak, so they're all 7.7, 7.5 sea level. meters in the China part, and Ismail Samoni Peak, known as in the past communism peak of communism, almost 7.5 meters sea level. Peak Krasnevetsskaya Peak, that's not far from Alai, 7.1 kilometers, 5 meters, are the central Pamir in Tajikistan. And the Lenin Peak name in Tajikistan is the Ibn Sina Peak, 7,134 meters. It's crowned the Trans-Alai Range at the Kyrgyz-Tajik border. And actually border, they do draw the border on the highest points of this whole range. And kind of within a couple kilometers north-south of that, it's kind of like a border. So if you want to go there like an alpinist or tourist or whatever, you have to have permission from the border control to get there. So just warn you, because they do go. They find the camps, wherever you are, you can hide in somewhere, they will find you, because they ask locals if there's any tourists or climbers or trekkers. And they will ask you to provide documents that you're allowed to be there, because it is the border zone. And sometimes there could be like conflicts between Kyrgyzstan and Uzbekistan or something. Well, they're just gonna go, and they have armor with them, so just be very aware of that, and get all the documents, all the permissions, all the posts you have to pass to, declare that you come there. Do that before you go there. Boundaries of the Pamir are well defined from the north by the above mentioned Kizilsu, Surkhop, Apavakhsh river system, from the east, where it's bounded by the Tarim depression, from the west, where the Pamir composed of the predominantly Paleozoic and Precambrian rocks, bounded by the Tajik depression, composed of folded Mesocenozoic sediment. You can see that kind of high peaks, older material, and more younger stuff in depression sediments that preserved. However, cannot be delimited geomorphologically with the same confidence from the south, southwest, and southeast. Here we consider the conditional boundary that partially follows the water divide between the Pinj River Basin and the Kokcha River Basin in the west, and Kambul River Basin in the southwest, and the Hunza River Basin in the south. We also included the area in the upper reaches of the Kochka River Basin in Afghanistan, where large-scale rock slides are widespread. In the Pamir, there's, oh my god, so many landslides. And as I told you before, these blocked river valleys, which caused lakes formation, potential for outburst flow, all this stuff. It's very dramatic landscape. In the eastern Chinese Pamir, this conditional boundary follows the 37 north latitude, approximately. That corresponds to the transition from the southeastern Pamir to the east-west, trending western Kundun Mountains. So let's just come back. And I did map some peaks on my Google Earth. So if we I'll go to my history, and I'm going to indicate those ridges. So they should be visible now. Yeah, so we have, let's just zoom out. So we have our Tibetan Plateau, we have Taklamakan Desert, this Kuluni and other deserts to the west, which is going towards the former RLC. I hope you can see. I don't know if you can see my marker. Oh, you do. You see my marker. So the RLC was all this, and I have a video about it in the beginning of the last year. I made a video about Google Earth, so I'll cut it out and put it separate about the RLC history video. It's a very amazing area. So this all used to be sea kind of borders, all used to be the seawall. It's basically lake, but we call it traditionally Aral, Aralskaya More, RLC, because it's so big. And it's been drowned in 60s, 70s, mostly in 70s, 80s. It's just there was less water supply from Sirdarya and Amudarya, two main rivers. One of the, they're both going from Pamir basically. One river here, you see, one second here. And they, in Soviet times, it was very much used for growing cotton and other stuff, vegetables. So they irrigated these rivers a lot. And because it was such a hot area, deserts here, you can imagine, evaporation's high all year round, and less water started being supplied to the sea. It was already very salty, kind of close sea, and it's eventually started drying out. But apart from the people, another problem is that the glaciers that feed in those rivers, for example, starts from the river starts from the Ala range here, the one we talk about. So there's a Pamir down south. This is all Tian Shan. So the glaciers here just dramatically disappearing. So I don't know, maybe it won't be so dramatic, but it still will the sea eventually like doomed to dry out because less water supply, because less glaciers here now. Plus, you see how this is all green stuff. This is all people irrigation, people using the water on the way. Of course, it's play a role, but I kind of question, how dramatic, how fast. That's just the question of the time here now. It's another little problem about climate change, glaciers disappearing because of the water supply to the areas. So the peaks, we have the peaks, peak Krzhevetsky here, peak Communism, kind of northern Pamir, highest points, as you see, 7.5. I show you before the peak Lenin. So here the border with the China. Where is the border with China? Here. And we have peak Lenin. Here, Oktyabrski on the other side. So that's the Lenin Glacier and the main base camp when people climb. The high peaks, even though are more towards the China, this Mutstagata, Kangur, Takh, and Takshkurgan. This is this depression valley in between, the highest peaks. And then we're going to the realm of Tibet, Nepal. Tian Shan. So I put you here the mark of Genghis Chokushusu, this peak here. It will be on the China land territory. And you can see the glacier is already from the space. It's a huge glacier. Obviously, they're located in the areas of the highest peaks. And then we don't have so much glaciers preserved left in Tian Shan, mostly rock glaciers. Here run Isikul and the main Tian Shan. Bishkek is located here, so it's the border with Kazakhstan, and just give you geographical location. And Almaty, very south of Kazakhstan, it used to be a capital. As I understand now, it's Astana, which located more north, And I think it's probably geographically, where's Astana? Here. Geographically kind of more logical position for the capital, for the country, but I don't know, I don't live in Kazakhstan. They found it's more convenient. And so we have Drungaria here, the Balkhash Lake, and you see it's kind of like, as well, the water supply probably is getting less for the Balkhash. Maybe in the future there will be, see the colors changing, could be similar like a Aral Lake. It's a cool, very deep lake, and here we have these two lakes, Karakol and smaller Rankul, two lakes, and you see they as well, they have numerous actually landslides, travel passes, all the moraines, fans filling up them, and these lakes probably doomed to diminish the water, so dry out, So that's our settings, and you can see we're in the very it's called Central Asia, in the very central of this continent land masses crashing together. So we have Hindustan coming from here, Asian, Siberia here, Eurasian continent, and Europe, and Africa is pushing towards Europe. A lot of surrounded by the mountain ranges or large valleys before, so there's very, very hard for big water masses, air masses to get into that area. I'll just talk about this now when we will back to climate. So what else? Pamir, geographically Pamir can be divided into three parts: western, central, eastern. Western embrace high ranges divided by deep valleys of the giant river. I think we already no, didn't read it. Main tributaries Vakh, Yagzgulem, Partak, Gunt, Sakhtara, and several smaller rivers. The valley up to 2.5 kilometer deep, with extremely steep walls incised by the glaciers and river erosion. And they getting steeper now because of deglaciation, all this stuff. This part of the Pamir, often named as Badakhshan, belonged to Afghanistan and Tajikistan. Central Pamir, 74.5 east approximately, they belong to Tajikistan, can be classified as the high altitude Tibet-like plateau with valleys 3.5, 4.5 meter sea level, ranges rising up to 5 kilometers. Most of the river's valley are much wider and much gentler than in the west. Some of them inherit shallow near tectonic depressions, and their deepest part are filled by the Karakul and Rankul drainless lake. That's what I show you. Eastern Chinese Pamir differs from both its western and central parts. Its ranges rising for more than 5 kilometers on average above the adjacent Tarim block, and are crowned by the summits exceeding 7.5 meters sea level. Divided from the plateau like Central Pamir by deep Sarikol and Takurgan intermountain depressions. And I show you 80 kilometer long and 15 kilometer wide boundaries by active faults. So they are later especially pronounced along eastern boundaries of these depressions. Such topographic peculiarities make Eastern Pamir similar to some parts of Tian Shan with its well-pronounced intermountain neotectonic depressions. And in general, rugged topography with higher ranges bounded by kilometer-deep tectonic depressions and erosional river valleys with steep slope typically of most of the study region. Yeah, large-scale landslides are prone there. That's basically what I want to say about that area. And you see this Pamir area. We have Kunlun Shan towards the south, Karakorum towards the south, towards the India, Nepal. Yeah, so basically Pamir is this last peak slope between more lower lands to the west and high Tibetan plateau. Here, crushing in Tian Shan is this kind of ridge built from crushing of all of that complicated Hindustan Tarim basin into the Asia. And as it says, it's continuous, and Altai mountains in Siberia already will be this continuation of all this curve and waves that build from this crushing. Geology. Geology of Central Asia has been studied for more than a century. You can imagine it's basically from previous video you figure out it started like towards late 19th century when the Russian Empire was patronizing all these areas. They started doing a lot of research studies, especially related to the big earthquakes. So they're trying to figure out, activity of the area, how it's active, how prone, what to do with in terms of people safety. And then already in 20th century, when Soviet Union kind of took over, geological mapping started, and we have a lot of very good, very detailed geological maps. Kyrgyzstan, Tajikistan, Uzbekistan, Kazakhstan were mapped regularly. And more general geological maps are available for all this territory. Even smaller scale, 250 maps are available for large part of the Chinese Pamir Tian Shan. China have it. You can access it online. And yeah, I can tell you that it's pretty. I did use actually for my research as well the Soviet geological map because couldn't find anything else, of course. They're very good. And the geology in Soviet times was very like fundamental basics. So you will trust it. There could be something like more quaternary stuff, recent stuff, a little bit more misinterpreted, or because there was not enough people, not so much like, we didn't have satellite amazing images of high resolution, you can help support your mapping. So obviously there will be like or generalization, for example, it's all more quaternary sediment, but which one, you go figure out. Or because big area and you cannot send people everywhere. And identify rocks and stuff and faults. So, but in general, it's pretty good. So people use it as a basic. basic geological maps. What else? So Jungaria, Tian Shan, Pamir composed of rock of different types: igneous, sedimentary, metamorphic, and the ages vary from Precambrian, basically very old ones, to late Cenozoic. And let's just tell you in general that mountain range is composed of Paleozoic, sedimentary and volcanic rocks, partially metamorphosized and intruded by Caledonian and Variscan granites and igneous rock of other type. So Caledonian, Variscan, it's kind of more the geological times when new mountains, new active area, new origin was happening. Mesozoic sediments are widely developed in Tajik Depression, in Fergana Range, east of the same name Intermountain Depression, so east of the Fergana Valley, and the central and southeastern and eastern Chinese Pamir, and in the now southern northern foothills of the eastern Tian Shan. Cenozoic and more recent sediments form inner parts of intermountain tectonic depression and the foothills areas. So you can see, like, you find similar material, but it's a very jigsaw mixed in different places, coming out in different parts differently, because all these areas have been squeezed and washed many times. So it's been general geology layers been mixed up many times, it overturned, a lot of faulting going through and kind of crushing and crumbling these older rocks and the newer rocks you can find on top. So geologically it's quite complicated, as you would expect it, but at the same time, you go there and you can find kind of similar patterns. Lithology of the region varies in a very wide range. Slope affected by gravitational processes are composed of almost all types of rock: sedimentary, terrigenous and carbonate, igneous, granites mainly. Yeah, that's what I saw, a lot of Tian Shan, a lot of granites. Metamorphic, nice, phylites, we saw a lot in the alley as well. Different ages. Information about rock types and ages affected by rock slides will be provided in appendix. Yeah, so, and also, like, whatever valley you go, you study site, there will be more specific information about your geology. Northern parts of the study region, Jungaria and northern chains of Tian Shan, were formed during Caledonian stage, while most of the Tian Shan south, so-called Nikolaev line, was formed during the Variscan stage. So this is the origins formation. Caledonian, when the Alps forming. Pamir is often classified as a part of the Alpine belt, that's what I say, and form the horseshoe shape system of northward convex belts. And you can see it on this geological map. I tried to zoom in, but there's no resolution, unfortunately. So that's our Isikul, Tian Shan. You see big geological kind of fault going through here. Jungaria will be here, Ili Valley is that one, Taklamaklan, and Yopamir, with all the cores, I understand. Pamir is often classified as part of, we read it. From the North Central Asian mountain system is bounded by the Epi-Paleozoic Kazakh platform, and from the southeast by the Tarim platform. Block located south of the eastern Tian Shan and east of the Pamir is occupied by Taklamakan desert. Taklamakan, so you have Kazakh plate, and here towards Aral Sea. Despite the significance of these Alpine stages, Caledonian and Variscan Alpine, main tectonic deformation itself does not play an important role in slope stability assessment as compared to the lithology in local geological structure. Pre-Mesozoic basement is most parts of study region have been subjected to intensive folding, thrusting, that's what I say, and reworking by intrusions and regional contact dynamic metamorphism. So it's so overcomplicated since you cannot see such a different distinguished dependencies of slope stability in your geological ages. Formation time. Paleozoic thrusting and formation of neps was especially intensive in the southern and central Tian Shan and in the central part of Pamir. You can check out the authors. Structure pattern of the areas composed of Mesozoic and Cenozoic, more recent sedimentary rock, and characterized by intensive folding and thrusting too. And strike-slip faults are widely developed in the study region as well. So I want to show you, like, for those who are not so much familiar. So strikes, slip faults, they look like that. So we can go different directions, of course. And anticlines, that's kind of like very characteristical geological feature of the area. So you have the valley, mountain ranges, you have this older rock in the middle of your anticline, and syncline, it's opposite. So the older rocks will be outside and younger inside. It depends how it's been folded. So you have originally layers obviously deposited horizontally. Older stuff at the bottom, younger stuff at the top. That's how your stratigraphy, I have a video about this, main stratigraphy works. And then you have this crushing plates, mountain building, and squeezing all the time, so that it starts overturning material. Yeah, and sometimes you can even overturn it and bring younger stuff in the bottom and older stuff on the top, and so on. Yeah, so think about this when you think about geology. It's actually not very hard if you can imagine in your mind. Many people give you your idea of the blanket when you have a nicely spread blanket over your couch. It's all layered, but then you start pushing it and you're creating these folds. Extraordinary variability of the geological structures, along with good state of the knowledge all over the Central Asia region, makes it impossible to describe structural pattern of the study area. Here, the regional basis, even in brief. So that's what they're saying. It's so complex. Just go in every area and have a look. Interested reader could find this information in special literature. In those cases when the bedrock structure plays an important role in the formation of particular rock slides, and such data are available, we will present them describing particular case studies. Yeah, so that's what they say in case studies. Next, near tectonics and geomorphology. I'll see how I do aim to finish it. So we have another half an hour, so I'm going to try to go through all the parts. Ambitious of me. And please write me your questions in the chat. Near tectonics, it's basically recent events, and geomorphology. Geomorphology, it's what you see on the surface, yeah, shapes with the land took, and of course it will be something more recent event, yeah, as much as the recent that earthquake last week, or the valley. It's something happened in the last several thousand years or millennia, millions of years. And you can even have geomorphological features which just created in the last night after the big heavy rainfall. So geomorphology is something more recent. Yeah. The latest near tectonic stages of the study region evolution plays the most important role in slope process, predetermine their distribution and magnitude. So the saying, so these recent events, as I say, like rainfall, heavy rainfall recently, or because you have here the fault area and you have this slope a little bit kind of hanging over the older one, and it will be more prone to collapse. New tectonic processes formed the modern tectonic structure and governed the seismicity, which is one of the main, probably the most important trigger of large slope failures in Central Asia region with arid climate. This stage is extremely well pronounced in the Tian Shan, where the new tectonic concept itself was introduced first in 1948 by Schultz. So, description of new tectonic structures of the former Soviet part of the Tian Shan were presented by other teachers, Makarov, Shedia. And let's give you that more information about recent various particularities of Tian Shan new tectonics and modern geodynamics being analyzed in more recent literature since 90s. Now we're getting into a section with a lot of pictures. So here you can see complex boundary between Jumgal Range and the Jumgal Inter-Mountain Depression. Main fault is marked by the red arrow. You can see the fault going through. And each basement massif marked by PZ, an individual basement anticline that was overlaid by neogene sediment N. Yeah, so it's younger material, older. Folded conformably with the planation surface formed on the Paleozoic basement. Quaternary sediments, that's more recent stuff, overlay neogene with angular discontinuity. So this quaternary stuff kind of preserve in the pockets, and in some places, you know, where the older stuff keep lifting, it will be washed off, demolished first, and then it will stay in this kind of lower pockets, or maybe because there's no outflow of the river or something, it will be preserved. Yeah. So you can see this zoomed in area. You can see this big, nice fold. Similar here. So it's going to give you like this idea of this amazing and complex, looking like a complex, but not so much a geology. Let's have a look at the text. The main peculiarities of Jungaria in the tension and tectonics and modern structure is the presence of large-scale basement folds. Particularly each range is near tectonic anticline. And that's the one that I show you. So the older stuff in the middle, younger on top. And you can see this is all younger layers, so there'll be this quaternary stuff kind of preserved in the middle here. And if there's no big of a river or the glacier that's washing material away, it will be there, will be preserved. Yeah, that's how I understand. But I can tell you I'm not a structural geologist, so there will be somebody who will tell me that I'm not right, of course. Usually these folds are asymmetric, with one lip connecting the adjustment anticline and syncline, while on the other side anticlines are thrusted over the syncline, sometimes with very complex system of the reverse folds and minor relatively sharp basement folds. They give you like peculiarities of the angles of these anticlines. Similar combination of near tectonically uplifted ranges and intramountain tectonic depressions divided by fault zone is typical of eastern Pamir Chinese area, while the central and western parts of this mountain system reflect more uniform plateau-like block uplifted during near tectonic period and dissected in its western part by kilometer-deep river valleys formed by glaciation and water erosion. See how I told you like the more recent stuff, glaciers, rivers, forming and shaping the valleys. The entire region is crossed by numerous tectonic faults, many of which are long-living, inherited from the Paleozoic stages of the tectonic evolution. However, faults originated during near tectonic stage are known in the Central Asia as well. Large proportion of all these faults can be considered as being active. And from previous video, you can figure out how much earthquake happened here in the last couple hundred years, and big ones, higher than 7 magnitude. We want to point out that active faults play dual role in slopes destabilizing. First being causative structures of large earthquakes, active faults delineate zones of most intensive seismic shaking that trigger large-scale rock slides. Besides, any large fault zone is characterized by intensive fracturing, hydrological anomalies, and so on, conditions favorable for slope failure. So it's kind of, as I told you, this feedback, yeah? So original scale map of active faults provided by Trifonov. You can see it here. And it's, you can, we saw it also on this, I show you these faults, big ones, on this geological map as well. You can kind of see through the coloration of different layers. Fragments of this map embracing the former Soviet part of the region in question is shown on figure 3.3. So that's the one. 3.3. Yeah, so the indicating these big earthquakes here too. Some active faults were ruptured. 1812, Nilki earthquake in Xinjiang area, and 1992, 7.3 magnitude Su-Samir earthquake in central Tianshan. Says figure 3.5. So let's have a look. Hope you can see. I'll just zoom in a little bit more. Small ridge passing along the right slope of the Cheonaksu River Valley, northern Tianshan, formed by recurrent surface faulting. The latest episode was associated with the 1911 8.2 Kimin earthquake. The lake with the submerged trees was dammed by this reverse fault. See this little bit lake? Giant erosional canyon at the background, that one, was formed after the earthquake. The exact date is unknown by the breach of the glacial lake associated with the same surface rupture. So you see, you have the earthquake and you have all these other events related. And on the second picture, surface rupture thrust fault with vertical offset of 2.5 meters of the 1992 7.3 Su-Samir earthquake, central Tianshan. You can trace it, you see here. Above, 5 days after the event, below 14 years. You can see how it's changed since. Much more active faults ruptured in prehistoric times have been identified and studied by detailed mapping, profiling, trenching. So you do know the recent events because we experienced them, we reported them, we can find them in recent data, even photograph it. But all the stuff geologists obviously reconstructing. But so the goal, they dig they find the fault area exposure and they create this trench. So kind of basically digging a couple meters wide hole through this fault in the mapping and measuring and trying to figure out how many times have been ruptured in the last whatever 1,000 years. Several northwest trending faults such as Jungarian fault forming eastern boundary of the same name mountain system and the Talas Fergana fault intersecting the entire Tianshan demonstrate distinct strike slip motion. And there's a saying that numerous case studies, special and likely temporal coincidences of active faults and large-scale slope failures, letter proof, require extensive dating, will be described in the following chapters. And that's what I told you. So you go and you find faults, you trace them, and you find the landslides. And then by dating the landslide, you can more or less know, like, okay, this looks like this landslide was caused by the earthquake. There's a specific kind of evidence you can look for, and like a scar, like type of motion, like river changes, all this stuff. And then you can date this landslide and plus minus know when this fault actually ruptured. It's another way to kind of support your suggestion of the fault activities or even just figure out. All right, seismicity. So let's jump through here. Instrumental and historical records. Central Asia is one of the most seismically active parts of the world. Sorry, towards the end I'm going to do this. Despite short period of observations, generally less than 150 to 200 years, hundreds of strong earthquakes have been recorded here, several of which we already mentioned, 1812, 1889, and remember this 1889 caused this dramatic research in that area, 1902, 1906, 1911 as well, and magnitudes of those, I'm going through the pictures, about 8 magnitude and even more, and many other exceeded 7 magnitude. And I'm just because I live in New Zealand and I've been through Christchurch earthquake, through all of it, and then also we have Kaikoura earthquake. I've been through that too, and we're all waiting for Wellington. Well, now we're not waiting for it, but everybody predicting the Wellington fault is overdue, and that's not nice, because Wellington have a lot of big buildings. The CBD, basically the skyscrapers located just within, like basically on the slope. on a fault, and university is standing in Victoria, basically on a fault. So when I'm reading about like how much magnitude 8 or 7 people experienced in that area, it's dramatic. It's very dramatic. Although it's in the mountains and so on, but still they have cities, they have villages, and it's dramatic. It's a little bit not geological, personal perspective on the earthquakes. Data on the historical instrumentally recorded earthquakes were summarized in several catalogs, so we can find all this in the provided in the chapter 2. Tanshan, Jungaria, particularly all earthquakes occur within the Earth's crust at depths from 5 to 25 kilometers mainly. This is a very shallow. So we have, like sometimes we have earthquakes in Cook Strait, quite often actually, and quite often we can feel it. In my house as well, and stuff shaking, something can fall down, but it's not so bad. But these guys like 30-40 kilometer depths, you know, and you can imagine it's the Cook Strait, so it's under the water as well. But when it's 25 kilometer, like a Christchurch earthquake was very shallow, this shake is crazy. So it's very surface, very intensive. So these things depends, you know, the effect as well, how deep it is, where's the epicenter. Also, what type of material you are, you know, on. In contrast, the Pamir, most of the historical earthquakes occur depths 70 to 150 kilometers. That's kind of like deeper stuff here. This belt of deep focus earthquakes passes in the northeastern direction from Hindu Kush range in Afghanistan towards the Karakul Lake in northern part of Pamir. That's the one I show you, and so-called Hindu Kush focal zone. Largest of these earthquakes are felt over vast area, usually much larger than that affected by crustal earthquake of the comparable magnitudes. And you can see, they even tell you here, you can even feel it on a bigger distance. Spatial distribution of crustal seismicity is quite uneven. No large earthquake higher than 5.5 have been recorded in this historical time in Jungaria. In Tanshan, several distinct seismic belts can be delineated, especially in its western and central part. Most of the earthquake, largest of which are now 1907, 7.5, Karatak earthquake, 1941, Garm earthquake, 1943, Faizabad earthquake, 1949, 7.4, Khait earthquake, Kansu, 1974, and 1902, Kashgar earthquake, magnitude 8. And then occur along the southern feet of the Gizar, Karetagin, Alai, and Koshal ranges. In 1716, large earthquake destroyed the Akso town, and I give you previous location. Another seismic belt coincides with the northern chain of the Tian Shan, while total number of earthquakes here is much less than the southern boundary belt. Well, kind of obvious, that's where you have this most crushing happen. Much of them 1885, Belovostok earthquake, Verny earthquake, we talked, gigantic Chilik, and 1911 Kemin earthquakes, 8.2. And followed by other earthquakes. So, so they're kind of basically listing here, and then they're talking about earthquakes in the Borohoro range. You remember this southeast of Jungaria range. Large earthquakes whose descriptions are quite scarce occur in this zone east of the border in Bishkek. 4075, 7070, close to the 8085 Belovostok earthquake epicentral area. And in 8007 in close to modern Almaty. The only one large earthquake recorded in the inner part of the central Tian Shan, 1992, 7.3. Largest earthquake with magnitude more than 7.5 magnitude occurred in 1946 in the western part of Tian Shan, west of Talas Fergana Fault, junction of the Chatkal in the Aitanok ranges. So there's a lot of data and a lot of events we do know about, so this continues, so I think I will just skip that. It should be pointed out that analysis of the spatial distribution of large-scale bedrock landslides does not reveal close correlation between this phenomena and spatial distribution of large historic and instrumentally recorded earthquakes at a regional level. Rockslides, despite the uneven distribution over the study region and pronounced spatial clustering that will be described in the next chapter, Pamir, often concentrated in the areas that have not been subjected to any strong seismic shaking in the historical times. That's kind of, I think, worth to mention. Central Asian historical and instrumentally recorded seismicity is characterized not by quite uneven spatial distribution, but also by temporal clustering. Large earthquakes mentioned above occurred in a few decades at the end of 19th, beginning of 20th centuries. Yeah, that's what we say. That was kind of very active time period for that area, and another activation of seismicity in the form of more than 6 magnitude earthquakes occur in 40s of the 20th century. And most of them triggered significant bedrock landslides. The recording period is too short to make sound conclusion about regular temporal coincidence between rock slides failure and seismicity. So they're trying to tell you that we didn't find, or we didn't have enough data to correlate seismicity and landsliding. Paleoseismological data. So paleoseismological, that's what I told you, that you go there and you dig a trench in your fault and trying to figure out what's happened in the past on this fault. Or you study something else, for example, geomorphology. Yes, so we study this river diverted. We have this landslide happened. Could it be an earthquake trigger? Yes, if it's in the vicinity of the fault, and you get looking for the clues to prove or confirm that this earthquake happened through something else. Yeah. Due to quite short period of historical recording of Central Asia earthquakes, it's obvious that paleoseismological data should have first priority for seismic hazard assessment in this region. What they're trying to say that you're looking for what's happened in the past. You kind of build a trend, build correlation. That they showed before that we cannot see correlation in the last couple hundred years. Yeah, but if you have a bigger database for all the stuff, you can have a more sound conclusion. Okay, we have this type of earthquake. For example, if we have I know people do it in Southern Alps in New Zealand. So if we have more than 8 magnitude on Alpenfault happened, we're going to have that number of landslides. They're going to be spatially distributed like that, and they're going to be plus minus this type of volume. That's dramatic. That's how kind of like what do you do with this information. Here we will present in brief several examples of primary paleoseismic evidence, surface faulting. Yeah, so that's direct thing. You can go on the land and see, okay, there's a line going through and it's been displacement, for example, 5 meters, 10 meters, and it can tell you how active this fault. So paleoseismological investigation, Central Asia, been performed since 1970s in Tajikistan, Kyrgyzstan, all the authors provided Kazakhstan. Karinkov summarized the results for Kyrgyzstan. During the last decade, the studies continued in Kyrgyzstan and Kazakhstan mainly. Yeah, we don't have much, maybe some, just local research happening by some self-funded or whatever, European or whatever states-funded researchers who come to that Uzbekistan, I guess other areas, but I don't think there's like a big government program that mapping, researching, for example, like we have in New Zealand, yeah. So it's these areas, a lot of research will be done. In the Jungaria, most prominent evidence of late Quaternary surface faulting were found along the Jungarian fault. Extreme pressive surface ruptures featuring dextral strike slip and surprisingly reverse kinematic were found there. That will be interesting for those who study faults and stuff. I've never been so much into the faults, so I do know this stuff, but I'm not specialized or done any work directly. I've been watching people doing it, been involved in programs, but not directly did it for myself. In the Tian Shan numerous evidence of the prehistoric surface faulting were found both at the faults and have been ruptured by large historical events such as 1885, Vladivostok earthquake, Kemin, and Nilki. Check my sound, will work. So that's you see that's just example of basically trenching logs of Oynagjar trench across the Atbashi fault, excavated, and give you the coordinate featuring recurrent offsets. So you see, even if you're not geologist, you know nothing about faults, you can see, okay, so that's the events, yeah? Fault D, fault C, fault B, fault A. So you have your material, you have your layers, and then shaking happen. You disturb it, and then again, and again, and again. And you can study it if you're a fault nerd, and you can tell us what's happened and when. I hope so. Numerous trenches excavated across active faults revealed evidence of recurrent faulting associated with large prehistoric earthquakes. Besides surface faulting, indication of seismically induced liquefaction were revealed and described in some parts of Central Asia region, banks of the Issyk-Kul Lake mainly. You see, that's another thing that I say, like how, like a detective, you can other way to see if you had earthquake events. So, for example, in New Zealand, we have this tsunami, yeah? Tsunami shores. You can looking for tsunami waves. Some people looking for tsunami kind of waves. They're not technically tsunami, but tsunami caused in a lake. For example, Wakatipu Lake and Queenstown, South Island. You look on the shores, and there's like unusual kind of layers on the slopes of remobilized material, and it'll be caused by if there was an earthquake happen and shaking of the lake and the water, kind of washed off, higher, like a big, like a little tsunami, and it's created this benches, and you can date them, describe them, and see it was from this catastrophic event, for example. It's my rough example to you. And that's what they're looking here for liquefaction, for example. Numerous trenches excavated across active faults revealed, this faulting associated with large prehistoric earthquake. Besides surface faulting, do I read it again? Yeah, I do read it again. This promising method of paleoseismological studies can be applied to lake sediments accumulated in the landslide dammed lakes as well. So you can have earthquake, block the valley, lake formed, sediment accumulated, and then could be drained, could be not, and you can describe it. And results of these studies will be presented in section 8. So that's interesting part of this interconnection that I told you before. We can read it later. Unfortunately, we have no data about similar detailed paleoseismological studies with trenching carried out in Pamir, both in Tajik, Chinese, or Afghan parts, though there are distinct geomorphic evidence of recent recurrent surface faulting in the mountain system too. You see this saying, we don't have much in-field data, but studies done there. But sometimes people kind of look on the satellite images and comparing and this kind of stuff, and can map and see evidence of faulting there too. But maybe in future there will be no borders on the planet, and people will not fight for anything, and we can go and research. Magnitudes of the prehistoric earthquakes identified by studying of surface ruptures were estimated based on relationship between surface rupture lengths and displacement on one hand, and earthquake magnitude on the other hand. So people are doing the studies. Northern Tian Shan, Kyrgyzstan, Kazakhstan in the past was associated with active fault in divine tectonic anti and syn forms. Alright, just go skip through now. If you are really into faults, you're going to read this. This finding strengthened the assumption of seismic triggering of bedrock landslides, which will be discussed further. So there'll be a whole chapter about landslides triggers. So let's come back to those images that we saw, and we're going to skip through. Yeah, so here they indicated you a lot of faults. You can even just go on Google Earth and see them in alive. And I learned to see these things before I closely work with the fault people. Fault and fault, but you can see it. You can see it in the field. You can see it from satellite image, and it's sometimes very striking and straightforward. You can see here in this image, for example, red line indicates you boundary of Sarikol intermountain depression displacing recent landforms. Rupture displacement, fresh, likely Holocene moraine. Yeah, so the Holocene moraine, that's whatever last, where's this Holocene, last 20,000, and you will, if you disturb this material, they've been, we do know, 20,000 years old. So it's mean this event happened in the last 20,000 years, whatever, 8,000, 10,000. And you see, it's not always like a straight line, sometimes curving, yeah? Here as well. Rupture displacement, alluvial fan. Only modern floodplain have been affected. I'll try to zoom in. You see here. You can find these places, give you coordinate Google Earth image. Let's have a look here. Another one. There's the trench. I think it's probably channel something, dig it in, and you can see the displacement. Sometimes the rivers, if you have this kind of you see like a jump in the river flow valley, it's indication of your fault displacement too. Very straightforward. Here as well, it's indicated to you. And here I wonder, what is it? Jungarian fault. Right lateral strike slip kinematics with reverse kinematics. Reverse and dashed oval mark the most prominent 10-meter right lateral offset at the B here. 10 meter. Here reverse kinematic. Let's have a look here. It's fragments of Flaps fault. Strike slip lateral, right lateral strike slip kinematic highlighted by the pull apart basin marked by the red arrows. Here, see? And eastern section with prevailing vertical offset marked plus and minus. So plus that went up and it's dropped down, and you can see the lake here, and it's kind of like a depression. You see it's more vegetated, probably the result of it. A small lake was formed in the gully at the down-thrown side. Larger red arrows mark the main rupture. That's where the main actual fault happened. Smaller arrows mark the auxiliary rupture north of it. Okay, I don't know how to pronounce this word. Please write me in the comment how bad I am and how it's correctly to pronounce. Alright, so special distribution of earthquakes epicenter in Central Asia. That's basically summary of all this seismicity chapter. Have a look. Crustal mantle. So mantle more deeper, yeah, and crustal more surface. If you kind of look in, imagine it in 3D, like depths and geographical special distribution as well. Sometimes people draw pictures like that. But here, just use your brain to create it in your mind. So the yellow stuff, kind of deeper stuff, and then the red more crustal. And you see how you can trace the main faults through this red activities. I believe here it will be recorded in prehistorical as well, probably. Unfortunately, it's not indicated. All right, so let's move on. Do we have time? Shall we finish? Let's do it today. Climate, glaciation, and hydrology. And it's not very much information for that one. Let's go through that. I will cut this in the sections and republish these videos, so you don't have to go all the way through, or you can just listen to me like a podcast or whatever, all the way through. There's the last pictures we didn't cover, so the Kalmakashu surface rupture here and here as well, 8 meter, you see the drop. Here the 4 meter, and that's probably the rupture indicated with the arrows, similarly here, see? As well, this is more, you see, more recent material, it's kind of cutting through. And here indicated as well. Rushan Range in Western Pamir in Tajikistan. C is the small scarp at the southern bank of the Chapdara Lake. Beautiful, beautiful locations, very dramatic landscape. Climate glaciation and hydrology. Climate of the Central Asian region can be classified as extremely continental. If you know nothing about climate, continental, it's mean remote from the sea, from the ocean, from the shore, and it's more dramatic. If we're talking about continental, it's cold at night, hotter during the day, or hotter during the summer, colder during the winter. Temporal, marine, or marine kind of type of climate, it's more like smoothed by the ocean, because ocean water holds the temperature through the winter or through the night more better than land. Land warm up faster, like rock, but it's cooled down also faster. Water warm up longer, but for it's hold the warmth longer. Yeah, if you kind of think about that. Plus, you have more humidity, so it's kind of smooth and these conflicts, these extremes. So every time you hear something, somebody tell you something more continental, it's more extremes. And when you a night, a day, and seasons. And when you hear something more temporal or marine type of climate, if I pronounce correctly, so it will be kind of more smooth, like here. Like for example, if I was continental in my latitudes, like New Zealand, I will experience something more like in Kazakhstan, Kyrgyzstan. If I was like I am next to the shore, next to the ocean, warm ocean, surrounded, whole islands, I kind of like summer, yes, hot, amazing, but in the summer I can have days equal to winter days, and in the winter I have hot days, not as it's summer, but warmer and nicer. You can go in t-shirts, so more smoother climate. All right, so it's called by location rather low latitude in the inner part of the huge Asian continent, far away from the oceans. That's what I told you. I'll show you on the map. Elevated mountain regions and surrounded by plains occupied by deserts that affect the climate not only of the foothills area but of the entire mountain system. However, large topographic diversity determines sharp moisture and temperature contrast. So you will have this, a lot of mountains. So we're not just like in Sahara, basically dry desert everywhere, but because we have these valleys, sometimes more precipitation there, or like a local water basins, like lakes, like Issyk-Kul or Balkhash will as well affect it, and glaciations as well. Mean annual precipitation vary from less than 100 millimeters per year and less than 90 in some parts of central Pamir, more to 1,000 millimeter per year, up to 1.6 millimeter per year in some parts of western Pamir and Tian Shan. Annual temperature variation in the study region can reach 40 degrees, 50 degrees, and even more, resulting in intensive physical weathering. So it's mean like you can have minus 10 during the winter, minus 20, and 20 during the summer, or 30, or even more contrast. Like Ali Valley, we were, it could be, during the day it could be 30, 35, and at night can drop down till 0. Big extreme, even within the days, can you imagine? So, and it's caused this physical weathering, and that's why there's so many kind of this rocky, dry valleys with a lot of kind of desert material there. Saturated Atlantic air masses carried by the eastwards air transport high above the Central Asian desert reach high mountain ranges, providing rather significant precipitation on the western slopes. So everything coming from Antarctica, which is a show you going through the Europe, then Caucasus, Caspian Sea, and then finally reach the western slopes. In contrast, eastern part of this mountain system and in the depression of Tian Shan and Pamir are characterized by much higher aridity, drier. And you can imagine if we look on our Google Earth, that's I told you Atlantic, it's kind of going through all of that, and whatever left precipitate here, and here you have this, you have all the China, and then you have lose all your water on these slopes. That's why Bhutan, Nepal, here all this area is very humid usually, specifically Burma, Cambodia, Thailand is very, very humid. But then to reach Tian Shan from the east, you have to go through all the Tibetan Plateau, cold temperatures, dry area, and that's the reason we have this Taklamakan desert here. Taklamakan. No, I don't think I say it correctly. Okay, I'm waiting for your comments again to correct me. All right, let's just read text. Most of the precipitation occurs in the summer period. Winter thickness of snow in the valleys looking westward reaches 2-3 meters, while some eastward looking valleys are almost snow-free, being used for winter pasture. Intensive summer air heating above the Central Asia deserts facilitate high level of snow line in this region that rise from 3.6 to 3.8 meter sea level. And I think, in Tian Shan it's up to 5,000. In Pamir, many passes at more than 4,000 meter sea level at free of snow in summertime. And I had a video about a very, very old video on my channel talking about snow line and about glaciers, how glaciers formed. And the snow line is kind of like the reason or why the glaciers. And it all depends how high your mountains, where they are, so which latitude you're located in, northern southern hemisphere difference, how far from the ocean, all these things. Yeah, so we can have glaciers the most kind of closer to equator in they're called like subtropical rainforest glaciers terminating into the sea level. Well, not so much right now, but it used to be Fox and Franz Josef glaciers in New Zealand. And that's the only place. It's because we're kind of so close to the Antarctica, but in the same time, a very steep slope, accumulation area to the east, and that's enough, enough snow supply because of this roaring 40s latitude around southern hemisphere, which like a conveyor bringing a lot of precipitation to these glaciers so they can go so low. So, and that's why Franz Josef and Fox Glacier are so unusual, and many people like to study them. Climatic conditions, particular site strongly depends on its altitude. While mean summer July temperature is low, mountains is about 20-25, decrease below zero at the watersheds of high mountain ranges. Mean winter January temperatures is negative throughout most of the mountain parts of the study region. Resulting formation of high altitude permafrost that is widely developed in the most elevated parts of the study region. Considering present-day climate change, global warming, permafrost degradation could facilitate destabilization of high slopes. So causing basically destabilization. There's a people in European Alps specifically I know who study that. So they put like a little sensors into the slopes. So you're kind of on the border between the still permafrost. It's when temperature doesn't go above zero through the year because you're so high in altitude, or like in Siberia, northern eastern Siberia, you're too close to the Arctic pole, so the temperature doesn't, so the ground doesn't warm up enough to melt. That's things important. So that's people also study like in the slope and the vertical, so the higher you are. And I know people who does study, so they put like a sensors that measure temperature, the kind of like breath of the rock. So the rock have moisture within some kind of cracks and stuff, and it's actually does react on humidity and like our hair. They kind of like they can expand several times when there's humidity, and if you have hair that's very sensitive, that's why we use in the barometers the human hair. It's very sensitive to humidity change. You can actually detect it, and that's what we do on the slopes in the high mountains. I know people did it around Mont Blanc in in the Alps, European Alps, and they recorded how the slopes start with the kind of global warming, change of the temperature through the seasons. This amplitude, the rocks become looser and then they fall down, and how it's called, slope instability. Yeah. So all these things, it's interesting. Several examples of sudden formation of large-scale bedrock landslides in the higher altitude zones of the study region that occurred without any identifiable trigger will be described hereafter. Yeah, that's another thing. It's like there's no trigger of your slope stability, of your landslide. And the big ones, which usually people like, oh, if it's a huge landslide, it's more probable very heavy rainfall or something like that happen, or the earthquake, yeah? However, not always. And we do know some of them happen just by themselves, and it could be something hidden we don't know about, like permafrost degradation, or just everything accumulated, and there will be the trigger point eventually when the slope just want to release itself, yeah? Topmost parts of most of the mountain ranges are covered by snow throughout the year, and many of them are glaciated. Most intensive glaciation characterized central Pamir with the largest more than 80 kilometer long Fetchenka Glacier. Transala Range, northern boundary of Pamir, highest Tian Shan, and the Kyrgyzstan-China border with 60.5 kilometer long southern Inilchik Glacier, and I think that's the one I show you. And its western side, the several large glaciers, its eastern side, and the Akchiryak Plateau in central Tian Shan, and the water divided by the Narin and Saridas Aksu river basin. The specific feature of the latter, as well as some other glaciated regions, presence of so-called flat summit glaciers. So they develop not in the valley, but on the elevated plateau-like remnants of pre-neogenic planation surface. So you have this kind of like higher mountain, you have slight depression there, and that's the place where you can accumulate snow, so it doesn't go down the slope, and there will be the source, kind of like a feeding area for your glaciers. Some of the Pamir and Tian Shan glaciers are surging, that sometimes result in the river damming and outburst flood. So the surging glaciers, I do have an interest to make specific videos, so please, I have somebody waving me, hello. Please write me if you're interested in surging glaciers. I spent a lot of chunk of time researching and studying them. Well, not directly, but for my research, I was very digging into the surging glacier. It's something phenomenal, and if the glaciers surge, it doesn't mean it means the glacier is sitting in the valley like normal, and then boom, for no reason, you think you're just gonna go down the valley. Could be kilometer, 5 kilometers or so. Yeah, Lenin Glacier, the one we worked on, it is surging glacier, and we have, just if you look in the satellites, even Google Earth, it give you last 20 years good, like almost every year images of that area. You can see the surges, yeah. And why they're dangerous? Because if there's something in front of it, some kind of lake or river, and usually it is, it can dam it or just cause like just remove material as outburst. So outburst flood, it's when just big chunk of water just going down the valley, so it can happen. Total area occupied by glaciers in the Pamir is estimated to reach 12,000 square kilometers. Well, you might think it's a lot. For modern days, it's a lot, but in comparison with the past, not so much. Provided for Tian Shan and Jungaria vary from 6,000 to 8,000 square kilometers. Present, most of the Central Asian glaciers degrade, while in the past it was much more widespread. And we even talking about not so much like a past, but recent time, even historical recent time. Particularly all Pamir valleys, both in the central plateau-like section and the deeply incised western and eastern parts, were occupied by the glaciers. Yes, because we're finding the material of last glacier maximum, so 18,000 years, and then 8,000 years down in the valleys. So the glacier was there, at least if you go back in time, 8,000 years ago, the glacier was sitting here. So they're occupying all these valleys, in particular in Pamir. And can you imagine how much water was lost since? There is still water, there's a lot of water, but the glacier works as a reservoir for the water, like storage. And like, it's like when you defrost your fridge, you start defrosting it, there'll be a lot of water first, and then there'll be no water left, yeah? So it's kind of what's happening. In the Tian Shan and Jungaria, the Pleistocene glaciation was also much larger than at the present. However, many of the intermountain depressions, except the most elevated, have not been covered by ice sheets totally. And that could be the reason, because it's very arid, it's so far from the ocean, so you had a lot of temperature was colder, but it was not enough snow to feed those glaciers to go further down the valley. And how we know it? We can know it from going and study the glacier material in the area. So let's just finish. It's assumed that quaternary glaciation in this mountain region occurred repeatedly, being divided by warmer periods. Such process when glaciers prograde first and then melt, providing powerful streams whose discharge could exceed the present-day values significantly, should be taken into consideration for studying past landslides, because they must rework, if not destroyed completely, evidence of slope failures that can occur before during past stages of glaciation. Can explain deficit or not enough landslide-related landforms at upper parts of mountain ridges, with extremely steep slopes and scarcity of the evidence of older prehistoric landslide-related landforms, despite the longevity of the preceding evolution of this mountain region. So I talk about this a lot when I talk about glacier material, about Ali Valley, that you face with the problem, landslides, first of all, happening if you have glacier in the valley, so more probably landslide gonna go, into the deepest part of your valley, down the slope, by the gravitational law. And because we have glaciers, they kind of creating this nice, down slope, kind of basically sliding surface for the landslide. And they're going to go on into that. And they're going to fall down on ice. And then the ice will rework it or bring it down the valley or redeposit it, or, or whatever. Just it's become part of the glacier. And we will lose it from your database. It didn't happen. You can't see it anymore. That's the first thing. And secondly, that was authors saying here that it will be, even if it's fall down in the valley, but it's glaciated, the water from this glacier, or actually glacier, if it's surging, it's going to surge over and they're going to demolish it, destroy it. Sometimes we find like little pockets of the landslides, old landslides, somewhere preserved, but that's it. But it could be a huge event. You don't know. Maybe it was a huge landslide that covered whole the valley and the glacier come and just, demolished. And because in Pamir, for example, narrow, steep valleys, a lot of glaciers, it's impossible to preserve. Plus, also the glaciers are surging, so they can cause this big outburst of the material, sediments, water, and ice, which will just, wash away the older landslide. So it's amazing, and you have to keep it all in mind when you're trying to understand, all these tendencies and trying to describe, landslide activity in the area. All rivers draining the study area belong to the closed drainage basin, the largest of which are the Aral Sea Basin in the west, Amu Darya and Sirdarya, the Balkhash and Alakol Basin in the northern rivers, and I'll show you that on the map, and Tarim Basin. So many other rivers. Some rivers do not reach any water body, but disappears in the desert and semi-desert surroundings in Central Asian mountains, such as Chu River, draining parts of the central and northern Tian Shan, that flows towards the Sirdarya River but does not reach it at present. So it probably did in the past, but it's not enough water now because not enough glaciers or precipitation, drier. And also because of people probably use it for irrigation. All largest rivers that start in the higher altitude glaciated ridges are fed by glaciers and snowmelt water mainly, and are characterized by pronounced summer peak. And if you've done hydrology, I don't know if you studied at uni, we did have studied, we studied hydrology. That's what I'm trying to say. And we studied for a year, and we did all this study peaks. And depends where you are geographically, what is your topography, geology, all these things affecting your behavior of your river. So if you're somewhere in Siberia, your peak of water will be the spring kind of melt, but it'll be always delayed. And depends where you are in Siberia. So some rivers, this crushing of the ice and melting happen in April or, I don't know, maybe March, maybe not March, maybe even in May. So you have this peak of the water. Some rivers will be affected by the heavy rainfall in the area. So if you go to Southeast Asia, some rivers will depend on the monsoon, directly correlated. You know, all these things you have to remember, and then the glaciers and peaks of melting. For example, in New Zealand, Southern Alps, we have in Mackenzie country, the rivers, I don't wanna lie because I'm not hydrologist of those rivers, but logically, by studying glaciers, I know that the peak melting period for the glaciers, it's kind of April, maybe like towards end of April. That's when we go in, we photograph the snow line of the glacier. So it's the least snow on the mountain peaks before first cold come and bring more snow. So it's the maximum kind of melting for that area. And I will assume that's when the maximum peak of the river flow will be there. Yeah, or maybe it's a little bit earlier, like a month before. So think about this when you think about hydrology. For example, the Vakhash River that drains northern Pamir and southern Tian Shan has mean annual discharge 580 cubic meter per second, maximal July discharge up to 3,120 cubic meter per second, you see? So it's in July here. And minimal value recorded in February, 130. Mean annual discharge of the Pyandj River that accumulates drainage from most of the Pamir is 845 cubic meter per second. Maximal recorded discharge of the Narin River that drains large part of the central Tian Shan, 2.6 cubic meter. Annual value vary. It depends on year to year, of course, from 270 to 709. So you see, mean value 418. And they describe, you can read it continue, so I'm not going to bore with the numbers. So you can see the difference and how it's vary. And then we have Pamir. In Pamir, it's as low as 170 to maximum values up to 2.7 thousand. And depends on the western central Pamir. That's everything we just talked about. Depends on the climate, the precipitation. All right, let's read the last paragraph. Most of the rivers provide significant sediment yield, 10 million tons annually for the largest streams. So the sediment yield, it's how much actually material rocks suspended. Could be fine clays, sand, and sometimes coarse when you have rainfall or something, or glacier surge, outburst, you can move big boulders. So that's all the sediment yield. Both large rivers and especially smaller streams that drain rich watersheds and slopes are quite energetic, often representing just chains of rapids and waterfalls with white color of surface typical of the turbulent water flows. That is why many of these streams all over the region are named Aksu. Aksu, that means white water in Turkish language. And I remember when I talk about Alay, we have Komansu, red water, and so on. So they do change it. And I have a picture I'll show you. I'll put it here when I do it in the video, when it's Komansu, the red river and the white river stream join, and you can see this distinguished difference in color, and they don't even like mix when they meet each other. The Tajik part of the area, such streams are named Safedop, means the same. Another common river names is Karasu, and Kizilsu mean black water, and red, the Kizil mean red water, not common, sorry. Kizil, but it's in Komansu, it's the river name. In Turkish, due to dark gray or red or brown color of the water enriched by silt, such streams, even if they have rather small discharge, have large erosion power and can destroy any obstacles, interrupting the flow in a short time. These characteristics should be considered when analyzing siltation, how the silts accumulated, and longevity of the landslide dammed lakes. Yeah, so hydrology, it's not just how much water, which is act as something that actually moving material. So it's removing the landslide in the valley, and it's also bringing material and accumulated material. So you have to keep it in mind if you're a geologist. So this is just the annual precipitation. You give you example. Urumqi, Almaty, Tashkent, Dushanbe. Balkhash Lake, Issyk-Kul, yeah? And you see Taklamakan Desert is totally not much precipitation, and long-term annual average temperature in January, Bath in July, study regions. You see this contrast. All right, I think that's it for now. So I didn't have any complaints and questions. You have a minute or so to write me something. You can ask me anything you want. And next time we're going to look on this little bit identification, discrimination, like which type of landslides, criteria, what is a rock avalanches, how they're different from any other material, how can we tell the dues of fan shaped deposit origin, and also how they distributed throughout. So it's quite interesting because my research was part of it, identification of rock avalanche material from other, specifically glacial, and I'm very excited for this chapter. I hope you like this type of live streams and videos, and I hope you will kind of write me your feedback. What do you want to hear more about? Any complaints, suggestions? And I'll see you next time in the next videos. Bye-bye. Welcome to the live stream. To everyone who are interested in geology, earth, rock slides, and everything related. So today we continue our looking at the book about the landslide in Central Asia, and we're just going to go through every chapter, and I'm going to show you a lot of pictures and views on Google Earth of the study sites. And the videos which I will then slowly relisting in my main video list, I will add some pictures, for example, my personal pictures from the sites, or something what I talk about, but I couldn't show you straight away because in the Google Earth they not allow you to reveal the pictures which provided due to the privacy. And I'll have some of my personal pictures which I can add later. So stay with me, share it. While we have a live stream, I do take any questions related to this video, any other videos. So it's the opportunity for you. All right, so we stopped last time. We looked through the general information about the area, and now we're going to dive into specifically the slides that have been studied. I just want to see if I have, that's our Google Earth study sites. I prepare some of the locations for you, and we move to the book. So chapter 4, Principles and Criteria of Landslides Identification and Discrimination from the Features Formed by Other Mass Wasting Phenomena. And this chapter quite big, so today I'm just going to go through first point, 4.1, because we're going to look in some landslides, and I'm realizing it's a little bit too much maybe for, one live stream. Maybe not so much for you, but for me it is, so I'm going to go slowly. There's also in this chapter we talk about rock avalanches versus moraines, and I have specifically my part of this work done in my research in New Zealand, mostly on some other areas, and also the Central Asia as well, in Pamirs. I was doing this in Alps, European Alps and Southern Alps of New Zealand, in helping other people identify rock avalanches from the glacier material around the world, actually, in fact. And I did some work as well in Norway, Fjordland, which I'm planning to do some videos in the future because I have a lot of material. So if you're interested, just please support me by likes, sharing, and asking me questions, what you're interested. Rock avalanches versus rock glaciers. Rock glaciers, it's in my list of planning to do video about rock glaciers in general. It's as I said in previous streams, very interesting, intriguing type of glaciers. And they're very, very often misidentified as some kind of debris flows or rock avalanches. Abnormally large fan-shaped deposits in the region. That's another thing which we're very common in New Zealand. We have it a lot here, and of course in Central Asia, China, whole Tibetan Plateau, and South America, North America. It's the big fan deposits, and they only with the practice you can kind of keep your eye on it and learn to identify them. But sometimes people do just remote mapping, so they're trying to identify deposits just by looking on Google Earth images or satellite images, high resolution, amazing images, or they even fly drones and they photograph a landscape and then they create 3D maps and try to identify deposits. Often it could be misconfused as well with ore or glaciers, or not so much the moraines, but with rock avalanches. And we will, in this chapter, we'll talk specifically why it's a different phenomena, although they're both like falling rocks from the slope, you would think, but the different process in different region and how they behave and all these things, yeah? So here we're talking about non-catastrophic versus rock slides, rock avalanches, catastrophic. Bedrock landslides in the contemporary glacier regions, and it's about those rock avalanches. And I talk about this in my previous videos as well. Check it out. The rock avalanches that fall down on actual ice of the glaciers, or for example, down wasting glacier, dead ice, all these complications. And they could be discarded as well because you cannot recognize them, or they fall down on a glacier and they become part of the glacier, and people just like, okay, it's not my business, it's the part of the glacier. Or they could be, they will be moved differently by the ice or not moved. They will affect the glacier, and the glacier will actually affect the landslide. So in the past, if you have just a rock avalanche, big landslide fall down in your valley, there's nothing there, just a stream. It will block the stream, or probably create some kind of confusion with the stream, and then it will eventually find its way through, because the water always finds a way out. But if you have on top of it glacier can or remove all this material, or be blocked by it, or it can cause the glacier to advance or change its mass balance. So this is all basically my research was involved with, and I have talked about conversations about glaciers and rock avalanches in my very, very, very first videos on this channel. You can have a look. But we can talk about this later in more detail. So that's why this chapter is quite big, especially for me, because I realized I will talk a lot. So I decided to go slowly. So let's start with first general criteria, and there's like a little introduction to this whole chapter. We will go as usual. I read through and I will stop and put my comments, and we're going to go through images and Google Earth as well. So large-scale bedrock landslides, so that's straight away give you identification. So landslides could be all sorts. And if you're not geologist, or even if you're geologist but you don't work with the landslides, it's quite confusing. And I just to show you this image, just want to see if you can see it. Yes. And we have all sorts of different landslides. So landslide is a very, very, very general kind of name. Land sliding, sliding land. So whatever your piece of land going down, we can call it a landslide. But then you can work with all sorts of different types. Depends on how they're happening, how they move, how they're deposited, how big they are, what type of geology underlying source of your rock, is there water involved or not, all these things, and the size very important as well. So we have traditionally we have this kind of general picture which we usually show students, and we talk about different type of landslides. Rotational landslides, when you have collapsing of the earth, and it's a little bit kind of why it's falling down. You can imagine it happen in one go. It slightly rotate, basically. That's why it's rotational. Translational landslides, so you're just moving everything down the slope, and you have all this cracking in a way happening, and kind of differentiation along the deposit will be with the movement. Yeah. Block slide, when you have this big, just a slide falling down. You see, it's very controlled here by your lithology. Rockfall, that's more common on the road if you're driving somewhere in the hilly or mountain area. We have a lot of those even here in, for example, around North Island of New Zealand. There's a lot of rockfalls happen, especially after heavy rainfall. And the rockfall, it's more like a looser, separate boulders falling down. Could be like a group of them, but they all behave kind of one by one. One go in that direction, one fall down on the road, other one stay next to the the base of the slope, and this kind of behavior. When The landslides, the ones we show on top, they kind of more behave like a one body here. Topple, it's this, you see, because it's controlled by lithology, this a little bit different type of falls, and depends on where it's come from, the source, it's going to travel further or closer to the slope. Debris flow, this is something involved water, a lot of water, so when you have heavy rainfalls, usually it can trigger this debris flow, so the slushy, kind of muddy, could be rocky type of material which located here on the slope could be by the gravity, it will saturate it with the water and start behave like basically like a water flow, but it's not as a river, but more like if you pour in some, I don't know, honey or something. So it's have a specific properties how it's behave, debris flow. And then you can actually identify it from other type of landsliding when you're in the field. Debris avalanche, so that's more like looser material avalanching. Earth flow as well will be characterized by its fluidity. Creep, it's when it's happened a long time, so like through a long time, you see by the tilting poles, sometimes tilting or even curved kind of trees. It's moving, but so slow, so the trees or poles, well, specifically vegetation, have time to kind of readjust to this creeping. And often people identify these things in the field by looking on a vegetation. If the vegetation trees kind of unusually tilted or curved, it's mean there's something like that happen. And of course, if you see a lot of tilted poles, unless it's very forgotten area and people don't do anything with the poles, it's more probable that you have kind of creeping landslide movement happening. And also these cracks, it's in all of these landslides, it's a very, very good, like one of the first identification that something happened with the slope. Lateral spread, it's just more kind of like different type of this topple or block slide type of movement. Yeah, so it's kind of spreading the area, not very much topography involved. And also the rock avalanches. So rock avalanches, it's usually catastrophic, more commonly caused by the earthquake in the high mountains. When you have very big drop, could be 2 kilometers, 3 kilometers, 4 kilometer drop, and the rock avalanche move is one big mass. So they're just deep-seated, we call deep-seated rock avalanche, because you can, if you have an earthquake, you can trigger the big amount, just of the slope going down, and there will be deep-seated. It means not just like subsurface, like on these pictures. So just like surface area just collapse from the top, or like here, but it will be like a big chunk of the actual slope collapse. So your scar, like your source scar, will be very, very deep, and we call it deep-seated. And usually this deep-seated landslide, they cause like a cirque formation. They're not necessarily caused by the earthquake, but more probable, especially in high mountains. You have a high earthquake activity, seismic activity, and they will travel often because it's a big chunk and they have a big drop. They might travel 1, 2, 3 kilometers. It's like normal for those rock avalanches to travel, but it depends on the valley and size, and maybe if it's earthquake triggers a big earthquake, they might travel quite far. And we talked about it already. We have earthquake landslides which travel 30, 40, 50 kilometers down the valley. Often the deposits even can climb in the opposite walls, and I saw it in New Zealand. We noticed that they can climb on opposite slope several hundred meters, like not a big deal for them. So you can imagine the forces involved. So you don't want to be in the area when it's happened. All right, so we just discuss about landslides, so I have kind of understanding. So this here in this book we're more kind of focusing on the large scale bedrock landslides, and we talk about them here in detail, but not necessary. So large scale bedrock landslide could be identified based on the combination of morphological and seismological characteristics, allowing their recognition both on the remote sensing imagery and in the field, and distinguishing their bodies from the deposits left by other geological mass wasting phenomena, glaciers, rock glaciers, extreme debris flow, and that's what we That's why I already mentioned. So you need to identify it from any other material. So usually if we're talking about mountain area and we're talking about Holocene, last whatever 20,000, you more probably had glaciers in the area, rock glaciers, again, just type of glaciers, debris flows, these debris fans. So you need to know that, okay, this is the landslide and this is something else. While rock slides and rock avalanches can be characterized, at least in many cases, as dry granular flow, so it's dry, the alternative phenomena could not take place without the intermediate agent, water and liquid or frozen state. And frozen state could be related to your rock glacier, or water liquid to this debris flows or mud flows, these things. Sometimes, so here, just come back. So remote sensing imagery, so it's very good to identify, because we cannot, even when you're on the ground, you cannot see whole the area. So if you're in the mountains, of course, doesn't matter how high you go, you still cannot kind of like observe all the landscape. Of course, it's very important to go in the field and have a look in the field to give you much better understanding what you're looking at. And sometimes on the image we can see something, but in the field it's revealed differently. And often, if you have vegetation, of course, it's a big deal as well. Over vegetated area, like for example west coast of New Zealand, very hard to identify anything there. We use the LiDAR images, which they kind of shoot through the vegetation, through the bushes and the trees, and they show you topography, underlying topography. But still, you have to go in the field, and somewhere you will find some river or stream crossing through, some boulders, some geology. You can come and touch every rock and see if it's same type of rock or not. So there's a lot of identification. Yeah. And sedimentological characteristics, this whole chapter will talk about this, and that's what I kind of focused as well. It's you look actual material of the main body of the landslide, and it show you what's happened with this. Because if you can imagine, when you have big landslide, catastrophic or something, you're crushing and changing material, and it will be dramatically different from other material that have been brought by on the beach by the waves or by the river flow. Yeah. Where there's a sorting and polishing of the rocks happening while water moving the material. Even mud flows have specific type of a little bit sorting, a little bit rounding of the rocks, this kind of stuff. So we will look on that. And also, in a very, very important point, it's the type of rock. So lithology, and not just the lithological composition of your material, but also how it's positioned in the body of the landslide. So if you have, again, if it's a river, you will have for example, rocks represented in the catchment of the river basin. So whatever river coming from the slope, so it's going to pick up the different rocks from all the slopes, some more, some less, but they will be representative, but they will be mixed. So because they're moving through the valley by the river flow. But if you have rock avalanche deposit, it's happened within the seconds, 10 seconds, 30 seconds, I don't know, 1 minute. Emplacement of this material, and usually the material, as you've seen in this picture, going to move. You see rotational, there will be some rotation happen, but the layering in geology, if you have any in a slope, they will kind of preserve through your deposit as well, so you can pick it up. So if you have granites and further down we have, I don't know, something some different lithology, some clay material, something, or diorite and granites, for example, and then they will move down and they will preserve like in the bands of this, so you can pick it up. I hope it's kind of clear here. All right, so we'll talk about this later, and in my talks, when I talk about my criteria to recognize rock avalanche material from the glacier material, I'm really focusing on that too. So let's continue. Sometimes, however, bedrock landslide identification is not so obvious. First, the gigantic size of these features complicates the recognition both on aerial images, each of which covers just a small part of the affected area in the field, if they could not be visible as a whole, and that's what I say. Some of the largest features were identified only when space images with a relatively high resolution, 5 to 8 meters and better, become available, allowing one eye to embrace the whole feature and at the same time to see the details of the morphology, and that's very important, the morphology. of the deposit. And another thing is these days we're using drones. So we fly a drone. We're basically just photographing, like taking many pictures of the area, and then using some software, it will build you up a very, very high resolution image of that area through just photographing. And then you can build kind of DEM, like 3D surface area of that photographed area. Maybe these days there's something better you can do because AI and stuff, but I don't right now doing this. So those who does it, please comment, say, yeah, there's better stuff. All right. So trying to see if we have a chat, if I have any questions. Some reason my one doesn't want to show you. I just go into my live stream. No chats. Please comment if you have any questions or or want to add something. Okay, so some of the largest features we identified. Yeah, we already read this. So detailed geomorphology, it can be exemplified by the Bishkek landslide from 8 to 12 cubic kilometers in volume. So it's very huge. It's in Kyrgyzstan, big landslide, one of the biggest, largest one in the entire Central Asia region, whose body exceeded 40 square kilometers in size, and the total affected area, including the headscarp, where it's come from, source and deposit, for 55.5 square kilometers. Or by terrace slide with affected area about 25 square kilometers. And I will, if you're interested, I can show you that on the Google Earth. So if you look on our area, so it's Issyk-Kul, I have here identified all the deposits, some of the deposits that were worked on in this paper. So the Bishkek, it's here, basically located not far from the a lot of studies landslides here, and that's where the Alexander Storm ran his summer school as well. They visited most of these famous landslides. So Bishkek landslide, you can see that's kind of borders the covered area of scar plus the deposit. So it's enormous, yeah. Let's have a look. If I turn off the map, and we can have a look. So that's its position here. If you kind of remember it, and there's some other little landslides identified. And if you looked on, I have a 3D 1.5 topographical amplification of elevation, so it's a little bit like, it's not in reality 1.5, so it's a little bit higher than it should be, but I always like to put this high elevation exaggeration so I can feel better the landscape. You can see here the big slide as well already. See how the material moved down, and that's all the body of the big large landslide with the headscar here. And there's some clouds on this image, but you can see all this kind of hummocky, weird material which already streams cut through, more probable since it was been deposited. So you can also figure out the relative age or the full age of it. So let's open the map. Yeah, so that's the deposit mapped here. Yeah, I don't know, this on the left, it haven't been mapped, and there's a couple two rock avalanches, so it's interesting to find out what we actually have here. You see, because some kind of mass wasted material here as well, feature. So in that area, there's a lot of these things. It's one of the biggest, and basically you can see from space landslides. I'll just come back to the north, true north, in the area, and you can see there's a much more different other deposits we will touch today. Great. So what they're saying here, morphological identification becomes more complex and questionable for older Pleistocene features that have been significantly reworked by erosion. And that's another thing. So if you have a fresh rock avalanche, which happened last year or last 50 years, It's obviously much easier and straightforward to identify. But if you have something that happened million years ago, or 100,000 years ago, or 20,000 years ago, even though, it's pretty tricky because you have a lot of reworking since even glaciers could occupy this valley, rivers, and so on. The additional complexity is provided by morphological similarity of rock slides and rock avalanches deposits with the deposits left by other natural phenomena widely developed in mountain regions that bring large amount of debris down slope or down the valley, sometimes resulting in a complete or partial blocking of river valley. Hence, we found it necessary to describe first the basic criteria allowing identification of the prehistoric rock slides and distinguishing them, the deposits, from those created by glaciers, rock glaciers, and debris flows. And that's one of the more important points you have to identify it from other deposits. Yeah, and one of the main one of the main debate that happened in the scientific community, it's to identify rock avalanches. And we'll read here why. The correct interpretation, these criteria were used when compiling the large-scale bedrock landslide database of the study region. The correct interpretation of such deposits, especially of those forming natural barriers in the formerly and presently glaciated river valleys, is not just a scientific problem, but it's critically important for landslide hazard assessment. So if you're kind of thinking, okay, you're doing your science and we identified the landslide or moraine or rock glacier, you'll ask question, who cares? So it's somewhere in the mountains. It's happened a million years ago, what's happening? But the main problem, it's the hazard. And we know with earthquakes in the mountains, they never stop happening. They're happening right now, and the valleys, glaciers retreating, valleys changing all the time. It's not just because of the glaciers melting. You have new slopes exposing, and they steep because they used to be filled with the ice and whatever streams of the ice or material that the glacier was bringing. Now they become exposed and they stop collapsing. But you also have earthquakes, and it doesn't matter where you are, in a glaciated or not glaciated valley, you're going to have landslides. And what's happening, it's the landslides happen and they catastrophic, and they can block those valleys, cause the creation of this lakes formation, which are not as secure, I would say. So the loose material which pulverized during the rock avalanche will block those rivers, creating those lakes, dam, reservoirs, which is very temporary, and any moment they can release. And I talked about this Sarias lake that created in 1911 after big landslide fall down in the valley. People still argue it could be the landslide caused the earthquake, but more probably it was earthquake that caused the big landslide. And this dam that built there, I show you in the previous live streams, any moment can breach, so just collapse. And the water from all this river that accumulated there in last more than 100 years now, will gonna go down the valley, and it's gonna go into the populated villages, cities, till the other lake. So half of the country, Tajikistan, could be wiped away, and Uzbekistan on the way as well. So it's a big problem. 2008 Sichuan earthquakes caused a lot of landslides and blocking and rivers and so on. So there's a hazard assessment, and hazard assessment could be both ways, overestimated or underestimated. And we need to have a correct database. How many landslides happen in the area, how they're prone, how they're active, how far they go. So by looking on these big landslides, how far in the valley they moved, and how they changed the landscape after it happened, and when the river find the flow back, when it's readjusted, we also need to think about this, for the safety of people, and of course pure scientific interest. So if past natural blockages, both intact and breached, were formed by glacier processes, they first indicate recurrent late Quaternary glacier advances and retreats, reflecting the differently directed climate change during this period. Secondly, considering present-day deglaciation typical of the study region and other regions, we can expect quite low probability of the occurrence of such events in the near future, and correspondingly low hazard and related risk of river damming and subsequent outburst floods unless significant inverse climate change. It's mean if we're going to have huge cooling event and the glaciers grow again and then they start melting and they're going to create all these lakes. But what they're saying that the glaciers already retreated, so we if the most of this stuff happened because of the glaciers, this outburst, catastrophic flows, we don't have to worry about it. There's no more glaciers. But in the same time, if you identify all these deposits as a glacier material, which is traditionally, I told you, like in Soviet times, they used to do this. I see the people just did it in New Zealand. They just, whatever, there's a hummocky kind of looking in a valley material, or must be the glacial. First of all, it'll give you incorrect dates for what's happened with the glaciers, where they were and when. And secondly, so you assume your climate was a little bit different, they were thinking. And secondly, it's give you different mapping of the landslides and your earthquakes activity in the area. Yeah, so this you're just removing all this database. Yeah. Only exception is possibility of floods and debris flow caused by breach of glacial lakes forming behind and moraine left by the degrading glaciers or being dammed by glacier surges and gradually moving rock glaciers. And that's very, very, very common problem right now in most of the Central Asia, all around Tibetan Plateau area. If, however, the opposite rock slide region of these features is true, then in contrast, no general restrictions of large-scale slope failures and river damming at any time in future exist, and related risks should be much higher. So you can even find that we have more of these catastrophic events happening because of the landsliding. It's not very much related to the climate change, so there's a risk constantly exist. Besides, it indicates absence of the significant glacial advances younger than these accumulations, otherwise the latter would not survive, retaining undisturbed shape and morphological peculiarities. Moreover, the correct interpretation of such prehistoric features in the mountain region play an important role in seismic hazard assessment. And that's what I say, if you don't have record, it didn't happen, basically. There's two maps, those landslide that I show you. The one bigger one, huge landslide here. And you can see it's hard to even figure out where's the deposits and where's just a slope. In this case, there'll be very, very important detail mapping and work in the field. So you go on every river, outcrop, trying to see the deposit material, walk on actual deposit, seeing if there's any boulders, study the lithology and this kind of stuff. Dating, you can date the rocks all around it and within the deposit, and you can kind of strictly see, for example, on some hills there'll be just younger rocks than all around it, so identification that it's probably rock avalanche material. And this terrace log slide on the south and south Ten Shrine as well, how would you identify it? It's enormous, catastrophical. I would do detail mapping, go in the field, study the outcrops and such. Moreover, the correct interpretation of such prehistorical features in mountain regions plays important role. We already read this. So there's a chapter about seismically induced rock slides and their discrimination. That's another thing you probably should do when you identify a new rock avalanche, because commonly people must be caused by earthquake if it have a deep-seated scar, big deep-seated landslide. Not necessary, and we know some big enormous landslide happen not triggered by the earthquake, and opposite, some earthquakes can cause a lot of smaller rock avalanches. Why do we need to identify it and time it with the seismicity? To understand the activity of the faults, and also to forecast. For example, you can forecast that your fault is active every couple hundred years. You have big event, magnitude 7+ or something, and for this you want to kind of suggest, and people do it, it's very common practice right now, suggest how many and how far and which probable landslide is going to occur in the area. While formation of moraines, rock glaciers and debris flows are climate-driven process, they have no or quite limited and indirect relation to seismicity. So that's one of the New Zealand researcher. He in 2005 kind of picking up the Alpine fault and landslides in the moraines and trying to see the correlation there. On the contrary, landslides, those in bedrock especially, are often triggered by large earthquakes. Yeah? Thus, if the seismic origin of past rock slides is proved, and their ages and recurrence intervals are determined, it allows estimating the probability of the occurrence of similar earthquakes in future and all the consequent hazard chains such as new large scale slope failures, formation of river damming blockages, and subsequent outburst floods. So that's basically what I told you. So now I'm going to look at some of the landslides. So general criteria of rock slide, rock avalanche identification. And usually what is the parts of the landslide you're looking at? So there's a great example. Just go bigger zoom. Good example of Ikeol rock slide. And headscarp, or kind of like a scar or source, usually we call it headscarp. It's the one you can see here, kind of like highlighting. This is like a source where there used to be rock sitting here, so it was some kind of type of slope here, maybe with some ridge. And then something happened, earthquake went up, and it collapsed. And then you can even see. So this is like a head scar, like bedrock exposed with some material on top that preserved. Here, more probably, it's all fall down because of the gravity. And then you see the material, so blockier, more carapace, and then more hammocky on the bottom, and you trying to identify how far it went. And here it's quite, you see there's a shadow here, there's a actually the lake, so there was a stream, and it's actually blocked it, and the landslide blocked it, so the water accumulated upstream. There's the bedrock here, and there's some other rocks, more probably bedrocks, and some more looser material. So you can try to identify, even just by the color or change of morphology, the shape, you can already say, oh, the deposit somewhere here. Yeah. I can actually show you this landslide. Let's read, and I will show you this landslide on the map. There's another one. You can see this kind of hammocky deposit and this supposed proposed headscar. So it's fall down from here, but 1.5 kilometer of the source. It's traveled down from 500 meters just till the deposit. Further down, it's obviously much deeper, and how far you see how far it goes. It's gonna fill the valley with the deposit. And most of the time, you see here, they're suggesting that we have some pre-existing glacier material, maybe rock glaciers or just glacier material. And the task of you as a geologist probably will be to, it's not very good resolution like that, it's to identify where the actual rock avalanche material will be glacial one. And that's why kind of like I will come and I say, okay, let's look at the deposits of the material, on the finds, on lithology, on the shape of the rocks, on the how they, the clusters and sorting, this kind of stuff. So you have to go into the field. So in many cases, identification of the prehistoric rock slides, rock avalanches, is a simple task and based just on the visual morphological analysis. But you can say it's not that easy. Combination of debris accumulation at the slope base and of the concave headscarp above it, whose volume corresponds well to the deposit's volume, allows an equivocal interpretation of the feature in question as a rock slide, as for example in the Ikeol rock slide case in Kyrgyzstan. That one. Sometimes, however, it's not so obvious, and additional evidence must be taken into consideration, identify site features. Quite often we can hardly reconstruct the pre-slide relief, and it looks as if the deposit volume is much larger than that of the source zone. And it's, it's quite common, but how can you kind of predict, unless you have images, satellite images of the scar before, slope before, it could be bigger than you imagine. It can be exemplified by the gigantic, about 400 million cubic meters, Aydin rock slide in the Chinese Tian Shan. So it's that one. You see, it's huge. Yeah, one of the biggest. Near the mountain with the same name, it's 1.5 kilometer wide and more than 600 meters high, rectangular headscarp on the slope, composed of the Ordovician granites, look much smaller than more than 3.5 kilometer long and up to 2.1 kilometer wide rock slide body, whose frontal part marked by glacier quaternary. So recent material. So here they're suggesting we found such a body, but it looks too big for this scar here. Although, as for me, I'm not sure. I don't think so. It's also the question is how thick the deposit. You can have kilometer, 500 meters thickness. We can have sometimes the rock avalanches, especially if it's a big drop, they start behave like a fluid, as I told you, and they can spread as thin as a couple 100 meters or 100 meters. So it's composed of the quaternary, likely glacial deposits bulldozed by the moving rockslide debris during the emplacement. This size discrepancy, however, is erroneous. So you have error. In this case, slope failure had affected the convex rocky spur that had extended for more than 250 meters off the main ridge, though its original shape cannot be reconstructed precisely. Additional criteria, such as the presence of large angular boulders on top of the main part of the deposit and the sharp boundary between the main blocky and the frontal, which one was smooth surface parts of the deposits, also indicate the rock slide origin of the features. So you're kind of looking, as I told you already, on the boulders. You can even date them, identify lithology, how angular they are. If it was a glacial something material, in this type of environment, it's probably wasn't being much rounded. But if you were looking somewhere down the valley or long-term carried, like I looked in Pamir, so on the Lenin rock avalanche, there was very, very, very dramatic difference between boulders there and there. First of all, different lithology. Secondly, the boulders in rocks brought by the glacier was much more subangular, not that sharp. Absence of this simultaneous fresh cirque-like scarp in the vicinity at the same altitude level exclude its alternative glacier region. As we mentioned above, some older Pleistocene, so we're talking about up to 2.5 million years, rock slides could not be identified just morphologically, since both the head scarps and the deposits have been so strongly reworked by erosion that none of them could be identified vocally on the remote sensing data and even in the field just visually. However, a careful analysis of the deposit's composition and internal structure, as well as of the relationship with other geomorphological features, helps to make sound conclusion on their origin. Such analysis allows to identify several large-scale Pleistocene rock slope failures which are not evident from the purely geomorphic analysis. And we're going to go through Kokomeran River one in a minute, but I'll just show you these two. Where are they? So Aikokyo and Aiden Ula rock slides, and also these two. I'll just show you on the Google because they impressive to look. Just need to go into my names with the so that one we just looked, Bishkjol and Ters, I would say. Something wrong with my Google Earth. It doesn't want to. It should be there south of. It's here. For some reason he goes in the wrong wrong position. So that's the landslide, which also provided in the book. But it's pretty hard to figure out what is what. I'm not sure I have a correct coordinate on that one. Probably should check it out. And the next one we have Aikokyo. Yeah, and this one's all the mapped identify in this book, basically by Alexander Strom landslide. There's numerous of them. You can see they kind of like tend to be somehow organized. Aikokyo, that's the one, and if I turn off the view, you can see the lake that it's formed as well, and there's another unwasted process here. You can see more material. And that one is very nice and kind of good to identify. Good for beginners, I would say. So you have a nice scar and it's fall down, and you have some you can see through the deposit some coarser stuff, very hummocky. You can see it's like a loose type of material. And this is already scree kind of material, just the scar is creeping through. There's a vegetation on top. Yeah, that's the actual scar. And there could be some of the material on top just keep falling down since, you know, emplacement or during. And then you have this damming and formation of this lake. Some local, some streams being dammed, and you see this topography here. This is what we talked when we talk about morphology. And this stuff already been kind of re-exposed since the material was deposited. Some of it started vegetated. And actually vegetation, quite good identification, because I told you if you have catastrophic rock avalanche and you will create a lot of pulverized crushed material, kind of a lot of fine stuff, and vegetation like this kind of material. So they kind of firstly will occupy it. Another thing is you have a slope with the screes, which is constantly moving gradually. It's harder for vegetation to occupy, but you have rock avalanche material and be sitting there, and already after first several years it start being occupied by vegetation. Yeah, so that's the good one. Another one I have, which they talk about in the book, it's this IDIN. It's why my Google Earth, it's so doesn't listen to me today all day. Where are we? If I couldn't find it, I will just give up because I don't want you to look through. Yeah, sometimes it doesn't show me for no reason. It should be in China. Yeah. So in China we have this several here mentioned, and there's like a cluster, Sarmi and Ula Ridge. So there's a cluster of these rock avalanches. Will be mentioned in the future. A couple of them we'll have a look. And this Idin one, it's here. It's quite big. I will just remove the. It's just a mapped scar, and if I remove it, you can see. Dun, 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 you can kind of see how it's different just by morphology from the surrounding slopes. Yeah. And the moment you're in the field, usually it's much more straightforward, believe me. So if you look on the topo, so that's the you see the scar here, and that's the one that the some of the older glacier potentially here, some of the older glacier material here, and that's this scar. See quite a good drop. You can see this material. You see it's been gonna spell here, went further down. It's behave like you spill something viscous over the topography. You see some of the material here, but is this the rock avalanche deposit material, or it's some older glacier stuff? Or maybe there's some new material come from here. So that's, you have to go in the field more probably, and you see some images okay, but some images not so good. Probably you need to get some better resolution than just Google Earth. Just for general understanding, it's pretty good. Which else we've seen? Yeah, this one, the tears, which I show you, it's not very straightforward, so it's very hard to identify. So that's that one we've seen, Aikol and Aydin Ula. All right, so let's look on the Kokomeran River. Kokomeran River located in, oh, I think I didn't switch, did I? Yeah, sorry, I didn't switch for the book. So Kokomeran River located kind of central of Kyrgyzstan, and there's there's a canyon, they call it, what is it, Chayak and Aral cities, villages, cities, I could say, and you have this like canyon going through, and it's so beautiful, so dramatic landscape, and you have numerous landslides. You see all the kind of identified ones that confirmed, identified, studied, saved landslide, and they're all kind of mapped here. You can see in different colors. Yeah. So I'll remove it, and then we'll look on the actual landscape. For example, here, yeah, you see the deposit. How different it's from surroundings. It's just like an example for you. of this Kokomoran River Valley. Very beautiful area, very, very beautiful. Alright, so don't forget to switch my book. Now I'm in the book. One of them is this Landslides Kokomoran River Valley, about 6 kilometers upstream on the Drumgal Intermountain Depression. It was named the Displaced Peneplain Rockslide. I called Kokomoran landslide. Since its headscarp has affected the exhumed pre-Neogene plantation surface, this one's beautiful, amazing one. This rockslide, about 400 million cubic meters in volume, originated on the 500 meters high slope composed of the Precambrian gneiss with schist interbedded and some mafic dikes that differ from the bedrock lithology of the depositional area. So that's very good, like it's straightforward. By lithology you can identify it. It had blocked the Kokomoran River Valley, so that the river had to erode a new bypass valley through the left bank granite. Afterwards, the entire area was reworked by the erosion so significantly that now both the source zone and the deposits can be hard to identify on space and aerial images and even in the field. So it's this picture. So that's the picture, kind of like scar identifying the red dots and the deposit being mapped. And the river, you can see the blue arrows show you approximately where it used to be, all stream. And we can find by the river deposit within the deposit, and you can figure out, and then new deposit on top and reworked material. So there's a lot of this detective work, as I always repeat you, happens. And I'll show you, just show you where it is. If we bring back our images, displaced peneplain. So it's this deposit here, and that's where usually go on the river, and that's the new passage, and all this material kind of been reworked by slow processes, brought down. You see this, how the river was kind of inside through till she find the modern day way. And so supposedly we can see the older river stream going through, and you can see here they have a power lines going through modern. And I remember we went there with Sasha, and he showed where the you can see the older stream. So it's pretty old, supposedly landslide. I don't think we have still dates for that one, so it's a good study project for any potential PhDs students or whatever. Yeah, and supposedly that's the scar when it came from, and some of the material could be right now traced, but because it's been there for so long time, you see the material being kind of moved, reworked. There's some good exposures you can see on both sides. It's one of those examples when you have to do a lot of work, detective work, to identify the landslide. Imagine when this happened, there probably was some kind of blocking and then breaching of maybe lake eventually. I have a couple images of people who just been there. I forgot to switch, so I'll show you again. So that's the river Kokomoran. That's the displaced peneplain. So the one in the book. And there's another landslide here you can see mapped, and that's the scar as shown in the book, and the deposit, and you can see the new stream. Yeah, I'm just showing you one more time again because I didn't switch. And the older river deposit was somewhere on this side. That's what identified by the arrows, and this power lines that I talked about. You see the power lines going through, and this is the material that been brought, and kind of reworking of older deposit. This you can see the river was trying to find a way. You can see this like a river, older channels preserved here, new exposures. Very dramatic. And the opposite side is enormously beautiful. So if I show you, don't forget to switch. If I show you the picture, yeah, so that's how it looked like, this power line, you see, which I talked about, and you can see these different layers of the river stream. So that's the modern river level table, and you can see this, some material was brought here by the river. So the river was first flowing through here and then incised through the bedrock. Very interesting. And this opposite side, it's beautiful scree here, and the color, you can see the color of the bedrock here is amazing. You see the screes, some vegetation trying to, numerous rockfalls probably happens. Very interesting, dramatic landscape. So let's come back to the book. Have a closer look on the deposits composed of crushed gneiss and stripped of crushed schist and mafic rock, with some evidence of the inverse grading typical of rockslide rock avalanche deposit that will be described in detail in chapter 11, allows sound conclusion that the deposit that form hilly area at the foot of high rocky slopes are allogenic. It is supported by the presence of the abundant river valleys on the present-day right bank of the Cocomarin River Valley, whose entrance, filled by coarse, well-rounded granite boulders, stream alluvium, can be seen above the road just upstream of the Pleistocene blockage, figure 4.6. And it's the panoramic view of the displaced peneplain rock slide. That's this river. Abundant river valley with stream alluvium, AQ. Here, that's what I show you, blocked by the rock slide. The small dark blue arrow on the inset indicates the position of the present-day Cocomarin River Valley. I'm not sure if I can see. Oh, yeah, there. There. And that's the current stream here. So it's just one of the example, very kind of classical, interesting example. Another site where identified the large Pleistocene rock slide was based on the detailed sedimentological analysis of the deposits is located in the southern Kyrgyzstan Tar River Valley, close to the Tereksu village that give the name of the Tereksu rock slide. Here, smooth hills covered by the well-cemented coarse limestone breccia affected by karst processes could be traced at the distance of about 3 km on the river's right bank, locally outcropping in the rock cut. Image 4.7. Headscarf, see, that's where it's come from. The deposit, rock slide deposit. Give you elevation for understanding the drop. And pseudo-stratified rock slide deposits with heavily crushed red sandstone and siltstone and whitish marl overlaid by coarse, well-cemented limestone breccia. This succession rests on the alluvial gravels, these ones. Position of the outcrop shown B and mark A by the white arrow. So that's what you're looking at. It's here. Let's just continue. The rest on the 50-70 meter high terrace. Such classification of the carbonate-rich rock slide deposit was described also for the alpine rock slide in Sanders. The rich, because, watch my Castle Hill, carbon-rich, they tend to do this nice kind of cementation lissification, but also they prone for karst within, because with constant rainfall they trying to wash out material faster than granites and other type of deposit. This ridge at the opposite side of the valley, rising above the riverbed, about 2 kilometers, picture 4.8. And you see that's another thing that I told you about. The deposits tend to climb on the opposite slope. It's you will see this with I've seen this in Acheron rock avalanche in New Zealand, in some Alps. So it's quite common thing happen with the landslides. And on the glacier, the landslide that fall down over the glaciers, they usually climb. They climb on the lateral moraines. They climb on the opposite slopes quite often. So it's composed of carboniferous sedimentary rock, mainly limestone, trusted over the Cretaceous red beds. All right. So let's have a look. The same succession of the crushed rock, sometimes pulverized up to powder, forms the deposits in question. The characteristic peculiarities are the preservation of the lithological succession typical of the source zone in the comminuted debris and inverse grading. Both are typical for landslides and rock avalanches. Since no evidence of the stream damming was found out, it's most likely that slope failure had occurred long ago before the incision of the canyon-like lowermost part of the river valley. It's another thing, we usually use the streams, the rivers, to help us to reconstruct the timing, what's happened with the event. The source area also underwent strong reworking so that the headscarp could be hardly identified. Nevertheless, the presence of large ancient rock slide at this part of the Tar River Valley has been proved with confidence. This case study demonstrates the possibility to identify large-scale catastrophic bedrock landslides with poor geomorphic expressiveness. So it's not that obvious in the field, that's what I'm trying to say. We should point out that both of them were identified first during the field study of the deposits, and only later the entire feature, headscarp and rock slide body, have been delineated and mapped. Moreover, the first description of the feature that was identified later at the displaced peneplain rock slide was incomplete, and its headscarp was placed erroneously, by mistake, in the upper reaches of deep dry gully that passes from southwest along the foot of its real headscarp. Only further field studies allow correct identification and delineation of the entire feature visible on figure 4.5. So you see, often even our author first identified it, and now they re-identified it as saying this headscarf must be here. And it's common, it's normal to, you have more data, more experience often, a comparison, or you go in the field. Other time, I had this when I had one study site, and I really couldn't put my head around what's happened there, but one moment you just see how it's happened and you see the evidence. And often it helps you to go to other sites, and then you come back to that site, you puzzle with, and it gives you an idea. Alright, revealing such features raise a question on the completeness of the Central Asia rock slide inventory. And that's all, what is it all about, we don't, if we don't identify it or don't see it, doesn't mean it didn't happen. Or if we recorded it as happened, it's a glacial material, so it's first of all give you a wrong glacial story in the valley, and plus it's removed all the seismic or rock avalanche record. Most features described in our book were identified from the satellite image analysis, and only for some regions they have been checked by our own field studies or by comparison with published and unpublished data collected by other researchers. Besides enormous interpretation of debris accumulations, which we'll discuss in the following section of this chapter, it's important just not to miss the features requiring a more thorough analysis. It is obvious that more recent Holocene, so last 20, and latest Pleistocene, last several 100,000 years, rock slides with better preserved deposits are more impressive and could be identified and interpreted with more confidence. Older Pleistocene features that theoretically must be more multitudinally, considering the longevity of the Pleistocene in comparison with the Holocene epoch, are nevertheless much more rare. Presumably most of them were reworked through time so deeply that only careful field studies, both morphological and sedimentological, could help their identification. But it could be they've just been removed, all the evidence of them, you just see the scars, but you cannot understand, when, what's happened with this scar from. And the deposit's been already gone. Several case studies of such older feature identifying space images are presented hereafter, along with the reasons that allow us to consider them as old rock slides. And this one location, we talk about this Sarmin Ula Ridge, composed of Paleozoic granites, and here about 15 recent and 4 older rock slides, which were identified with a kind of small area, so the cluster, we could say the cluster of the deposits. And we'll talk about this later. And we focus on the suspicious geomorphic features and 2 landslides. So 46, 47 China, and the interpretation is rock slides. For the rock slides shown on this figure, so you can see here, hammock kind of present here in the valley, and then you have this kind of nicely incised slope. Concave cirque-sharp slope bounding the deeply dissected flat surface about 400 meters above the valley bottom. Consider it as the rockslide headscarp and its body surface correspondingly. The additional important argument in favor of such interpretation is the hummocky macro relief well preserved on the surface and typically a frontslide deposit. I do have it on my Google. And we again moving to China. So we have this cluster here. Yeah, that's what I show you. China 46, one of them. Yeah, I think it's that one. Yeah, that's in the image, and you can see this hummocks on top. Also, these interesting characteristical boulders, and of course, we do need to go in the field, and so we can identify. And I'm sure you could see somewhere outcropping. And there's since the deposition surface features and so on it. Very interesting that this kind of stuff we can see a lot on Mars surface. I do have interested in the Mars geology as well. Just talk about, speculate about. So give me a signal if you're interested in those. So you can see that deposit here. Yeah. So that's what been talked in a paper in a book about. Here. Such combination allows assumption that this feature represents strongly reworked old rock slide. Additional reason for such decision is the concentration of the few similar features within the same area where much more recent rock slides form a cluster. That's another thing. So if you're more likely you have some triggering phenomena, most likely large earthquake. If you have a lot of features around, many rock slides, so if you have one questionable, more probably it will be. Similar peculiarities are typical in China 47 case study. The body is not as thick as in previous cases. Only you see a couple 100 meters, 300 meters, that's what I told you, but it's wider with large smooth hummock on it. Could be the reason they travel over something, or depends on the condition, it was a rainfall that time, or snow present, or if it's triggered by large earthquake. The presence of rather large, more than 3.5 million cubic meters recent landslides, and the material visible in scarp show that this body is composed of strongly comminuted debris. This old Pleistocene rock slide had dammed the river, and remnants of its body can be recognized in left bank just downstream from the landslide. Is it that one? 47. No, it's not. Figure 410b. Yeah, that one you see. The B. Here. This is the Google Earth image, so you can yourself go and explore. A, recent rock avalanche here. B, recent landslide in the rock slide deposit. So that's identified as a rock slide deposit, and we have recent landslide in this older rock slide deposit. If you understand what I mean, hopefully you do. Another set of evidence in favor of landslide origin of the cirque-shaped lowering on the slope was used when analyzing the giant deeply eroded conical-shaped body, about 200 million cubic in volume, at the foot of the 1.6 kilometer long cirque-like bite at the 1.2 kilometer high left slope of the Ashu River in the northernmost chain of the Chinese Tian Shan. And it's China 95, figure 111, that one. I will go to Google this time because I think it's not a very good photograph resolution. I just need to see. Jumping between the landslides could be tricky. No. I think it will be that one. I don't think I put a number on it. And you can imagine this is just a touch of the surface of all the landslide available in the area. So that's 146. The 147 is here. I think talked about that one too. And you see there's a nicely mapped, if I remove you can see the deposit mapped nicely here too. That's the one that we just looked at, the scar. And you can see how the deposit is sitting here. The moment you're being pointed to the landslide, you're kind of like, oh yeah, that's so obvious. But the question is it actual deposit? Is it not the glacier material with the source, with the scar? And sometimes there's a 2, 3, you see these ones clusters together, and you could be kind of confused. I'm not sure I can see where that one is. 0.95, 44.2, 83.6. Pretty sure I didn't map it. Google Earth is very tricky today. Sometimes it doesn't. Yeah, it will be that one. 44.2, 83. Yeah. Okay. Yeah. So he lost it somehow. China 95. That one. I don't know why it doesn't, when I show him going to the location, it doesn't go to my location. A little bit tricky. Sometimes I do. Yeah, you can see here as well. And again, not this good image. And you can see the material and surface stuff happen since. You see the kind of canyon developing, river cutting through since. Probably more seasonal, depends on what's happened with the rains and snow melting in this area. I assume it's very dry. You see something preserved in the bottom, in the valley. But the landscape is amazing. You can see even here, like 2 images. We have snow in the snow season, and this image probably done, doesn't say date. Oh yeah, it does. 10/25/2023. So for that one. So it's October. So it's like the minimum snow cover, which I will assume is correct. Let's come back to book. That's image. Finishing the description of the general criteria of past rock slide identification, we want to describe the case study where the conclusion on the origin of the suspicious features was made by contradiction, based on the impossibility to explain its origin by the alternative natural phenomena. So sometimes you can go in opposite direction. So it's not that, so it must be in the landslide. As I told you, your work as a detective. Strange 50-meter high debris accumulation composed of angular granite boulders was found at the bottom of deep, dry, wedge-like gully on this image. Yeah, so it's a Sate rock avalanche, which here there's a scar and the body. You can see nicely sitting like a tongue of the deposit. And you have this material, and is it related to that or not, or there's something different? So what they did as a detective, they concluded, it's in the upper reaches of Cocomera River Valley, I'll show you in the map, adjusting to the extremely impressive late Holocene Sate rock avalanche, that one, yeah? Sate. And it's very typical one, beautiful one that Alexander Strom takes school there, so you go there. You walk on the boulders, you walk on the body. You can run till this source, but it's a little bit too far. The entire area is composed of Paleozoic granite and granodiorite, different in strength and erosion resistance. Same angular bouldering material composed the fan-shaped surface below at the deposits of 2.140 meter sea level, overlaying the granite spur marked by PZ on figure 412. Here, you can see this like a spur, kind of like a bedrocky spur. These deposits are located too low to be classified as moraine. At the same time, the gully catchment below the summit of 2.890 meters sea level is too small to produce the debris flows powerful enough to displace blocks of granite, some of which are more than 1 meter in size. Closer view, this is the closer view of this Presate rockslide deposit. So there's a huge boulders. It's a very, you see, kind of contact with the slopes, very unusual. Some event, probably older, and it's here as well. You can see it clearly. It's so lucky there's not much vegetation in the area. You can see the morphological features. Moreover, this bouldery hill does not look as the fan-shaped debris floor or snow avalanche deposit, which, common as well. Impossibility to explain its origin by the ice or water-driven process force us to consider rockslide origin as the most logical and consistent explanation. Such explanation contradicts neither with the wedge-like shape of the assumed source zone, nor with the size and shape of large angular boulders forming the deposit. So you look at the source, you look at the deposit itself. Its closeness to the incontestably identified Sate rock avalanche is in line with the commonly observed phenomena of the spatial clustering mentioned above for Rockslides at the southern slope of the Sarmin Ula Ridge. This cluster in the Chinese. Thus, the conclusion that the feature in question is the remnant of the very old Presate rock slide that has been reworked for millennia sounds reasonable and well-grounded. We did not follow, that's the last paragraph. We did not follow the approach used by researchers from the United States and Pakistan who compiled the landslide inventory for the area just south of the region in question in northern Pakistan, drained by the Indus River and its large tributary, the Hunza River, based just on slope topography. So you see the map those ones in those areas, Hunza and Indus, just by morphological topography. Each feature included in our database was identified on space or aerial images based on the combination of the geomorphic geological evidence. Geomorphic is, all these shapes, composition. Geological evidence, it's the type of rocks, all this angularity, all these descriptions I told you. In some cases proven by field investigation. So that's the first part of this chapter, and I think I have to probably finishing up now because it's been an hour. And we will, I will add some better images of some maybe case studies from this book which we talked about. The only thing I want to show you right now it's this Sate rock avalanche, the last one. And again, we're coming back to the central Kokomeran River Basin, central Kyrgyzstan, Sate and Kyrgy 241. So that's the Sate, and you see nice, beautiful, kind of more classical scar, and the body mapped here with the pink color. And you have this potential scar somewhere here, and this deposit which was in question. The position of it make it kind of like impossible that it's here, it's come from here, and there's no evidence of connection. And I will turn off, first of all, switch for my Googlers. I will show you. So we back to the central Kyrgyzstan, Kokomeran River, and it's here. Indicated in pink, and this potential which Sasha talked about. And if I move around 3D kinda doesn't like it. Yeah, that's the river. There's some images which it will not allow me to show. And you have this classical beautiful Sate with a beautiful carapace on top, rock avalanche. You can see it's even from the Google imagery, yeah? How it's traveled down and deposited its tongue. We call it the end termi of the deposit here. Vegetation, as I told you, big boulders, crushed material, clear contact. When you walk on it, there's a big boulder, so typical, like you walk on any other landslide deposits. This actually was one of the deposits that helped me identify some deposits on the glaciers that become part of the moraines in New Zealand. Very clear example. You can see that's all the rocks, huge boulders, even if we measure some of them. We'll talk about carapace, and this is a very good example. Look, that boulder is, I want to be in meters, over 10 meters in size. And then you can see the very clear age. So there's no possibility. There's all the material, bedrock, river stuff. There's a road. So this material, which is supposedly second older rock avalanche, mapped, been identified. It's more smooth, removed, but there's some boulders here, and we cannot explain it with any other slope processes. See some damming here, local happened probably because of this event. So there's like a little lake was formed. You can see by the kind of swampy vegetation. So it's quite, the moment you start working with these things, you can find it, identify. Ooh, I'm getting too close to it. Let's fly out. Fly away. Beautiful, beautiful landslides. And if you see about the clustering, that area one more time, I will emphasize how many confirmed, mapped, date, researched landslides all around. It could be that some of them triggered by the one event, earthquake. Could be not. All right, thank you so much for joining me, and I hope you do like this type of videos, and I will see you in my next live stream. And please share my videos, like it. I do want to make something from this channel. Thank you very much. And we're live, and we're checking the sound. So welcome to the live stream, and we continue our reading and discussion of the book Landslides in Central Asia. And I just took some time to set up my sound and everything going. Chat is here. So please write me comments, questions while we go, because it is live, so I'm just sitting and talking. In this part, we continue to go through the book, and we will specifically look at the rock avalanches versus moraine, how to identify landslide material, rock avalanches, rock slides material from already pre-existing moraines. Moraines, it's the material they've been brought by glaciers and dumped there before. So often they have kind of geomorphologically similar features. You can find them in similar location in the valleys, narrow valleys, of course, and those mountain valleys being glaciated or still glaciated. So it's very common misconception to identify one instead of the other. And why it's important, we will read through the book, and how to do it as well. That's the good question. And we also will look at some case studies I have here on my Google Earth. Today, mostly there will be examples around Tajikistan in Pamirs. And last, we'll just go through the book and see what the authors tell us about this. And it's a more important and personal for me part, because my research focus on that, how to identify rock avalanche material from the moraines or any other glacial material, and how to identify also rock avalanches on the glaciers, and what's the importance and part of these events happened, how it's important today, how it's rock avalanches affecting the glacier which still exist in the valleys, how they did affecting them in the past, and how it's affected the deposits of these glaciers or behavior of these glaciers, and what the connotation for the climate change or studies of past climates. So if we understand how glaciers behaved We can reconstruct the climate from that, and opposite, if we know the climate in the past, we can reconstruct how glaciers behave. So it's all interconnected and related and important, because there's a big discussion, and as important as we talked in previous chapters to study rock avalanche materials, it's similarly important, or no less important, to study glacier and glacier deposits. And there's a kind of clash of titans, which one's more important. And when we attributed one geomorphology feature for one event, we kind of diminished the other one from the record. So that's what we're trying to here, understand sequence of true events in the valley. And it's very attributed to modern day. There's so many case studies today when the rock avalanches fallen down on the glacial deposits, destroy them, remobilize them. And you can imagine, even if you move your glacial deposit several meters, 100 meters down the valley or up the valley, whatever, it will change your modeling and understanding of the climate, because glacier deposits very much depends where the glacier was at the time. You date this deposit and you understand when the last time glacier was sitting here, and from that you understand what was the snow line, where the glacier balance was in that area. From here you assume your climate in the past, or change in the climate here. And if you have some disturbance because of seismicity, rock avalanches, it can change your figures, numbers, your data. So you need to remember that when you go to the very active landscape like Central Asia or Andes, Alaska, European Alps, New Zealand Alps, Southern Alps. So it's very important to understand that there's other things happen, and we're still on the blink of understanding which more important in moving material there, the glaciers, rock avalanches, normal erosion, or rivers, so it's all very interesting and important subject to study, which people do study these things, and there's a lot of debate, but it's not as well studied as it should be, and there's a lot of kind of one-sided studies happening, so there's a lot of potential. So rock avalanches versus moraines, there's one chapter 4.2 in this book, which I remind you, we're going through a book, Rockslides and Rock Avalanches of Central Asia, distribution, morphology, and internal structure. So we look through live streams. So I have live streams and I kind of republishing them, editing my pictures, all the other chapters. So we've been through general information, overview study area, a brief history of bedrock landslide studies in Central Asia, who, when, and why I study this. Overview of study regions, so we went through everything: tectonics, geomorphology, seismicity, climate, glaciation, hydrology. And now we're looking at the principal criteria, CA principles and criteria, how to identify these deposits. Because you cannot tell how many landslides, how important they are, how frequent they are, unless you study, unless they're in the valley. So we have to correctly identify this. So it's chapter 4.2, rock avalanches versus moraine, and we just briefly go there and go through. Yeah, that's the little rock avalanches on the modern glaciers. We will look in that next video. So I have some videos about glaciers. I have some videos specifically talking about my work about rock avalanches on the glaciers, very old videos. You can come back and see it on my page. I probably will add some link for those videos. Here, I don't know how much time, probably 1 hour, hour and a half, and we have a lot of examples, so we're going to try to kind of go briefly through. So the first, what the authors say, it's has been mentioned, rock slides and rock avalanches are often misinterpreted as moraines, and opposite mistake are possible as well. So rock avalanches could be identified, and it's in fact the moraine. I personally find more cases when it's opposite, rock avalanches misinterpreted as moraines. I don't know that many rock avalanches, moraines have been identified as rock avalanches, because usually people who study rock avalanches, they have an eye, they very see the rock avalanches. They can identify it by morphology, find scar. They see it by how it sits in the valley, relation to any other deposits, and also by sediment. So usually it's trickier if you don't study rock slides and you study glacier deposits, and you could be confused, because rock avalanches, as you will see today, they have these features like hummocks and kind of like a floating features, like you can see in this image, which could be attributed to the glacier material. So unless you go and dig through and look through the deposit and map it and find the scar, you probably will not identify it. So in my experience, more commonly, people who study glaciers confuse rock avalanches as a glacier deposit, and I think it's from just because they don't have experience on rock avalanches. So if you are very keen to identify glacier deposits in the valleys and date them, don't believe just to the geological maps, because we mentioned further, and we already mentioned it before, that in the past, because it was all remote and people didn't have sophisticated satellite images in the past, like 60s, 70s or whatever, people didn't have abilities to go to every deposit. We didn't have such a database and examples described in the literature. You cannot access the literature as fast, in the past. These days online, you can just put keywords and they give you all the articles available for that. So in the past, especially like when people were doing like Soviet Union big program, or Chinese whatever government was doing geological mapping, they were just kind of like more or less, this all look like a hummocky stuff. Same in New Zealand, although you would think New Zealand quite small, and many valleys quite detailed studies. But I found that whatever it was something global program, there's much more mistakes when it was some individual researchers who go to the specific valleys, and they have specific papers about specific moraines or deposits, which they suggest or argue there might be rock avalanches, and that's what we kind of use as a stepping stones, and from that you can go and see if they're right or not. And they might have crazy ideas, but actually they might identify it as unusual glacier deposit or moraines, but more probably if it's something like everybody going there and creating some geological map for whole country, it's usually much more these words come out of my mind, not approximation, but like a simplification, I would say. All right, so let's see. So numerous debris accumulation left by rock slides that are considered now as classical case studies has been interpreted initially as being left by glaciers. It was for the Alps prior to Albert Heim investigations in late 19th century, in Karakoram before interpretation of numerous river valley blockages made by Kenneth Hewitt, and he also described he has a lot of work done in Karakoram. And I use it a lot for my research to study his case studies, Baltar glaciers and others in the very dangerous remote areas and highest peak on our planet. And there's amazing glaciers, surging glaciers, and he did a lot of studies of looking not just for the old deposits, but also modern rock avalanches on modern glaciers. In Southern Alps, of course, New Zealand. Rock avalanche deposits were misinterpreted as moraines in study regions as well, many study regions. So we'll talk about this later. There was a long story of back and forth interpretation of the Common and the Achiktash Hamaki fields in the Ale Valley. And again, we'll talk about this chapter number 9. And I have a specific video, it's called Hamaki Moraine, Achiktash video, and I talked about that. They were interpreted first as glacial deposits in 1930 by Korzeniecki, and I actually have a book, original book of glaciation description. It's kind of my Pamir's Bible, and I'm thinking to go through this book and just like show it what is in this book. It's old Soviet book, which is very dear for me. I find it from some bookists in Russia, and I studied well because I went there and I was trying to understand what Korzeniecki saw and described, and what I do see in the valley. So please comment if you're really interested in this, and I can do some kind of cool review of all book. And then rock avalanche had been identified by Kurdikov in 50s, 60s as a rock avalanche, and again as a moraine more recent time. And recently we did sophisticated research, and I can for sure tell me that there's in the glacial deposit all the ones, and on top of that we have big common rock avalanche, which attributed, I think, the second biggest in the world by the Ranout, that travel more than 30 kilometers, common rock avalanche. And also I found the Lenin rock avalanche. So there's a rock avalanche sitting on top of the huge, vast, hammocky Lenin glacier deposits, which I don't know the age for. It's approximately 8,000 or older, those deposits, but we did collected some boulders, actually a lot of boulders for dating, but we never end up finding funding to date them. Same enormous interpretation was for the long run out Chartash rock avalanche, and for rock avalanches that collapse from the back wall of the gigantic Peshkol rock slide. See figure 4.1. We looked at this in a previous live stream. The southern feet of the western Akcheryak range, they were mapped as glacial deposits on the state geological map compiled by the Geological Service Soviet Union, 60s, 70s. Yeah, that's what Alexander Strong keep referring to, and I used as well the same map when I went to the structural geology is amazingly mapped there, and very correct, at least in the valley where I've been. So it's very cool mapping, but with the quaternity deposit, it's arguable. Even still, people there on the planet who don't believe that it's rock avalanche. Recently, the problem was raised again for the Central Asian region and publication of Nikolai Ishuk, who considers majority of natural barriers in river valleys, including well-known features such as existing dam of Yashel Kul, and I'll show you Shiva, Iskander Kul, Alex bridged Kudara Pasor blockage, as well I'll show you, as being formed partially or completely by end moraines. So I do have them on my Google, and we're gonna go through them because in the book we're gonna go through Kudara, we're gonna look on the Yashkul, Langar, Imom, rock avalanche in River Kut, and also Shiva. Where's the Shiva? Shiva Lake, yeah, here. So there's these things, well described and argued, for and against. Let's come back to the book. However, several reasons do not allow Green with his interpreting of most of these valley barriers, either by end moraines or in combination of end moraines as the main river damming feature, accompanied by subordinate rock slope failures. So most of them, basically the lakes, there's the lakes were formed, and similar, like I talked about Sarias rock avalanche, which happened historically on our, we basically watched it through in 1911, or as I remember, and there was an earthquake, it's happened, it's fall down, and we see how the lake filled up within 20 years or so. So these things happen all the time. I told you in the very, very first video about this, especially around the Pamir. It's a very, very common case. One of the main arguments in favor of the moraine origin of natural barriers is the presence of large amount of moraine material, rounded, semi-round boulders in sandy salty matrix. So we call it glacial till, classically T-I-L-L is correctly spelled. And this is the material which, sub-rounded, rounded, so the material kind of brought from the slopes, and mostly it's been bulldozed by the glacier that's traveling through the valley. If it's a big valley, like, in Pamir, you can travel several more kilometers, and there's always will be water present because the glacier constantly, in the melting season, a lot of water coming through, percolates through. You probably, if you ever been on the glaciers, even in Pamirs or somewhere else, in Alps, you can constantly hear, even not see, but hear the water somewhere, going somewhere. And if you watch numerous videos, people start publishing when they walk on the glaciers these days, there's a lot of crevices, like there's cracks of ice, and it's very dangerous. There's little ponds, big ponds. And some of these caves, if you fall through, you might go through hundreds of meters of fall and into the under the ice and never find your way out. So it's very dangerous. At the same time, that tells you about, you know, how the material falling through from the surface, from sides, from in the middle, and of course kind of bulldozed by the glacier from the bottom, and it's all froze, defrost all the time and grind over each other. And the rocks which carried in the ice, usually through kind of like sharp movements of the sometimes a glacier, it's not always just slowly kind of moving, you know, if you can imagine it like a train. It's have this kind of little movement, so it's moved a little bit sharp several meters and then it stops for some time, even froze to the bottom. So it's quite dynamic, but not as simple as you can imagine. So the whatever rocks there in the glacier, they will constantly moved and how to say, kind of modified by the water, and also they will grind towards each other, rocks, or the glacier will actually grind it against the bottom. It's kind of classical glacial sedimentology described. So you will see it in the deposit finally, which come all the way down through kilometers through the valley towards the end, but not necessary. And there's glaciers which have a lot of kind of rock falls falling down the surface, and they passively move down. And especially like what Hewitt described in Karakoram, there's a very active, there's a lot of rock slopes. So you have this involvement of this kind of sharper material, and that's why for the many glaciologists it's very confusing when they go there and they see this carapace of very angular boulders on surface, and then kind of more rounded stuff underneath. That's what Sasha here say. They'll be like, oh, it's typical glacial, but not necessary. So here was saying, however, this observation can be explained in different way consistent with the rockslide origin of the features in question. Most of the Pamir River valleys are some rivers in the Tian Shan and Jungaria have been intensively glaciated in the past. These glaciations left the material from the lateral and bottom moraines that cover lower parts of the slope. So you'll find some remnants, not that much, but remnants of these moraines. Usually moraines kind of preserve more on a kind of higher slope if the glacier melted drastically and it's left these lateral moraines. They're kind of very subangular. Or these end moraines which didn't have been destroyed by the river, and usually they're kind of less preserved in the narrow valleys. And if you have wide opening or wider valley, like for example, like I have in my Ale Valley, there's a big opening, you know, of the foot of this steep rising mountains. These deposits kind of have more chances to preserve because the rivers will surely destroy a lot, but not everything. But if you go like a valley in the modern glaciers, for example, New Zealand, West Coast, there is hardly any even terminal moraines I observed like 20 years ago, they're gone now. They've been demolished by active fluvial processes. So besides thick debris fan come out from the tributary valleys with modern glaciers in the upper reaches. When large-scale slope failure occurs, moving bedrock material bulldozes these boulders in sandy mattress and often overrun and overlaid. So what they're trying to say in this paragraph, even if you see this rounded, sub-rounded, semi-rounded boulders in sandy, silty matrix with some angular stuff, it could be that the rock avalanche remobilized and moved and bulldozed or went over these deposits. Yeah. So let's go to the examples now. Can be well exemplified by the Imom rock slide in the Gant River Valley, about 15 million cubic meters in volume, resting on the 10-20 meter high left bank river terrace. And we have this picture of that one. So you can see very, very clearly this is something kind of alien material sitting on top. So this debris fan here coming from this tributary little valley. She was glaciated before, but now it's just a river. So there's a lot of, you see how many like veins cutting through. A lot of, I'll just zoom it a little bit more. A lot of material, we call debris fan material here. And they have a very typical classical profile, some sorting of this rock. So it's quite a common feature. It's easy to identify. And lithology will be strictly from this valley. And then you have these thing. And they described that this is moraine material, which was sitting, used to be somewhere here. And probably when this, you see the scar identified by the arrow, fall down from this slope, it's gonna remobilize this material, or even just went over it and created this landslide. So this EMO landslide, let's just read what they say in here, and then I'll show you in Google. It also overlays large late Holocene alluvial fan, that's one, Holocene alluvial fan, fed by debris flow from the steep gully with the small glacier and its upper reaches. There's a tiny little glacier there somewhere. And it's probably quite often this type of already glaciers, very tiny, could be the rock glaciers actually. Such relationship indicates very young age of the rock slide. So that's what I told you, kind of just superposition of these deposits can tell you that it's something younger. If this was true glacial stuff here, probably won't be this such sharply overrun this fan, because this fan probably material here will be younger than this material if we date it. So you have to come and date it and kind of piece by piece to reconstruct the events. Typical moraine material, rounded and semi-rounded boulders with sandy matrix. Sandy usually kind of, there will be some finer sands and some even clays, but that's how we describe it. Till composes the 300-meter wide belt at the front of this 1.4-kilometer long body, and from 50 to 100-meter wide stripes bounding it from both sides. This zone has different color and smoother surface than the inner part of the deposit, composed of crushed crystalline rocks exclusively that form the 700-meter high slope, from which is caved and have significantly different hummocky macro relief. Quite fresh escarp with a crown of 3.8 meters sea level, which is much lower than the present-day glacier cirques. And it's another thing, so if you find some scar of some source, which is kind of out of your average glacier cirques, because they for same date glacier cirques, present day glacier cirques, they will be in specific areas, because further down, lower down the valley, it's not enough cold temperature we have to create. If it's all the glacier cirques, which people argue, they won't be as fresh, yeah. So the material, the slope will be already vegetated, or kind of, the surface will be older. Yeah? So the level for Pamir right now, it's 4.5 meter, and that's what we saw in Ali Valley. Is unique for this section of the Gant River Valley and also contradict the glacial region of study feature. So let's have a look. So that's what this image, very nice. I really like this image of this deposit. So you can see this kind of, this is the debris fan here. You see how it's a lot of concurrent flows of the water coming through, and maybe some of these channels won't be occupied by water right now. Probably this photo was taken August or something, but end of the melting season, the driest time of the year. But after the winter, it could be that some of them channels actually there could be snow remobilization, but I would assume it's more in the melting season, kind of later spring, early summer. There'll be a lot of streams, more water, because the more snow will be still on the slopes and they'll be melting. And you can see here the fresh scar, see, to the left, and this thing fall down. And you see the difference between kind of older, round, big, and more smaller hummocky material on top. And it's the modern river, basically water base. Notice the difference, macro relief for the outer inner parts. Yeah. So you will look for morphology, but it's not enough. It's not enough. And here we're talking about crystalline rocks exclusively. So that's one of the important argument, and I talk about this in my Achiktash, how we looked on geology. So if you have one or just this scar, if you study the scar lithology, whatever come from here, estimated, and if it's one-to-one match it, and often the lithology will even match the rock in the rock avalanche sequences. So you can see how they say it could be like layer, like a cake, or it could be like a train, wagon by wagon, represent whatever you find in the slope. It will be very important argument, because if it's glacier material, it will represent all the rocks, all the lithology from whole catchment, so from slope to slope, everywhere further up. And you will find that the rocks, they're never like that, one lithology, second lithology, third lithology. They will be absolutely mixed. So because of exactly how the glacier behave. Yeah. So we look in lithology, angularity. Sometimes angularity can be confusing because, as I told you, you can have glaciers with a lot of stuff on top of them, kind of subangular, angular, and if you have same in rock avalanche, it's hard to distinguish. Another thing, it's the sorting you're going to look at. So you're going to study your deposit. And I will also look in the fines, and the very fine clay, nanometer, basically submicron particles, which I talked about in my previous video. Why? Because glacier, in a glacier, usually this finer material will be washed away by the water, most of it. If you have rock avalanche and it's fall down, and this part that preserve, so some part of the rock avalanche could be washed out and removed, and you don't have to worry about it, it's gone, become part of the landscape further down the river. But whatever preserved, and if you can find, you will find is kind of sealed within finer particles. They're not going to go anywhere. They're not going to percolate through because of the water. No way. All right, so similar phenomena. Let's have a look on the Google. So this one is Imom. So Imom, it's located in, where's my Google? Basically in the middle of Yoto. This is all the Tajikistan country, and it goes up here into the open valleys, and you have this Pamir, basically all the Tajikistan. Very lucky country, have such amazing geological feature as a part of them. National treasure, I would say. So Imom is located here. So this is a huge valley, and there's a lot of landslides. Here, this Gant River. It's the only ones that we recognize. And of course, you have the Sarias Lake. It will be here. That one that I talked about. So you can see it from the space. So it's used to be just river valley, same like a Gant. And we have landslide here. You can as well see it from the space. It's blocked it, and it's created in 20 years. This lake filled up. So dramatic. It's still danger. People still doing research if it's gonna breach. The water gonna push through, and it's all gonna go down the valley into the open land, down towards the open plains. It's a lot of water, so we don't want it happen. So Imom, and I found that these images, a lot of them that one's covered with the snow. You see, it's the 3/5. So I believe if it's American, so it's March 5th or 3rd of May. That's confusing for why they don't tell me for Google Earth. So I need to flip my mind around. If there was like 25th, it would be more obvious. Okay. Yeah. So the first is the date, then the month. Okay. So they have a good order. So this image, it's 24 May. So you see, in the May you still have snow. This is May. Hello. We should already have flowers and tulips blooming. No, you see, and you can see even in the slope. So there's a modern river flow here. There's actually the people living there. You see, there's houses. It's impressive. I can imagine live there. And we have this landslide. Look at that. So very sharp edge. How it sits. Just irrespectively, we have these hummocks. You see how the deposit fall down. This contact here, and the slopes and the potential source scars here, as suggested in the paper, and this kind of like hold the cirque they occupy the slope. And there's a probably lateral moraine here. So if I remove the snow, I'm just gonna go find all the picture. You can do it in Google Earth. So we have September 22, not so good. Next image will be 2019, not much. 2008, so 2008, I find the image better, especially one in it's 1985. All right, it's too far. 2008, yes, 2008 is good. I think that's what Sasha used in the book. So you can see the scar here. You can see it's fresh. You see, this is the original slope. So if there was the glacial, solidly glacial material, you will have this slope here everywhere. So this is a very modified modern. Even here you can argue, okay, but there's still rocks falling. But you see how they're falling gradually, creating those debris fans. Yeah. And look, there's a glacier. I can see it's probably, there's a material, more probably rock glacier. Here you see sitting on in this cirque. So this is the modern cirque position. So it's much, much lower elevation, of course. So here we're talking about 5.5 exactly what it says in the paper, and here it's 3.7, and there's no way there was a glacier here recently. So these deposits, and another thing, if you looked in a valley, how unusual is this? So if this was a glacial typical climate related deposit, we'll have it here and here and here. So we'll find it in every other catchment for this elevation. We don't have it. So if you see something unusual, out of place, as I told you, with for example with the lakes, if it's something unusual, out of place, it's the indication. Same with the rivers. If the river kind of here, not very big landslide, so it didn't affect the flow of the river, although maybe it did, we just don't see it. But if you see there's all the houses, people living here. But if you see, for example, the something very meandering, like, so the river is nice, and then boom, there's some kind of weird meander happened, then more probably some rock avalanche or something unusual happened. Yep. Yeah, look here. Boom, something happened here. So is a glacial material or not? You can see by these features the river trying to maybe cut through. That's the debris fans. Something unusual here. Boom. Maybe not. It could be because of the debris fan affecting. So if you just go through the valleys, you would see that boom here. Look, we're going to talk about this. Yashelku. Absolutely crazy what's happening here. Yeah, and the lake formed. Yep. And they're actually trying to regulate this lake now. Yeah, huge lake. So definitely there's this darker material. That's the one rock avalanche caused that. We'll come back to this case scenario. So that's our case scenario here, and suggested in the paper that the material was remobilized via glacial. Even if you find glacial material in your rock avalanche deposits, it's or sitting on top of it, or pushed against it, or overrun it. Similar phenomena was observed. Just come back to the paper. Similar phenomena was observed in Langar Rockslide that had blocked the same name river valley, Gunt River. Gunt or the Gunt? Probably Gunt. 3 kilometers upstream. 150 meter wide zone is composed of the glacier deposits bulldozed from the slope's foot. In both cases described above, the succession of the lithologies forming rockslides bodies retained the initial aura rock mass that originated from the upper part of the headscarp, pushed the material resting in its foot, so that all of them move like a series of train cars. That's exactly what we talked. You can see here, so 1 lithology, 2, 3, or could be lithologies, could be pre-existing material, for example, some moraines or something, and then they kind of pushed. So we've seen it on a diagram in the previous live stream. There's a rotational landslide or different type of landslide, how they move material. Yeah, sometimes they kind of overturn it, but you see sometimes it's happened like that. That material will be first. It kind of will be. They're going to be layering on top of each other, and it's probably will depends how higher this slope here. So if this number 3 was much higher, it's have more run out, more travel distance, so it's kind of will speed out more than other layers, and it will end up kind of traveling over these layers, and that's what they described here as well. However, quite often the material from the headscarp crown with higher unit potentially energy overruns and overlays the material from the headscarp lower part, forming the pseudo-stratified body. That's what we just seen. But yeah, I've seen those landslides in Central Asia, and we will come back to them, and of course we will describe them. But it's also it probably not just the geomorphological, predisposition. It could be also type of, if it's an earthquake, for example, how long the earth, these kind of things, or how loose the pre-broken, kind of how loose the material which traveled. So you kind of maybe take into account these things. Probably somebody studied this already and can tell you the reasons. But just remember, each and every landslide have very, very individual situation, and there could be so many odd cases. When such transformation occurs within moving log slides in which the moraine material from the slope base is involved, it looks as if coarse apron of angular bedrock boulders and debris overlays glacial deposits. So it's because you have this more higher broken material sitting on pre-existing glacier or glacier they've been further lower down the valley. Excuse me. Yeah, just such interpretation of valley blocking by end moraine and its subsequent overlapping by rock slide was proposed by Ishuk for the Yashikul blockage in the upper reaches of the Gunt River Valley in the central Pamir. Yashikul image, that one. So that's the big one that I just already show you. We find it ourselves. And you can see very straightforward darker material. You see this kind of lakes, ponds occur, and scar. So that's and even the arrows showing you material of the glacier material that pre-existing in the valley. And when we look on the images, it's very straightforward. So that's I think it is that landslide. No, maybe not. It's not that one, isn't it? I think I did find picture. Yeah, so that's one. You see this kind of boulder. This is so typical carapace of the rock avalanche material. There's if you find something like that sitting on a glacier, it will be a rock avalanche that fall down on a glacier and passively moved by the glacier, or the glacier was already stagnant and it's just glacier meltdown and it left it. And there's a ways to identify it from rock avalanche material. Yeah, you see here, you can see all the glacial stuff, glacial material. I hope you can see my, just check, you see my arrow. You see this hammocky thing, and it's kind of what I saw in Achiktash, Ale Valley. And then you have this bouldery carapace of rock avalanche material, uniform, same lithology. You see how it's distinct in younger color from, obviously, from the rest. You remember single source, maybe everything same lithology. And just by vegetation erosion, not much vegetation in this area, but just kind of like by whatever lichens and algae you can already see. And some people do, they go and they date them by using algae. I've seen people who does it in Norway, they're kind of testing it. But it's very complicated because you need to know for specific valley, specific algae, specific temperature fluctuation, and they kind of behave differently. So it's not universal. Same the Schmidt-hammer. Schmidt-hammer is this kind of tool that you kind of banging the wall, and people use it in construction, and they can tell you how strong or resistant the wall. So if it's something with a high hardness, granite, for example, you have nice wall, or if it's something loose, it will show you how kind of weaker it is. And people start using it in building construction or something, and then they end up using it in geology as a test. So if I kind of Schmidt-hammer hit one of those boulders here, and they show much less resistance, it's just, then statistically everywhere much higher resistance than on my glacier material, you will definitely know that this is older, this is younger, if you find the boulders of same lithology. So there's a lot of complications. And that's this, I found another picture. This is all courtesy of the Google Earth. And as you see, they are digging through this deposit. So you can see the rock avalanche, very typical rock avalanche kind of open work. And here probably kind of more subangular, you see stuff. You see this kind of rounded boulder. Another rounded. So it's stuff underneath, or probably they're digging into the older glacier material. So here you see they're doing it here, that's where they were digging. They're trying to build some kind of hydro plantation or something. I'm not sure. All right, so Yashilkul, and there's another image which show you displaced moraine material bounded the Yashikul rock slide debris at the right side. See, and note the distinct difference between slope base formed by the reworked old moraine and its part covered by the moraine material mobilized during rockslide motion. So even this material that's been remobilized by the landslide will be still different from the one that nobody touched for whatever 1,000 years. From our point of view, there's no need for such complicated interpretations. Yeah, just let's see it on Google. We're already opening up. So Yashikul. So they proposed supposedly scar from here, I understand. And you see this darker, like a rocky stuff. This is a lithology. There's a lot of images, and you can go and have a look. Yeah, you see the building. They say some kind of hydro station. What they say, hydropower plant. For some reason, they're doing it with conjunction with the Swiss, as I understand, because there was a Swiss flag. So I'm not sure what's happening there. So you see how this happened, and then gradually this kind of local lake formed, and then they're trying to use this, but for how long? And the water been dammed, and this lake formed. They probably should be worried about breaching it rather than. But the glacial material was here probably much older, and if I go there, probably dated, probably will show me. So the glacial material will be sitting here, and then you can even see some. Let's have a look. Hope I don't move too fast. You don't feel too sick. Yeah, look at those ones. So this is the typical kind of, more or less typical glacial material. You see with the lobes of the glacier, and we can see even how the glacier fluvial was coming out. You see there was a mainstream recently. Well, the last time the glacier was here, more probably. So it's very kind of classical for that area. And then the rivers washed it out, this older moraines, but it's preserved here, so you can see shows nicely sitting. So that's what I saw in Ale Valley as well. And there's a big lateral, so there was the true left side. If you can imagine you're a glacier, you're kind of sitting like that. You see there's two basically valleys feeding. So there were one valley feeding from here, one from here, and they joined, and they become this big blob. And probably you see the other side as well, when already glaciers disconnected. So in the past it was all one big one. You see there's another one. So they were sitting. So you can very nicely date it, and figure out. You see it's a very typical kind of for that area, nice glacial material. And then you have you see there's a lateral, and then you see this drop. So then the ice was stuck here for some time. It was still probably connected, these two lobes, but it's become like kind of a lot of ponds and glacier melting down. So you start having these laterals created. And you see in the modern how much like little tiny kind of debris fans here created from the slope collapsing, and the river occupied this. So the river used to be on the side, and then she keep meander. And when the glacier finally down-wasted further down, because if you have this kind of lobby thing, it's mean the glacier was covered, but a lot of material was kind of dirty glacier in terms of covered surface, kind of dark color rather than bad behavior. So, and it's I was sitting here. So if you have these dirty, we call debris covered glaciers, it's mean they will done wasted. You see. So they was stuck here, and they were kind of a little bit out of balance. So they have still kind of dead ice here, which preserved just because of the debris cover, not because of the climate. So they're a little bit lower than the other kind of clean, nice glaciers. But because you have a lot of material coming from the slope, these glaciers more or less, you see modern, yeah. You see this kind of down-wasted kind of dead area. Yeah, not as dramatic, but something like that. And you see kind of cleaner part. So that's these two babies, and you see, see it's done wasting already here. So it's stuck here for some time and it's melting kind of down. So there'll still be patches of older ice underneath, maybe not anymore, and it's disconnected. So it's kind of gradually melting like that. But then the river will rework. You see there's some remnants of older material. So a little bit glaciology for you. Very, very patient about that. And then so they joined here, and I think it's probably was even 8,000, these ones. And then you can even see there's a more recent lobe created, so it's kind of melted here and then disconnected. There's another one, so you can even date each of them, and they will be younger towards up the valley. With the rock avalanche material, there's no way it's going to be like that, yeah? It's going to be everything uniformly, same date, same more or less lithology. And then the rivers kind of wash down, so you can basically, even looking on old deposits, you can see how the glacier was sitting in the valley and retreating. And unless you have next glacier coming up, you see how many deposits are left here, growing. If it's going to be some cooling event, the glacier will grow down, and they will just remove all of that. So there'll be some older stuff preserved if the ice will not reach that place, but otherwise it'll be all removed. And you see there's an older material which belongs still here, so it used to be lateral for bigger, maybe LGM. Here as well, it's amazing glaciology. So if you want to study glacial sediment, you should find funding and go to these valleys. And then you have this odd, absolutely odd boom material. Look how odd it is in the lake form just because of this event. You don't have to be I don't know, super rock slide glaciologist to tell that. And you see all the material, this is a glacial, and on top of it we have rock avalanche. And it's kind of even it says it's run over other side of the valley several meters. You see, it's climbed. You see how it's climbed here? Because of run out. It's traveling so steep slope with such a big speed. So if it's collapsed from here, maybe it took like a minute or two. Just so sometimes they pick up the speed and fluidity, and they're gonna climb over the other slope. Very beautiful case scenario. I don't know how much dating and stuff down there, so it's something to look at. Yeah, so you don't have to complicate it, as observable phenomena can be explained within the frames of single event rock slide model, catastrophic failure of several tens of million cubic meters of gneiss from more than 1 kilometer high slope, which base was covered by the moraine of the Pleistocene Alichur Valley Glacier, so Pleistocene. Likely by moraine fluvial glacier deposits from the Justin Valley, visible true left from the headscarp. That's what we'll show you. So it's been bulldozed, this material, and threw it into the stream, blocking the river, while coarse gneiss fragments spread over, forming relatively thin, blocky apron. Some moraine material spread in front and aside the blocky part, and from this rock avalanche outer zone. Figure 419. Yeah, there. So you should go in the field, and if you can draw this kind of more solid conclusions. Look at the material, unless it's so hard even from the photograph. Unless you go and actually look in the lithology, do some content of different lithologies, different rounding. Look, observe material, describe it, and also do build the profiles of the material, so how they leveled and stuff. Otherwise, it's hard to understand. One of the most didactic case studies in the giant breached Kudara Pasor, probably Rockslide Dam, also considered by Shuk as a moraine dam. However, mutual position of variegated concentric lithological bands expressively visible within this almost 4 kilometer and up to 250 meter thick body, 1.5 cubic kilometer in volume. Shows unambiguously that the material had caved from the distinct headscarp on the right slope of a Kudara River valley and could not be deposited by the glacier moving either along this valley or enter it from right tributary just upstream of the blockage. We should also mention that the frontal part of the blockage is characterized by more than 100 meter run-up that decreases gradually up and downstream. Yeah, run-up that I told you, 100 meters. We've seen run-ups up to 300 meters. Sometimes they kind of climb opposite valley lateral moraine. It's happened in Alaska, I think in the Denali earthquake. They climb a lot. It also shows that this blockage was formed by the avalanche-like motion of gigantic rock slide that has rushed across the wide through like glacier valley and splashed over its opposite slope base. So another important consideration opposing glacial origin of such natural blockages is the common coincidence of the bodies and of the concave scars on the valley slope above them. So this kind of very sharp new scar that I told you, which out of the climatic cirques. Yeah. And these features been formed by small cirques, niche glaciers, or preglacial nevation hollows. However, practically in all cases, the scars are distinctly younger. That's what we talked. So River Cool Dam, the Rivak River, those same stuff. Climatic driven process depending on the elevation, precipitation. Yeah, glaciation is a climatic driven process depending on the elevation, precipitation, distribution, and slope aspect. Yeah, that's what I say. And that's why the more or less similar local glacier features develop an entire uniformly oriented slope at the same elevation, while the steady features are rare or unique, and that's what I would say. So if it's something out of place, Shiva Lake in Afghan Badakhshan, a specific hummocky topography observed in some of the blockage interpreted as indicator of the glacial region. It also typically have many rock slide bodies. So River Cool Lake rock slide. And actually been there's a one big one you see here, and there's actually a couple more different. So suggest the several landslides, and they happen at the same time, and this can happen as well. And there's a flat meadow here, like a darker meadow. It's used to be when this happened, it probably formed a little lake and then it's drained through. See how the river meandered there. So let's have a look on the Google, River Cool Lake. So what they're saying, a flat green meadow, bottom of the small emptied lake, modern glacial deposits contemporarily with the blockages originated much higher than headscarp crown. And yeah, you see here. So that's the kind of modern, well, modern. Maybe it's 8,000 climatic event. I don't know, maybe Little Ice Age. I actually had no idea in this valley, and the glaciers there. So let's have a look. Yeah. Oh, I didn't show, yeah, because I closed it. I shouldn't close it. So let's have a look. So we're talking about River Cool. So River Cool will be, so this is Langar River, and there's a Langar event. I think it's mentioned there too. Just show you, see this landslide too. See how the river kind of meander, and you can see the, again, debris fan, and this deposit. You see how the river incides through, and you can go there and kind of explore the material you have. Little cirque. And we're looking at River Cool. Same river, just further down from Imom. A different valley here. So we have this, you see the lake formed. Remember I showed you in the very first video live stream. Again, we'll have, oh no, we should turn off our time. Oh, the modern picture, very good. So this is the deposit. It's so obvious, like even if you're not geologist, you say straight away, what's this block? It's like somebody put material in, it's blocked the river, and it's created a lake, and you have how river meander throughout. So there's another deposit here, fresh, maybe they suggest same time. This is this meadow, and there's another material here, stuff there, and the big one. And the big one they suggest come from here, yeah? Very, very fresh scar. Still some boulders you see sitting on the slope. So if you like really like, oh, I see this little tiny glacier there, preserved, tiny, and there's another one. So the global warming, you see they're all disappearing, and there's the glacier more modern. You see there's a little lake, this kind of typical landscape, river finding, water finding way out in two places. And there's these floating lobes of the material within the ice here. You see this calving lake actually happen. It'd be cool to go there. And this is the cirques. So this is the cirques we're talking about. You see how high they are, and another, and another, and another. And here you have even a little body. They're going to pick a one, what used to be one, and separated now into smaller cirques. I really love glaciers. And you see how the modern all the debris fans preoccupy this, keep collapsing from here, and here a little even rock glacier formed. You see, maybe rock glacier. See the deposit, or it's just remnants of the old glacier material. So that's what they're talking about, all the glacier material. So you can see there's this landslide here. That one probably fall down from here. Could be spread in two directions. There's a fresher one. You see that's definitely scar for that one, little one. And that's the glacier was here for some time, so we do have some maybe here lateral. That one, you see moraine here, some remnants. It's hard in these very steep mountains, and the water is very active, so it could very easily remove this older glacier material, and then more modern glaciers here. So it gives you the understanding. And actually, I don't see any other material glacially removed. So why we have preserved so significantly here with the lake when everywhere else they removed? So it's another question. And there's a more bigger, see, glacier sitting, still feeding this intensive river. That's the deposit here. More recent. This is probably Little Ice Age. So when we had the Little Ice Age, whatever, 18th century. The last time ice was here, melted down. Could be even younger. I'm not sure. I know this quite limited supply of the snow. Well, there's a snow, but it's not as for example, like a Norway, or you don't have so much cyclones bringing a lot of snow. So the glacier, if you have a lot of snow, it can be more farther down the valley, and depends on your slopes orientation and stuff, could be more up. Yeah, I can tell. I can see how they thinking this is the proglacial lake formed, but it's obviously not just by just looking at the morphology. But it's understandable if you can just have a look like that, and you see there's the moraines. That's the moraine. See this kind of concentric things, the river. See how it was, and then you have this deposit. You see it's sitting on top. It's fall down on top of it, and there's more modern. Keep creeping this slope, very active. And you have this another little landslide caused this. You see mini lake, and then the river incised through here. It'd be cool to go here. There's a lot of outcrops. Go and study the deposits. So you'll have this kind of glacial moraine stuff, and on top you have rock avalanche sitting. Same story here. Look at this mess. So I do have images from the location. So that's probably that one. Yeah, I think it is that one. Unfortunately, Google Earth doesn't allow me to show its images. Because why? So I'm looking at that one. So this one is amazing image. So that's see the deposit here. Filling up the lake. And further down you have landslide that blocked this debris fan. Is it that one? No, I'm lying. Did I? No, it's correct. So you see these deposits. You see that deposit. I didn't switch on my Google Earth. So you see that deposit here, remember? And then this filling up river, and big landslide here, and another. So there's several. Yeah, and there's amazing fans. So you can see it on and this big debris fan here and here. You can see it right now on the picture. Let's switch for the picture. Here we go. So the big landslide there, that's the one debris fan, the one I just showed indicated, and another ones, and you have this further up deposit. You see how the river kind of walking around it, finding its way around it. And sedimentology of these events. So you will see specific how the lake filling in. You can see it in the sediment. And that's another indication as well. It will be told in the paper about. So let's come back to paper. What else I have? And this, I think, a different valley. Yeah. Okay. So Rival Cool. There's a couple more examples. Shiva Lake, Rockslide Dam, clearly visible that the headscarp marked by the small white arrows, unique here. Trying to zoom it more. Here are the arrows. Unique feature much younger than other parts of the valley slope. So you can also see, by the slope. Not always. RG Rock Glacier sitting here. Already that deposit of, don't think it's active. And the Rockslide headscarp. Outline area shown figure. Further down, we're going to look at this deposit. So that's the, you see the cirque. So the landslide fall down. There was some older glacier material. It's blocked everything, and this big lake formed. And you see how the river kind of find its way through. There's a second one feeding. So it's impressive and catastrophic as well. And it's impressive how people live there. So this example, impressive conical molars on top of the Spur rock avalanche body, central Tianshine. That's already from Kyrgyzstan. And see general view of this feature on figure 5 further down. We'll talk about this. Look at this. That's very typical rock avalanche sitting on top, and there's a bigger bouldery carapaces. So I wonder if I have time to go further. So we talk about scars. We indicated that. So more or less similar local glacier features develop on uniformly oriented slope at the same elevation, while the study features are rare or even unique for the large areas. As we can see in the Rivak River Valley, even more expressively in the vicinity of Shiva Lake, specific hummocky topography observed at some of the blockages and interpreted as indicator of the glacier region is also typical of many rock slide bodies. That's what they're saying. You can have this very hummocky type of material, especially if they kind of run out on a flatter, more or less surface, and they have a good run out vertically. What about the hypothesis that the main damming feature are end moraines plagued by the material of bedrock slope failures? We cannot accept very high probability of association of end moraines in subsequent rock slides. There is no reason to interconnect these totally different phenomena. Of course, sometimes such coincidence could occur. Yeah, so you can have a moraine there sitting and a rock slide fall down after already glacier moved, or you can have end moraine formed and then rock avalanche fall down on the glacier and the glacier bring it towards this moraine and dumped it. Or you can have just the rock avalanche block the valley and there's no moraine. Or there could be some remnants of the moraines on the slope sides, but there was no lake before. In such cases, it is difficult to distinguish the exact boundary between the underlying glacial deposit and overlying rockslide debris on the space images with confidence. Serebiruk rockslide dam in the upper reaches of Kızıltenek River, here by 20 cubic million of rock slide debris caved from 800 right slope. So that's example Serebiruk rockslide. We can see the river dammed. You see how it's filling up this lake by this landslide. You can see the scar and all that glacier material here. And some probably glacier material on the slopes here. So despite the presence of distinct headscarp, indicating the slope failure region, is difficult now to say with confidence if the lake has been dammed by the slope failure or had existed already been dammed completely or partially. But the end moraine from the left side tributary valley. Such conclusion require field check here. And another thing that they're showing here, in this diagram, schematic longitudinal profiles of dammed lakes. So you have, if there was nothing there, and then you have rock avalanche, and then the river start filling up because it doesn't breach through, you will have this talweg kind of level of the pre-existing material specific, like sediment formed, and you can go and study, and it will indicate. And then if you have end moraine dam, so as I told you, I'll show you in the modern glacier. So there's a glacier here sitting, done wasted. There will be multiple glacier fluvial lake sediment overturning. So you can look at the sediment deposit and recognize it. It will be different profile as well. See the profile with the material. So that's how it's filled, more or less leveled. With this freshly rockslide dammed lake, it will be under particular angle tilted. So you can go in and build the profiles and kind of reconstruct too. Dammed lake, so the natural blockages, similar depths of some dammed lakes could be expected from the longitudinal river profile. Excuse me. Dammed lakes siltation starts from their upstream part, so it can be hypothesized that the lake bottom level just at the dam should correspond to the original pre-damming talweg. So talweg level is this, which is pre-existing level of the valley. While the lakes dammed by end moraine will be shallower, initially being underlined by bottom moraine. Yeah, and they're saying that there's some numerous rockslide dammed lakes have been silted completely. Some of them will be described in the following chapters. So it means they just fill up with the sediment. Water bodies in deep narrow valleys with intensive talus formation overfed by debris flow prone creeks will be filled by sediment over the entire length. And river damming rockslide has been triggered by strong earthquake, could be accompanied by numerous other rockfalls, rockslides, so it could be filled up much faster. So you can see this lake siltation along this blockage chartim, and they proposed this little system how it worked out. You have multiple landslides, and if you can build up the profiles and reconstruct which one happened before other, so you can all deduct it from your investigation. You see there's a Vir village. You have this deposit here. That's one on the image here. And another one, and you can breach blockage, so you can reconstruct it here. So we just finished with here upstream of this side up the Chartim rockslide dam. The valley bottom is nearly horizontal, indicating significant siltation of the past dammed lake. Assuming smooth profile of the prefailed talweg, thickness of lake sediment just upstream of the Virtangif blockage could exceed 50-60 meters, demonstrating situation shown figure 425b. So that they're showing that it's could be like here. So often, sometimes I told you it depends on your valley. Could have multiple events, so it's absolutely you need to study each case separately. Case study described above demonstrate that neither the presence of marine material in the river damming barriers nor the debris accumulation along the entire lake lengths can exclude the rockslide origin. Combination of blockages and headscarps just above them, along with the specific micro relief of the bodies in mutual position of bedrock debris and quaternity material involved, proves that most of the large neutral barriers in Central Asia river valleys, both existing and breached, have been formed by rock slides, not by end moraines. Some controversial case studies will be discussed in the next chapters. They're just saying that in these study areas, moraines kind of just sitting there and the river find the way through, but if you have these catastrophical landslides, more probably you have this breaching and dam lake formation. Additional argumentation, either pro or contra of rockslide origin, could be provided by analysis of the presence or absence of agglomerate signature typical of rock avalanche materials, despite the original lithologies and identifiable under scanning electron microscope. So that's what I was saying. We can find those finds. This technique was successfully applied for common, and Achik Tashna talked about this. One more method that could be shed a light on this still controversial problem is age determination, especially for those cases where several rock slides block the same river valley. Let's already talk to you, have uniform same age, rather than this kind of younger moraine changes. You can see comparison with modern rock fan and stuff like that. I'll give you example. So this is just some of the as well. In Tajikistan will be all rockslide damped or moraine damped water bodies. If the latter assumption is correct, the ages must be decreased from downstream to upstream. That's what I'm saying. Otherwise, all the dams will be destroyed by the advancing glacier. And they did some beryllium 10 dating in Aksu rockslide in Kyrgyz range. And they showed the glacier did not extend towards the northern front of this range after 63,000 years ago, which contradicts glacier region of relatively young natural blockage. Otherwise, glacier advances during the LGM, last glacier maximum, has been dated in the northern Tian Shan about 49,000. You see, that's the LGM for Central Asia. It will destroy its body inevitably. This data, though quite limited, provides some constraints on the extent of glaciation in Tian Shan. More symptomological and geochronological studies are needed for final solution of the controversial issue of the origin of some river damming features in this region. And that's the thing, so you can go from both sides if you know the glacial history very well in these valleys. Like, for example, more or less, we know New Zealand, we can definitely see those odd cases of these deposits. Or if you opposite, you don't know any glacial history, you can study all these landslides, assume the old glacial moraine, and your glacial history of the valleys will be totally odd as well, not incorrect to start with. But I think the more you, like from experience, the more you have experience in the valley, you see how you go on the modern glaciers. So that's what I started from. You just go on the modern glaciers and you study in that valleys what the modern glaciers do. And you kind of extrapolate it for the older deposits, more or less. Because similar lithology, similar kind of climatic conditions, similar patterns, describe the lithologies, catchment, material, sediment, how they deposited, how active glacier. If you have surging glacier, it will be totally odd type of material. You see, this is actually image here of the landslide blocking the river and filling this lake. That's another valley we just looked at. So it's a rock avalanche material, and more rock avalanche material. And here in that valley, you can see some glacial material further up. So you can actually trace it. And where's this image? That one. So this is the glacier, which is surging. It's in the Karakoram. Look at that. Look at those waves. So and you're gonna, can you imagine the terminal moraine of this glacier? So you need to know about all these things for the whatever glacier you study to have your interpretations. Yeah. All these moraines here already say how they formed. So that's probably more or less similar surging type of glaciers. And so you go there, you kind of study, observe modern situation, and then you can infer. And then you go and look on the older deposits, and you go on the modern landslides in similar valley, and you, if you potentially see somewhere rock avalanche material, you go and study. So you have to be very complex in this sense, and it's only come with experience in database you collect for particular valleys. And they're so different. Like you go to Central Asia, you go to Pamir, you go to Tian Shan, you go to Alaska, you go to New Zealand, Southern Alps, West Coast, East Coast, even different dramatically, but different behavior of the glaciers. Norway, different type of glaciers. Andes, I don't know, South America. Then you go on the Antarctica glaciers and they behave. So you need to have this expertise and walk on the rock avalanches, talk to people, You cannot never see in rock avalanche deposit or walk on it and see the deposit, dig through, study the sediment, and then go on glacial. And if you only study glacial deposits, you cannot identify them. So you have to know, because it's happened in the valley. Yeah, it's all one system, and you need to know that. And that's unfortunately what kind of like discouraged me, that in the modern universities people are very narrow to specific what they do. So because if you're a glaciologist, even sedimentologist, you need to know about climate, modern climate, paleoclimate. You need to know about basic kind of physical processes, chemistry, geography. Otherwise you're going to be very narrow-minded and limited, and you'll be faced with a problem and misinterpretation. And unfortunately the university is trying to kind of like approach like very specific. For if you study, I don't know, volcanoes, you're only doing something very narrow, and you're not broadening your mind, so you don't. But we cannot do this on our planet. Everything interconnected and related. So I hope you enjoyed it. Please like and write me comments and stuff, and I really hope to see more comments, likes, and views, so I can continue. And I hope you enjoy this type of videos. I think I did what I did. I just put this picture. Yeah, that's better. And I hope you kind of got my feeling through about that topic. And I'll see you in my next videos. Thank you so much. Welcome to the live stream. Welcome to the live stream. Welcome to the live stream about rock glaciers and rock avalanches in Central Asia. I'll just check if my sound is going and everything is working properly. So welcome to the next part of, we continue reading the book Rockslides and Rock Avalanches in Central Asia. Amazing book about so many unknown and known cases in Central Asia, particularly Kyrgyzstan, Kazakhstan, a little bit of Pamirs in China. And we look at different slope processes and how to identify them from other events. So we're going through the chapters, see my previous live streams, and I'm making the videos from these live streams as well. But I cut off my unnecessary talking. But because it's a live stream, you have opportunity to write live comments. So just put some hearts in the chat. So just please ask me something, anything about this topic or anything else from my channel, and it's opportunity to have like live discussion. So I'll just see if the streaming is going, sound is okay. All right, so I have this image of the rock glacier here. That's the one that Wikipedia provides us with, and that's how the rock glacier looks like. And commonly in this part we will talk about how to distinguish these processes. We talked about moraines and just the glaciers. And now it's turned for rock glaciers. Rock glaciers, a very kind of tricky point in glaciology, glacier science, because there are people still not kind of agreed, scientists not fully agreed about maybe like a properties or origin of these rock glaciers. Many rock glaciers misidentify as glaciers or debris-covered glaciers. Other debris-covered glaciers misidentify as rock glaciers, and so on. And of course, just make it a little bit bigger. And of course, we have a problem with landslides and rock avalanches, because if you look at at this image right now, it looked like it's some kind of mass of something fall down. And you would think, okay, maybe it is just a rock avalanche, yeah? Because I talked about this before, that rock avalanches, big events, we identify rock avalanches from any other landslides, the different landslides exist. And rock avalanches, ones catastrophic, big ones, and because they're so large and they travel big distances, up to 1, 2, 3, and we have recorded 40 kilometers down the valley, they start to behave as a fluid. And here you can see the features that show you that it might behave like a fluid, you know, like for example, like a honey flowing down the hill, down your table. But in particular, this case, it will be the rock glacier, and there will be the things that we can differentiate it from rock avalanche. And there's not much in the text here about it, so it's quite small, part 4.3 in this book. But we will look at some case scenarios that provided from Central Asia in study area, and also I'll just put a little bit my personal perspective on this topic. And I want to, in detail, look what are the rock glaciers, in particular, so you kind of will be able to identify them from rock avalanches. Also, very interesting that rock avalanches, rock glaciers, and actually rock avalanches themselves, being found on the Mars. And I, from my channel, that I do like other planets, everything in space. It's kind of my personal passion, although I've never done any research in that area. But I do interested in geology on other planets, and in particular on Mars. We have such a good observation of the Mars, so we nicely photograph it. We can see the surface of the Mars when there's no wind storms or dust storms, so you can actually observe it. And because we know what's happening on our planet, we can kind of infer with conditions on the Mars and gravity and all these things, atmosphere, temperatures on Mars, we can kind of figure out, how particular landforms created on the Mars and what can it tell us about Mars history, or Mars, what's happening right now on the Mars in terms of geomorphology, geology. It's very exciting. And maybe if I was in the beginning of my of my science research career, I probably will be looking in planetary geology. It's a very interesting topic, so something for you to look at. So we kind of touch about it. So let's first start with what in the book provided and what they described in the book, and then we will go through other points. Just check one more time that I have sound. I don't know why I want to see if I have a chat as well. So if there's any activities in the chat. Oh, already 3 people. Beautiful. Thank you so much for support and coming and watching me. All right, so I do waiting for your questions in the chat. So rock avalanches versus rock glaciers, that's what the book tells us. So I'm just going to quickly read. Another natural phenomena typical of high mountainous regions that can be misinterpreted as rock avalanches is rock glaciers. Rock glacier, gradual and relative slow movement of debris enriched by the interstitial ice. I promise I did practice to pronounce this word. So interstitial ice, it's the ice that kind of trapped between particles, between debris, parts, whatever, sand, rocks, gravel, whatever we have in the debris. And the main idea here, so it's not so apparent about rock glaciers, but what they're trying to say that the debris, which is rocks that come from the slopes, obviously, and the ice kind of mixed. Like when you're doing I don't know, I'm not such a good with these things, but when you do crush the ice and then you put liquid and you drink it, slushy, people call it slurshie. So the pieces of the juice or whatever you put there, some kind of syrup, mixed between the crushed ice particles, yeah? And if you spill it on the table, it's gonna spill, uniformly, more or less uniformly, depends on the particles, and it will move together. So the liquid, viscous liquid, your syrup, and your ice particles gonna move together. So the syrup and the ice blocks gonna move. But if you have just the ice floating in your syrup, when you spill it, the syrup going to flow by itself in particular direction, maybe obstructed, maybe not by the ice, and the ice will behave by its own. So in raw glacier, what we see in separately from in normal glaciers, glaciers could be all sorts, different varieties. And I do want to make a video about it because it's my kind of one of the point of research, and I constantly want to thinking to do it. Different type of glaciers, we can find them, how they different. But the glaciers behave, we have ice, this kind of core of the glacier, which behave like a glacier flow of the ice. You have particular lows, how it's flow down the valley, and you might not have something on the surface, like debris cover, you might not. You might even have rock avalanche on surface of this glacier. But the movement of whatever's on top going to be governed by the main laws, how the glacier itself is moving down the valley. But when we have rock glacier, that's where we differentiate them. So they kind of, I would even don't differentiate them as glaciers. It's kind of different, alien entity from glaciers themselves. It's behaved differently. And it doesn't behave like a debris flow, mud flow, because you will include, instead of just water in the debris, which is debris flow, mud flow, you have here ice. So, and it will be governed by, usually it's in permafrost area, so high in the mountains elevation. We don't see so much like in Siberia, raw glaciers in a flat area because you don't have, gravity pull to flow down the valley. So it should be some kind of hills, mountains usually, supply of the rocks, a lot of rocks supplied, and permafrost situation. And they do slow move down the valley. And usually it's kind of like probably related to, time of the year. So when it's warmer, they flow a little bit further down the valley, and then it's colder, they kind of a little bit slow down. So that's my understanding. But I never worked with raw glaciers. I know them, I met them a lot, and I differentiate from them. But I never actually observed them for my research. So let's read further. So you have to understand that the raw glaciers and the glaciers, it's quite different, different species. Okay, in general, debris transported by raw glaciers move like a crawled belt, so that boulders lying on top of the body move faster and gradually fell from its front, being overlaid by the inner part of the raw glacier a bit, which is totally different from rock avalanches that can be derived from the internal structure of the deposit. So that's kind of what Haim and Strom are talking about in their research. And move entirely is a laminar flow. So the rock avalanches, what they're trying to tell you that when you have rock avalanche or any landslide, whatever type of movement, your material will move once, hopefully. It can be reactivated later on, but it's usually just move once down the valley, and it's behave like it will behave like one event, and then it will just stay like that. But the raw glacier is any other glacier. It's constantly been moving down. So if whatever boulders you're going to have in front, they're going to be getting entrained or dumped. And material, as I said before, get entrained with ice, whatever slushy, icy medium you have here. So it's all behave like a one. And you can kind of tell it by vegetation on top. So if you have rock avalanche landslides and have some time pass, you will start quite fast develop vegetation like bushes or first the grass, lichens, grass, and then some kind of bushes and maybe even trees develop. So depends on the climate. So in Central Asia, there's not much trees in these areas, so it's hard to tell. But if you look through Alaska, a lot of Alaskan glaciers and rock avalanches and raw glaciers, you will see if you have raw glacier, there won't be trees or bushes there because this material still moving. Once a year at least, it will move. But if you have rock avalanche even sitting on a glacier, there's ice underneath. You would think. But it won't be like moving like ice underneath. It will be just passively transported. Like when you put the suitcase in the airport on this, moving, how they called things, that moving the luggage away or bring it to you. So it will be just like your luggage sitting on top. Nothing happened with particles in the luggage itself, but underneath the glacier flows. So you will start seeing the trees, even the trees start growing. And we see on Sherman Glacier, for example, after several years, after the Good Friday earthquake, we see the trees, pines start growing. And it's kind of like pine trees growing on top of the glacier, which is possibly impossible for debris-covered glacier or glaciers. But you can tell straight away there's a rock avalanche material that's passively sitting and just moving down the valley with the glacier. It depends on activity of the glacier, of course. So that's that's like mine and straightforward observation. We're just kind of surfing through Google Earth. I can see those things. Debris is supplied to rock glacier either by real glaciers upstream. So you have material brought down by the glaciers or by the numerous small rock falls and snow avalanches from the steep valley falls. And usually those rock glaciers found in very kind of steep areas where there's not enough accumulation for actual glacier, maybe not enough precipitation through the year, through the colder period, or there used to be glacier, but it's melted away and the rock glacier kind of developed. And there's two types. The rock glacier can appear by itself on some particular slope, or it can appear from used to be big glacier, and then this glacier get choked over with too much material, melted away already, and something up in the cirque left, it will start behaving like a rock glacier. So there'll be like this transition point when normal glacier, heavily debris covered glaciers start behave like rock glacier. The frontal lateral slopes of these accumulations are inclined, the angle of repose typical of the class-supported mixture of angular boulders and fines. Yes, so you can actually, if you go and measure it and compare it with rock avalanches, you will see this difference. Gross glaciers are widespread in Central Asian region, usually above 3,000 meters sea level. That's what I told you because of the specific condition. You have to have some kind of permafrost or partial permafrost. No, you can't be partial permafrost, at least of frozen time for most time of the year, so called permafrost. And sometimes really look very similar to rock glaciers. Rock avalanches, sorry. So rock glaciers look similar, and that's what we can see. They often dam small river valleys. Well, obviously because they're kind of flowing down. So we will look at ones particular that are provided here in the figure 4.29. Sound discrimination between rock glaciers and rock avalanches is based on the absence of the head scar somewhere above the rock glacier, comparable in volume with the deposits, which is essential for rock avalanches. Well, it's one very, very common thing. Just in general, if you want to identify rock avalanche, if you have big rock avalanche, you will find a scar. Scar, it's just like this kind of fresh, we talked about this before, fresh up on the wall collapse area from the slope. But again, if it's pretty old rock avalanche, or depends on you have too much like snow stuff, on the slopes, or very active slopes, so everywhere rock falls happening all the time, it might be hard, could be tricky. So keep it in mind. Or you might have rock avalanche happened back in the day, material down the valley, or even been removed by the river, so you have this nice scar still preserved, and then you have the rock glacier developed in a cirque that created. And then if you were a landslide person, you would think, okay, maybe this is the rock avalanche there, because I see fresh scar in the cirque, and in the cirque nicely sitting, this kind of rock glacier, which you think is rock avalanche. So again, there could be a lot of confusion, and you have to go and observe it. Another discriminating feature is the run up of the to the opposite valley slope, or any significant obstacle which is impossible for other slowly moving rock glaciers, but it's common for rock avalanches that move by inertia, releasing enormous momentum gained during the initial downslope acceleration. And because in high mountains you have deep run out areas. So let's look at these pictures here. Just have a look how they look like. Maybe I will zoom in a little bit. Oops, like that. So they, if you have a rock avalanche, there will be scar here or here, source where it's come from, and they're gonna travel, like vertically, maybe half kilometer, and then down the slope another couple kilometers, just vertically, but it's also to the distance. So they picking up the speed, and even they spread thin. So this is actually rock glacier here, not rock avalanche. But imagine if this was rock avalanche. So I will have, first of all, much thinner material left here on the steeper slope, deeper material here. So it's gonna basically like when you spread, sand from your bucket, down particular topography, it will, fill it in, redistribute like that, and it will behave float, and sometimes often it flows towards the opposite valley, and we can see like a remnants of the deposit there, and the river will cut through with time. But you can see here we have this active rock glaciers, so you have constant supply of this frozen, defrosted, permanently, constantly slush debris, and even we see the river here. It's kind of going over it. So if a rock avalanche, you will see the deposit sitting over the active river flow only in the moment of deposition, and then next season, next several years, it will be reworked or dammed by the river. So these things you should look at, and obviously I already said that you will dam it, so you'll have water accumulated there because the river couldn't find the flow through the deposit, this kind of stuff. But with the rock glaciers, because it's happened slowly, you see this material moving very slowly all the time, you will see the difference, straight away. So you have to kind of turn on your logic, your Sherlock Holmes, as I always say, investigator, in the field, to understand. And then again, remember about this vegetation problem I told you. You can see these more kind of dead lobes, which have some vegetation developed, maybe lichens, maybe some kind of grassy things growing, mosses. But then you have this active part with a constant flow, which not going to happen on rock avalanche. So rock avalanches was at least 10, 20 years old rock avalanche. You will start develop some more vegetation. And of course, you tell me, okay, there's no vegetation everywhere else. Why do you think there will be vegetation? Well, it depends on your location. So if you're in Alaska, for example, or New Zealand, there'll be a lot of vegetation already developing. Because also rock avalanches, because of the crushing out of material, they produce a lot of finer particles, which very fine, submicron size, and they're very great for vegetation. Vegetation loves this. All right, so that's what the text told us, and they suggested these two rock glaciers, not rock avalanches, and I'll show you in the Google Earth. I have the position where they are. We're just gonna have a look where they are. So this is our Issyk-Kul Lake. Issyk-Kul Lake, the pearl of the Central Asia. A beautiful lake. So we have, just to zoom out for those who kind of disoriented where we are. So this is the India, this is Tibetan Plateau, and Tian Shan is here, kind of like squashed with the in the stand, squashing into the Eurasia plates, and we have created a big plateau, Tibetan Plateau, with all these mountains, the biggest in the world. The Nepal. You have all these Everest, mountains, and from the northern side, we have the countries, beautiful countries, Kyrgyzstan, Tajikistan. We talked about this in the first stream, Kazakhstan, and of course Mongolia and China. And Issyk-Kul is kind of this trapped lake here, and it's quite big, and I actually was lucky to visit it. And for some reason, around Issyk-Kul is quite high, these mountain ranges here, and we have a lot of rock glaciers there. And I think it's rock glaciers not everywhere. You can find them not everywhere. So some mountain ranges they just have glaciers, and then just nothing, they just melted away, debris covered glaciers. But in some places the rock glaciers develop, and it could be something about particular factors, elevations, permafrost situation, and rock supply, geology, and maybe orientation and composition of the slopes, these kind of things. And when you looked, if you just kind of surf through these mountain ranges, this Ilia Latau National Park, so you will find quite several rock glaciers actually, which could be, people would think, they could be rock avalanches, and there will be all rock avalanches as well. So that's why we talk about this, because it's very, very, very common. So when we zoom in here, there's these rock glaciers, which mentioned in text, and you have nice, beautiful pictures. But if you look closely, there's actually much more. So this image, a little bit, I see the snow cover on that one. You see these lobes, so it tells you this or glacier or rock glacier, normal glacier, rock glacier. But I can tell you already by this very intricate, kind of like a mud flow patterns, you see. that it will be the rock glacier. You see they have this slope one after another. It's very typical for this, like a spreading, I don't know if you ever work with something viscous. I did some experiments with, how it's called, this sugary substance they put instead of sugar in the baking. Oh, it's come out of my mind. Okay, for example, honey. Yeah, I wanted to use honey, but it was too expensive. Waste of honey. So use these other substances. It could be like agave, liquidy syrup, this kind of stuff. It's very viscous. And if you put some dust on top of it and you let it flow with a little bit of slope, it will create this type of pattern. So it tells you it's very slower viscosity, bigger viscosity, slower movement than, for example, for normal glaciers. Yeah. And some of them will be already dead material, and the examples that we see in the paper, in the book, it's that glacier. You see, it's quite big. So take it a start from here, the cirque, 1, 2, 3, 4 cirques feed in it. You see, quite a big area of feed. And maybe up here, there's like a normal type of behavior glacier. There's definitely that one, rock one. That one I'll question, but here looks like a rock glacier, and it's end up in this big lobe. But you see how it's here. You can see still movement in the lobe, so it's not passive; it's still active. And you see how it's taking over the river. But the river doesn't. If it was just a rock avalanche, the river will probably have. You see the big outcrop, and she will wash out the material. But because it's constantly flows, constantly supply this material, river can't cope with it. So I think she just find a way underneath. That's what's happened in that area. And you can see there's some slope features here, maybe these ones, but it's just some kind of debris fans / developing. There's a lot of images, so I recommend you to go into this valley and explore. There's a lot of image with people provided. This people go for trekking there. And there's another lobe, and that was so interesting. Look how big platform it developed. So there's all this material that's sliding down, large platform. So if you look about elevation, 3,400 meters, 3.2. So it's about 200 meters. You see like a platform developed. And this raw glacier, you see how it's flowing there down the valley. So this on top is just the snow. Probably the image was taken, I can tell you, in February, which, logical, there'll be snow. But you see the lobes and patterns. So it's very typical for rock glaciers rather than normal glaciers or debris covered glaciers. You see the patterns as well, how it's spreading like a viscous and eventually just kind of dumping material towards the river. And see how the river finds its way a little bit around it. She's a little bit trying to move materials, quite active river because we're more up the valley, but material still brought by the raw glacier. You see here slight damming happens, but probably this stream is not strong enough to cut through. Yeah. You see the two different streams, and there's another one as well, which is not recorded, not suggested in the paper. You see, so this is all the raw glaciers, and personally, when I kind of fly through this valleys, there's a lot. Look here. Here there will be some small. They could be very tiny. These raw glaciers. It's kind of like some people say debris flow, mud flow, but they're constantly moving, and they will, as I say before, they will be moving with situation with permafrost. Sometimes faster a little bit in a warmer period. You have more supply of the snow, and they will be a little bit reactivated. But they are different from glaciers themselves. Yeah, so there's a lot. All these little valleys have something going on. Look, yeah. All right, so it looks like it's not such a good image, but unfortunately not always. If you go through historical, probably we'll see better images. So the people suggested some, I'll just switch. People have some pictures. So that's the rock glacier just from Wikipedia, and I did open it somewhere. Yeah, these ones. So that's how the valley look like. So it's just a picture of this local river and how much material there are. So it's not rock avalanche or rock glacier. Here is just a debris fan here on the side, washed, washed away by the river. I'm not actually sure where exactly this picture taken, but you can see the geology and settings of this valley. Yeah, so that's a lot of this kind of coarse material coming from the slopes. It's a very important condition for creation of these rock glaciers. It's another image, and here you would see this material actually moving down, kind of like a debris mud flow. Yeah, so this is just a normal slope processes. This is probably supply coming from here, from those slopes. You see the very active, a lot of material moving down, and you have your permafrost, high altitudes, and you have this creation of the rock glaciers. And I wanted also to return to Wikipedia and just have a look what the Wikipedia says about the rock glaciers, because when I was doing research, it was always, you cannot find define definition, okay, buttery butter. You cannot find definite terminology for the rock glaciers. There's still people who claiming the rock glaciers should do this, or this, and often they get confused. I told you it's the debris covered glaciers, or some glaciers that kind of in transition between debris covered overchoking towards the rock glacier, and they may get misinterpreted. So, and some people totally don't understand. They confuse rock glaciers with normal debris covered glaciers, or with rock avalanches, or deposits, or with mud flows and stuff like that. So let's see what the Wikipedia says. Rock glaciers are shielded from the melting by a layer of rock, allowing them to stay frozen in location where they would otherwise melt. So I would not agree with this definition. Sorry, Wikipedia. Because you can have normal glacier that shielded by layer of rocks, and it will be debris covered glacier, or the glacier which just have recently rock avalanche fall down on it. And we know there's a glacier, smaller ones, where you have gigantic rock avalanche to just cover all glacier. So it's already by default, won't be true. Allow them to stay frozen in location where they would otherwise melt. And that's not true too, because rock glaciers, they start the kind of existence produced in a higher elevation where they are permafrost. And because there's so much material, the slushy, half-frozen material created, they start moving down the valley. And down the valley, that's not enough warmer days for this material to fully melt, so the body still exists. But the difference between just the ice and this slushy, because it's very well kind of mixed material, rocks, whatever, rock debris, with the ice. So as I told you, this example of I think they call it slushy when they crush ice, they put syrup and you drink it when you're a child. So rather than, just whatever scotch and rocks, people drink. So differentiate this. So sorry, Wikipedia, not agree. Formation. The two known factors that must be present to create rock glaciers are low ice velocity and permafrost. All right, okay, we do have to have it. So you just contradict yourself because you just say permafrost. Layer of rocks, so you don't need permafrost. So okay, I'm just telling you, don't believe Wikipedia and everything they say here, and it's all work in progress. And maybe there's such a confusion here because so many research which differently define rock glaciers. Most glacial rock glaciers what is that? What does that mean? That's a little bit strange. Are created by the recession of the debris covered glacier. So it could be like a transition, as I told you, when the glacier get overchoked and eventually. But in my we would consider it as a separate, landform, separate behavior. So I would say it could be in the past it was debris covered glacier, but now it's behaved differently. Glacial rock glaciers. That's very weird. Okay. Are often found in cirque basins. Well, that's normal, where rocky debris fall off the steep slides and accumulates on ice glaciers. All right, so I'm totally not understand what does it mean, and everything I just explained you, this misconfusion, that's absolutely just confuse you more. As glaciers shrink, they become increasingly covered with rock debris. Well, not necessary, but okay. Eventually, the glacier ice may be completely covered by the debris, although the ice core continues to float. No, well, you see, so if you have ice core which continue to float, you have debris on top which move kind of passively, This is now rock glacier. Rock glacier behave like a one entity with the rocks and the ice. So, yeah. That's why I'm not like this article is not, I'm not fan of it, and you just have to kind of dive into research to understand it better. And you can even see it from this image. So that's the image they provided, the way, it flows. If you have ice underneath it flowing and passive rock on top, it's not going to create these lobes of obviously debris mixed with whatever frost, permafrost ice. So that's my understanding of that topic. All right, so the next thing I want to cover, it's the actually I have an article which I found, which maybe I will do another live stream about. It's types of glaciers on Mars. That's what I told you that, in the beginning. I'm interested. I'll find this article. You see, it's free, available for you, so I'll download it and I'll make a separate, maybe just a live stream about it. There are glaciers on Mars. There are glaciers on Mars? Question mark and exclamation mark. It's a question or not. So what they say. So when we are just gonna exploring the Mars, and you see how nicely we can see, we know we have ice poles on the Mars, and which not actually ice, it's carbon dioxide frozen, as much as research tells us. Although none of us been on the Mars, so we cannot say for sure, but that's what all the instruments tell us. Polar ice, and there's some water ice, and there's combined water ice similar to the Greenland ice sheet on Earth. That's what they say, the polar water ice, made mostly, but there's also carbon dioxide. That's what, permanent layer of carbon dioxide ice on top. This is because temperatures in the Mars so cold, and carbon dioxide become, frozen state, through the year. That's how it looks like. And actually, when we observe the Mars poles, they do change, and it's amazing. And I can tell you my experience when I had my first telescope when I was child, maybe teenager. Well, I don't remember, something. I was still at school. And I get this, not very good, but this common telescopes they sell for kids. But you can actually see very well Mars and Saturn and Jupiter. You can see in the Jupiter 4 satellites. So I encourage you to get, even in a good binocular these days, you can see Jupiter with the satellites. And observed Mars first time in my life, and it was amazing. It was the year when the Mars was quite close to our Earth, like one of the closest position, and you can even see it, like a red dot on the sky with your vision, if you have good vision. And I used my telescope. I found the Mars. It was quite tricky because it's moving, very fast because it's quite distant. But you can see the poles, the polar caps, that this snowy whatever poles on it, and I could see it in my telescope as a child, / teenager. It was amazing. It's one of those experiences, you can't you can't repeat. I probably should zoom in a little bit more, like that, So what they say, there's polar glaciers beyond the margin of the polar ice caps. Korolev crater is an impact crater which is filled with ice. So let's have a look. Yeah, you see those lobes, that's what's suggesting. It's probably floating down ice, whatever is carbon dioxide or just the water ice. And in the Google Earth, I think, I don't do it now, but in the Google Earth, you can go in and switch for the Mars. You can switch for the Moon. You can switch for the Mars. You can switch just the stars, sky, and Earth, obviously. So you can actually kind of explore and see good resolution of images, of the Mars. So I suggest you to do it. So this article, we're going to go through it, but just here, what I want to say. So these are polars, and that's what they find in the mid-latitudes, where commonly you can find some glaciers. So they say they're made up of nearly pure water ice covered in a thin blanket of atmospheric dust and debris from nearby hill slopes. Obviously, there could be nearby hill slopes that supply it, not like on our Earth, in the mountains we have very big supply of rocks, but atmospheric dust, because we have these dust storms on the Mars, and I have a video about the Mars when I talk about this. It's enormous. Those dust storms, they crazy, and I would imagine after one of those you have a lot of debris on those on those glaciers or whatever ice caps you have. And as a result, I think because of this supply, maybe even more than just the nearby hill slopes, you will start having more raw glaciers than just the normal glaciers or debris covered glaciers. And actually, a very cool movie I like, Martian, with Matt Damon, when they show the Mars, and there was covered this dust storms as well, if you're interested. Mars mutilated glaciers are thought to be the most similar to coal-based debris-covered glaciers in the dry valley of Antarctica, so they suggested. Actually, I was surprised. Some people don't know that there's a place in Antarctica we call Dry Valley, where there's they call Dry Valley because there's no precipitation, such as this, like basically air masses with liquid with drops, whatever, with the rain doesn't reach it, so you never have a rain there basically. But you have the slopes, you see there's some snow, and there's places where there's no actually ice cover. There'll be this kind of debris, slushy permafrost areas, but there's no thickness of kilometers of ice. Because I think some people thinking that Antarctica is just like uniformly covered, piece of land with just ice, but it's not. And if you're interested in discussion about Antarctica geology and glaciers and what is underneath and all these questions and mysteries about Antarctica, I'm very happy to cover it because it's on my list, but just didn't have time to look at that. So that's the Antarctica. You see this debris-covered glacier. I probably have a question, is it debris-covered glacier or it's a raw glacier, and who can tell? Not sure. So the glaciers on the Mars, they behave like a viscous flow features, and that's why we kind of thinking, okay, there must be the raw glaciers or debris-covered glaciers. So they find these glacier-like forms in lineated valley fill, and they different in size, and the glacier-like forms, they're similar, a few kilometers long, the ones that we find on our planet. And because you have this, you see this one of the glacier-like form in the Mars, it could be behave like rock glacier. So as I told you, it's not actual glacier, but behave like rock glacier, or it could be the actual glacier. So we don't know unless we go there and observe it, or any other instrument can observe it for us. But you can see, we see absolutely similar features. It's flows, have these patterns, have the slope, have kind of terminal area, moraine, when the material probably dropped. You can see here some surface processes removing material from the side. Are they active? Could be like still, so they used to be active, created this feature, and then it's just now stagnant still. That's the question I have. So, but I think because we already started photographing Mars for several years, many years, decade maybe, we can see the difference. So if I have absolutely same reference point, photograph, I will see if it actually flows down or any ridges changes or not with time, this kind of stuff. And that's my main argument for how to identify rock avalanche from raw glacier. And I would say observe raw glacier. Raw glacier through the year, put stakes, go, with GPS point, record some boulders and see if they're moving down or not. So you will pick up the movement, even just remotely through the satellite images this day. You might satellite images sensitive enough, you can pick up the movement. Rock avalanche material not gonna move unless it's in the river, outcrop, when it's just sliding down, because river removing the slope, like normal not the reactivation, but just destroying the material. But in the raw glacier, you have whole the mass from its start till the down the valley will be actually moving. Some way slower, some way faster, but you will pick up this movement throughout the whole body of the raw glacier, which not going to happen with rock avalanche. Rock avalanche fall down once and stay there. There will be some reactivators, so it could be another event, another earthquake, and the rock avalanche just, this material will be moved down the valley farther or disconnected, or the river can cut through, something can happen, or there's another rock avalanche can fall down on top of it. But most of the time, it'll be just stagnant sitting there. And that's why I told you vegetation will establish. So that's what's happening in the Mars. There's another big thing. See these features, they're floating down somehow. They even kind of going around the obstacles. It's pretty amazing. And it's a big size. Look, this is 5 kilometers direction to the north. So it's quite a big feature. And it's quite a thick, created like a platform, yeah. So the Mars, it's interesting. Glaciation, lowland plains on Mars as well. So we have this kind of like more low bed debris apron glacier-like forms here. So you can have a look. This cool article, and this ice-free lowland plains as well here. The circlish things probably, I don't even know, could be some impact areas. What else we have? Impact crater glaciation. Oh yeah, so apparently it's quite common. So you have impact crater, and that's been occupied by this ice and dust. And on the slope, on the sides, it will probably, obviously, because of gravity, works. there's a less gravity on the Mars, but there's still gravity, and there will be material will still be trying to find a way down the valley. Yeah. All right. What is here? This is another map. So that's it. How old the glacier is on Mars? Who knows? Some even as old as 1 billion years, and some of the hundreds of millions of years old. That's a big question, because how do you know? How can you tell? But okay. So yeah, that's what this author tells us. So just have a look if you're interested, like me, in the Mars geology. But if you keep in mind this image, and I will show you this image just before I show you. It's pretty similar, isn't it? Look at that. Just like purely geomorphologically, we can see, okay, there's some kind of correlation and relation, how it's formed. Yeah? So just compare that and that. Central Asia, Rock Glacier, Issyk-Kul, and supposedly Mars. All right, so that's what this basically part tells us about this. I think it will be enough for today, and I will make a separate video from it, and maybe while talking about some processes, I'll usually, when I re-editing these videos, I add some better illustrations maybe. So next point, we will talk about the fans as well, and we're going to go through more case scenarios and bedrock landslides in the contemporary glaciated region. So when they fall down on the glaciers, and I did some work about that too, as you know, and we'll talk about that and look at some real case scenarios. And there will be the end of the part. Which part is that? 1, general information. And we will move to, see, it's quite a big one, so I'll leave it for another day. And we have next chapter about the bedrock landslide types we'll cover next, based on the case scenarios of Strom and Kanadbek that they study in Central Asia. Thanks so much. I just have a quick look if there's any comments. No comments. Please comment at me, ask me questions. I'm really interested in a real life feedback, and of course, write comments about questions or something you not agree with me about, or something you're actually interested in, because I can make a video about it, and I will be cool, because it will be not just interesting for me but for you too. Thank you so much. I'll see you in the next live streams and next videos, and please share this video with somebody who might be interested in these kind of topics. And it's very fascinating things which not many people talk about. I don't know, YouTube is like just an ocean of so many topics people discuss, but I think in the future we kind of move in direction there'll be more science topics, more other historical topics, anything like more important for us, more substantial, something that exists beyond temporary affairs on our planet. So I hope you all be healthy, in peace, and I'll see you in my next video.